My name is Jean and I'm a surgeon at Grooteskier Hospital, one of the most famous hospitals in the world, home to the first human heart transplant. I'm also a senior lecturer in surgery at the University of Cape Town. I lead the Klopper Research Group, and one of our main aims is really to teach biostatistics, to help people, to empower them to do their own statistical analysis. Not everyone is blessed with their own large research teams and access to statisticians, and I think it's important for you to learn how to do your own data analysis. It's also important to know something about data analysis when you read journal articles. How can you look at those articles? How can you judge them if you don't understand a bit of data analysis, a bit of biostatistics? Now, there are a variety of courses out there on the internet about how to do statistical analysis, biostatistics using computer programming languages. And I think the best ones all have one thing in common. They tell you straight on that there is no better way for you to learn how to do this than to sit in front of your screen with your keyboard and play with the data. You've got to sit and do this yourself, work at it. It's no good just really watching someone do it. So I really want to encourage you to create your own data, to import some of your data, and eventually do all this analysis yourself. Do it over and over again. Speak to someone else who's doing it as well. Get involved, get a group together. But really, you've got to get your fingertips on that keyboard. So in this course, we're going to use the Python programming language. It really has become the de facto standard when it comes to data science. It's really become more and more popular. And some of the reasons for that might be that it's a powerful language that can do so much. You can do web development, you can do game development, you can develop applications for your phone, and you can do biostatistics and a lot more. It's also quite an easy language to learn. And if this is the first time that you see a computer language, Python is probably the way to go. So in this course, we're going to use the Python programming language. It really has become the de facto standard when it comes to data science. It's really become more and more popular. And some of the reasons for that might be that it's a powerful language that can do so much. You can do web development, you can do game development, you can develop applications for your phone, and you can do biostatistics and a lot more. It's also quite an easy language to learn. And if this is the first time that you see a computer language, Python is probably the way to go. In this video, I want to show you just how easy it is to install Python on your system. That is, whether you use Windows, Mac OS, or Linux. It really is no problem. There are a couple of very good distributions, and by that I mean packages that have Python and most of the libraries that we are going to use in this course. My favorite is the Intel distribution for Python. You can simply type in Intel distribution for Python in your favorite search engine and you will get to this page. It is, as always with Python, a free installation. So all we're going to do is hit free download. Once we do that, we get to a page where we simply fill in a few details. Hit submit and that will bring us to a downloads page. You can clearly see if you use this drop-down box that you can install for Linux, Mac OS and Windows. Please always choose the newest version. At the time of this recording, that would be update number 3. And you can choose either Python 3.6 or 2.7. This course was developed with Python 3.6 in mind, so please select that. If you click on the release notes, you'll get to a page where you will find some release notes on update 3, if that was indeed which you decided to download. That'll bring you to a page that contains all sorts of information, and very importantly, it'll help you with the installation process. Now, if you simply double click and run the file that you did download, all the instructions will be there. But in case there's any kind of problems, you can read this release note and it'll tell you all about the installation. If you don't run an Intel processor in your machine, or you're not sure, or you wish to use a different distribution, I would really recommend Anaconda. Just search Anaconda Python. You see the URL there, it's www.anaconda.com/download. And once again, it'll be for Windows, Mac OS, and Linux, but this time it's really agnostic as far as the processor that you are concerned, that you do use. So there we go, Windows, Mac OS, Linux. Choose the operating system of your choice and then stick with Python 3.6 or newer to download. Once again, very simple, just double click the file and run it. Once you've installed your version of Python with all its libraries, it is a simple matter of opening a terminal window or command prompt as we do have here in Windows, and all we're going to type in is Jupyter Notebook. As simple as that. If you have this Anaconda version, there's actually a little navigator program that comes with it that will open a user interface where you can simply choose a Jupyter Notebook. And that's going to open your folder structure right here in your default browser. Very neat indeed. And all you have to do is to navigate to where you want to save your documents or open a new document. I have now simply navigated to my Dropbox folder, New MOOCs, Biostatistics Fundamentals using Python, and we see all my Python files here. This is where I save all the files for this course. To start a new fresh notebook, we're going to say new Python 3. And we have a brand new notebook. Now the notebook is the environment in which we're going to do all of our coding. It really has been a phenomenal series of developments that have led to this Jupyter Notebook. It started off as an IPython notebook, but is now called a Jupyter Notebook. It runs right inside your browser and really allows for the creation of the most fantastic documents. Let me show you around. First of all, because we've opened a new document, it'll be untitled, we can simply click on that and rename this. Let's just name it test for this instance and click rename. It is now test, and if we do scroll, we'll see that we now have a test notebook and a little circle there that it is running. And most importantly is this drop down box here. Code and Markdown, those are the two that we are going to work with. And what they do is determine the behavior of these cells. Do you see this dark area? That is a cell, and I can start writing code right inside that cell. But before we get to code, let's just format our document. The format of a notebook document relies on a language called Markdown, but you can also just write normal HTML code. Don't worry if you're not familiar with that. It really takes a couple of seconds to get used to. So let's change this cell from code to Markdown. It is now a Markdown cell. And let me show you the headings first. If I type a single hashtag in a space, that means the biggest headings. We've all seen web pages. Some headings are bigger than others, and in the standard form, there are 6 levels of headings. Heading 1 is the largest, to heading 6 is the smallest, and it is just the number of hashtags that we put down. So we're going to put down one hashtag, and I'm going to call this my title. And I'm going to hold down Shift and hit Enter, or Shift and Return if you're on a Mac, or you can click Run there. And look at that, we have my title. Now I will explain a bit later why my notebook might look a bit different from yours, and I'll show you how to get your notebook to look like this. But we see a beautiful my title there. For the second cell, see a new cell opened automatically because we used Shift and Enter or Shift and Return. Let's make this Markdown as well, but we needn't go to Code Markdown. We can just use a keyboard shortcut. That's Escape, M, Enter or Return. And you see immediately this changed to Markdown. So Escape, M, Enter or Return. That's M for mother. Now let's make this a H2 heading. That's a slightly smaller heading. And let's call this my second heading. Shift and Enter or Shift and Return, and you see that is slightly smaller. And you can go up to 6 hashtags. Let's make the next one a Markdown cell again. Escape M Enter or Escape M Return, and we have another Markdown cell. And I can type normal text here. This is a normal line of text, and we can go back and capitalize the T, And there we go, it's a normal line of text. And if I run that, I have a normal line of text. And you can see this is like a Word document. And you can write a beautiful report. No problem whatsoever. Let me show you something else. Code, markdown, and all we're going to do now is put little stars. First bullet point, and I put a space after the star. Second bullet point, star. Now I'm going to hit the tab key to make a little indent. First sub. Can we call it a sub bullet? Is that a word? Sub bullet point. There we go. And we'll delete that P. Shift enter, shift return, and look at that. Bullet points. No problem whatsoever. And there's quite a few of these things that you can do. Look them up online. You can create beautiful, beautiful notebooks. You can print them out. You can share them with your colleagues. And then code, of course, is the other type of cell that we're going to be busy with. And it's very simple. We can just write 2 plus 2. And I put spaces in between just to make it look better. You needn't put those spaces. Shift enter, shift return, and we get our first result, our first coding result, 4. So you can well imagine you can create a nice document. You can put code in, do your analysis, and even put plots right in line inside of this coding environment called a Jupyter Notebook. As far as we work, from time to time, this will be auto-saved, but we can just click Save just to force that. And under File, we see we can create a new notebook, open some notebooks if we don't want to navigate to it from our folder structure there, make a copy, rename it, save and checkpoint, create a print preview, and even download it as a notebook, as a Python file, as an HTML file, and even as a PDF file right here at the bottom. And there is so much you can do with this notebook file. And in time, we're going to use the majority of these features. I'll show you just how it works. You'll familiarize yourself with it, no problem whatsoever. So we've looked at how to open a Jupyter Notebook. We open the command prompt here on Windows, or whatever the equivalent is in macOS and Linux, a terminal, and you've typed in Jupyter Notebook. If you read carefully there, it says use Control-C to stop, and it's going to be slightly different on a Mac, how to stop your notebooks from running. Remember, this is actually a web server. A server is being created that is serving up the web sites here using some JavaScript. Don't worry about that. So here we are inside of a notebook. Remember, very easy to get to things. There's a folder structure here on your computer. You can go back here to the home directory, and it's a normal file browser that you get on your operating system, and you just navigate to where you want to be. So we are in Dropbox, New MOOCs, Biostatistics Fundamentals using Python here, and I can see this little circle here. It means the notebook file is opened, and indeed it is opened. I've worked on it a little bit. I can save it. You see checkpoint created, it says there. And now how do I close it? Well, I say File, Close and Halt. So save it first, wait for it to be saved, then say Close and Halt, and it's gone. And now I can actually just shut down this Jupyter Notebook environment completely. And here we are, just left with a command prompt or terminal. Here in the background, you see the beautiful Erasmus Bridge in Rotterdam in the Netherlands. That's not what it's about though. So we're inside of our command prompt or terminal again. I'm going to hold down Control and just hold it down and hit the C key twice quickly in rapid succession. It'll be Command on a Mac and CC, and there you see shutting down. The kernel has been interrupted. It's shutting down. It is finished. So to start up again, we just have to type Jupyter Notebook all over again. In this video, I want to introduce you to Google's version of the Jupyter Notebook called Google Colaboratory. So if you have a Google account, you can log into your Google Drive. You can create folders. As per normal, you can click on New and create Google Docs and Google Sheets, etc. There's create a new folder. So I've created a whole folder structure here, and I want to show you how to use the Colaboratory notebook. So I'm going to say New, come down to More, and then Colaboratory. That's going to open a new tab in my browser here, and we see what looks like a slightly modified Jupyter Notebook, and that's exactly what it is. So you don't have to install Jupyter or Python on your local machine. With the limits that do exist here, you can use Python in the Jupyter Notebook right here in the cloud. So first of all, let's just rename this. So I can just click and highlight there, and let's call it test. I'm going to click away from that, so we see our notebook is now named test, and we can start working. Now you see these cells look a little bit different. Instead of a run button up here, we have the run button right there. And if we hover below here, we see we can add new code cell or a new text cell. Let's add some code though. One thing is you have to upload the files that you are working with to the cloud for you to be able to use this. So if we use pandas to import a spreadsheet file, we have to upload it first. And the way that we're going to do that is to say from google.colab, we're going to say import files. And I'm going to hold down Shift and Enter, or Shift and Return. That'll do the new cell for me. Or if I just clicked on play, that cell would have executed and I would have had to go to new code cell here. So there we go. So let's import a file. And the way that we can go about that is to give it a name. I'm going to call it data file for reasons of simplicity. And we're going to call files.upload, open and close parentheses. Once I execute this, I'm going to hit the play button there. My folder structure, my hard drive is going to open up and I can choose the file to upload. So there we go. And we see choose file. So let me use choose file, and let's scroll down. And I get to the file that I want to upload. Click it and hit open, and you see the upload starts. It's 100% there, and there it says raw data underscore CSV. That is the file. It says there to this file. That is the name I can now use. It is now up in the cloud. So let me move down. I'm going to add a new code cell. So here let's say import pandas as PD. Shift enter, it's there. Let's create a data frame, and we're going to say pd.read underscore CSV, and I can hit tab, scroll down to CSV, that's for auto completion, and now I've got to use this name that was given to it right here. So I can copy, let's copy and paste that right in there, and let's run this cell, and there we go. Let's add a new code cell below, and let's look at df.head, open and close. There we go, it is uploaded. So you have to import this files here, and every time you want to import a file, you've got to give it a name, a computer variable name. We're not going to use that though. We call files.upload, and then we click on choose files, and then go onto our hard drive and find that file that we do want to use. If you want to use Plotly, so if you look at the section on data visualization, where we draw plots and graphs of our data, if you want to use Plotly, there is one thing you have to do, and I'm just going to copy and paste the text here. So let me increase the size so that you can see properly. There we go. This is the code I want you just to copy and paste and keep at hand. If we're going to use Plotly, this is a little function that we have to call every time we want to use Plotly. So you've got to watch the section on how to use visualization, and then this will make sense. And then every time you run a piece of code that is in Plotly that is going to draw a graph or a chart for you, you have to run this bit of code. Let me show you. Let's add a new code cell. There we go. So within the cell, I can now start adding my plotting code, and you can, as I said, you can view that in the section on plotting your data. So that calls this function, configure underscore plotly underscore browser state. It calls that and allows us to plot right here inside of Plotly, inside of the notebook using Plotly. If we use the notebook, a Jupyter notebook on our hard drive, we don't have to do these two steps every time we want to plot something. But when you do go to plotting and you are using this environment, please have these two cells at hand. In the last section where we actually go through full demonstrations of research projects, I use the co-laboratory there with lots of plotting so you can see how to implement this. Please refer back to this video though, just to remind yourself how to use this in the co-laboratory. So in short, that is the Google Co-Laboratory. It is a fantastic environment. You don't have to install anything on your hard drive. You can simply use Jupyter Notebooks within limits right here inside of your Google Drive. It is saved automatically every couple of seconds, so you needn't worry about that. And you can share this with others, and you or they can also just add little comments. And that is beautiful. If you're collaborating with someone, you're helping them with their data analysis, you can share this file with them, and instead of them understanding the code, they can just leave normal comments to ask you about that. Or you can leave comments for yourself just as any other Google document. So let's close this. And we see test.ipynb is now on this hard drive. If I double click on that, this page opens and it says no previews available. It suggests that you open it with Co-Laboratory. We can just click on that Co-Laboratory, and there we go. The file is there. Remember, if you've logged off and logged back on, you'll have to go through the step of uploading this data file again, or any other file that you are using, before you start using any of the data that's in there. Now, whether you use Jupyter Notebook on your local system or you use Google's Co-Laboratory, I want to just show you a file that we're going to look at right at the end of the course, where we start going through a whole complete project. And this is what it looks like in the end. I just want to scroll down and down some more, and down and down and down. There we go. All this beautiful text. You can see the graphics there. But look at the structure of this document. I have the logo of our research group here. I have nice text up here. I have smaller text there explaining what I'm doing, so that's a subheading. We have the data that is imported there. I can write the research questions here. So we were going to do descriptive statistics. Then we're going to ask, is the presence of skin and soft tissue infection independent from the surgical approach? Is the presence of skin and soft tissue infection independent from gender? And we can then start with the descriptive statistics, etc. So it's such a beautiful environment to code in. As I said, either in a Jupyter Notebook on your local system or here in the Google Co-Laboratory. So Jupyter Notebook or Google Co-Laboratory Notebook, whichever one you want to use. But look how easy this is. And when I double click on the cell, it opens up for me to edit. And there's the markdown. It's very easy to pick up markdown. Just start typing. That'll just be a normal paragraph, or put these hashtags. You can put one hashtag up to 6 hashtags, as long as you always put a little space there. And that will give you heading size 1, which is very big, to 6, which is very small. And here you can see, well, it's just 1 dot space start, 2 dot space start. And when we execute the cell by hitting Shift Enter, Shift Return, it makes a nice little list for me there. There's so many ways that you can go about it by just 2 different types of cells. Remember, this is a code cell where I write normal code in, and this is a text cell. And you can open a text cell or a code cell inside of a Jupyter Notebook on your local system, and here in the Google Co-Laboratory, here you would just hover at the bottom in the middle, and the next cell could be a code cell or a text cell. Let's put in a text cell. And while I'm in the cell, remember, I can move the cell down. If I put it in too soon or back up, I can just move it wherever I want. And to delete it, I'm just going to hit those little ellipses and say delete cell. So with a code cell and with a text cell, you can do so much. You can create these beautiful documents that you can share. And that is what reproducible research is all about. Everyone can see how you went about doing your analysis. It's open for everyone to see Well, those with whom you share it, of course. Your collaborators can see how you did your analysis, and when you do the analysis and try to present it to someone else, it's so easy to use these documents for your presentation. You can very quickly change something, change the code, execute that cell, it'll update the results for you, and you can have these sections of words in which explain to people what it is you were doing there. And these beautiful plots that are rendered here, look at this, we can save the plots as a PNG file on our drive. If we work in Microsoft Word, for instance, we could just then put this graphic inside of the Word file. If we're creating or preparing a manuscript for submission, we can even open it on Plotly, on Plotly's website. There's a whole section just dedicated to creating these wonderful plots. And look at them, they're interactive. As I scroll over them, we can see the values here of the median and the first and second quartiles, the first and third quartiles there. So beautiful environment this. And remember, this is just inside of a browser. Your Jupyter Notebook will open inside of your default browser, and here in the Colaboratory, of course, in Google Drive, I'm using Google Chrome. So I hope this gets you exciting, and I hope it gets you thinking about all the wonderful documents that you'll be able to create at the end of this course. I've started the Jupyter Notebook and my default browser has opened, and I've navigated to this folder on my desktop called Biostatistics Fundamentals using Python. So that's a normal address, the same as you would find in a Finder or Explorer, depending on the operating system that you use. Just an address to a folder. I'm going to go to New, and I'm going to say Python 3. You can see I have all these other languages as well. So Python 3, a new notebook is going to open up, and the first thing I want to do is just to name this. So I'm going to click on Untitled there and call it the Fancy Calculator. There we go. I'm going to click Rename, and there we go, the Fancy Calculator. Should I go back to this first tab, I see the Fancy Calculator.ipynb IPython notebook is now a file inside of this folder, Biostatistics Fundamentals using Python, on my desktop. Great. We're going to start doing some simple arithmetic. Statistical analysis is all about mathematics, and at the heart of most computer languages is a powerful calculator. So what if I just want to know what 2 plus 2 is? So let's just do some addition. 2 space plus space 2. Now you don't need to put the spaces there. I put them there for readability, but of course it wastes a bit of time and it's a bit of effort putting the spaces in between. You needn't have, you don't have to, but I like putting them there. I'm going to hold down Shift and Enter, or Shift and Return. Lo and behold, it's 4. But you can see it's the same as we would have written it on a piece of paper. 2 plus 2 is 4. I can put more of those together, 2 plus 2 plus 3, for instance, and I'm going to get 7. Simple arithmetic. What about the subtraction? 2 minus 3. It's minus 1. Powerful, powerful stuff. Now remember, negative, that's the same as adding, or subtraction is the same as adding a negative number. So if I put that minus 3 inside of parentheses, that means that's negative 3, the number negative 3, and please add that to 2, and we're going to get exactly the same thing, minus 1. So what about multiplication? Well, there's no multiplication sign on your keyboard, but there is a star. Most keyboards that will be Shift and 8. So let's do 2 times 4. 2 times 4, so that's the little star, Shift and 8. I'm going to hold down Shift and hit Enter or Return, and 2 times 4 is 8. There's nothing difficult there. And I can string these together as well. 2 times 4 times another 3, and that gives me 24. I can just add on, add more and more integer values or any kind of numbers to that. What about division? Also no division symbol on your keyboard, but that's just simply the forward slash. So if I were to say 4 divided by 2, so that's 4 forward slash 2. It looks like it's 4 on top of a 2, sort of like a fraction. 4 divided by 2, Shift Enter, Shift Return, and I see 2.0. Now that's different from what you've seen before. There were no decimal places there. Division is going to give you this 2.0, because if I were to say 3 divided by 2, let's have a look at that. That's going to be 1.5 decimal value again. let's do 10 divided by 3 because we know that might be problematic. And it's going to give me this numerical approximation. And see, it looks a bit weird there. You would expect that to be just, a bunch of threes and never stop. But that's just a bit of fancy rounding happening behind the scenes. Don't be concerned about that. We're obviously not going to deal with decimal places to this extent in normal biostatistics. What about powers? I want to raise 2 to the power 4, and that's going to give me 16. And most languages will have the caret sign symbol there, that's shift and 6, but not in Python. It'll be 2 stars. So 2 to the power 4, that's the star shift 8 twice, and 2 to the power 4 gives me 16. Now, what about just rounding things off a bit? That might be a bit difficult to do. So we're going to introduce one of my favorite packages, and it's called NumPy, Numerical Python. I want to introduce this as soon as possible. There is the base Python language. Can do a lot of powerful things, but clever people have gone and they've extended the language, brought extra functionality to this language, and they bundle that in a package or a library, and all you have to do is to import that library, and that just expands the ability of Python no end. And one of the most powerful things that we are going to use in biostatistics is the numerical Python package, NumPy for short. And the way that we bring this extra functionality that lives inside of a package or a library into Python is just simply by importing it. And we have this command called import. And I'm going to import this package called NumPy. It's just what it's called. It's what it's bundled as this name NumPy, which stands for numerical Python. But I've got to let Python know if I want to use something inside of that package. So I've got to first refer to the package and then what is inside of that package. Now look here, we've referred to the powers by putting in 2 star symbols there. That was inside of Python. I didn't have to tell Python, look inside of Python to find these. They are just inside of Python. But these extra libraries, whatever's inside of there, if there's a power there as well, I have got to tell Python, no, look, first go to this library that you've imported and then find something. And that means I have to type NumPy every time. So I would have to put NumPy and then this functionality inside of NumPy. And that can get tedious. There are a group of people who think that you should just do that. But most people just put in an abbreviation. So Python has this as NP. So instead of typing in NumPy every time I want to use something inside of NumPy, I can just use NP. And you'll see what this is all about in a few seconds. I'm going to hit Shift and Enter. Now NumPy is imported, and it's imported as this abbreviation NP. So let's just do 32 divided by 6. Let's do that. We see it's 5 1/3. There we go. But what if we just wanted to round that off? Now there is a beautiful function inside of NumPy. It's called round. So I'm just going to call it, but now I have to say, look, go find this round. Round is just something that Python can now do, such as addition or subtraction or whatever. It's just round, but I've got to say numpy.round. And there's this dot notation. You've got to get used to this dot notation. We're going to see it a lot. So it says go inside of this new library that I've imported, NumPy, dot. Now go find something in there, and the function I want you to find, this command I want you to find is the round. And I'm going to put parentheses. So we have a function, and we have to pass some information to this function so this function round can know what to do. And these things that we pass, this information that we pass to round, they are called arguments. And these arguments always go inside of these parentheses. So now I'm going to say 32 divided by 6. So that's an argument. It's just an expression, this argument. It says take 32, divide by 6. And I'm passing it as information to the round function. And if I just leave it as such, it's just going to round this off. And it's rounding 5.333. It's rounding that down to 5.0. So there you go. It really is, it's fantastic, this ability just to extend Python. And there are so many packages out there, and beautiful statistical packages. And that's what we're going to use. So now you already know, what the basics of this, what it's all about. So there's another function called floor. So I'm just going to say numpy.floor, And let's just put in 32 divided by 6 again. And that all that's going to also do is just to round down. Floor means round down. And it follows the convention of if it's 0.5, the decimal is going to round up, and if it's less than 0.5, it's going to round down. But I can force this rounding up, irrespective of where the decimal lies, by this function np.ceil for ceiling. So if I now put in 32 divided by 6, it's going to, let's just do that properly, 32 divided by 6, it's going to round up, irrespective of what that decimal is. Just rounded up to the nearest integer. So that's beautiful. You've seen what the basics are of this importing a function, a package, a library, and using some of the functions built into that, which is not inside of the base of Python. Now, one thing that's very important that I just want to put in here in this introduction using Python as a calculator is just the order of execution. So if I were to say 2 plus 4 divided by 3, and I were to hit enter, so we know the order of execution from mathematics at school. The division is going to come before the addition. So it's going to take 4 divided by 3 first, which is 1 1/3. It's going to add 2 to that, that's 2 1/3. But you can force the order of execution, just as you did at school, by putting it inside of parentheses. So that's 2 plus 4, that's going to happen first. And now I'm going to divide by 3, so that's 6 divided by 3, which is 2, which is just very simply 2. So let's put some of this into good practice. Let's calculate the mean, the average of a couple of values. So my values were 2 and 3.3 and 4.3 and 4 and 9. And I'm just going to add all of those and divide by how many there were. There's 1, 2, 3, 4, 5 values there. So divide by 5. Have a look at that. You've just calculated the mean or the average. And just as you would with a normal calculator, or at least a scientific calculator that has some parentheses, it really is as simple as that. Of course, this is Python, and we've imported numerical Python. So I just want to, just have this little sneak peek for you quickly. There's a mean function inside of NumPy. And all I have to do when I want to do this is just pass all of these values as an argument. But there's a little trick. And this is just a sneak peek, so don't worry about it now. We are going to look at these things. They're called collections. And this specific collection is called a NumPy list. And a NumPy list always goes inside of, they always go inside of these square brackets. And we separate all of them by commas. So there was a 2, there was a 3.3, there was a 4.3, there was a 4, and there was a 9. And if I hold down shift and enter, shift and return, I get exactly the same value, 4.52. So a beautiful function there called the mean inside of numerical Python. Now this mean function is inside of a lot of other libraries, more simple libraries like the math library. Don't worry about that now. It's NumPy we're using. It's the base of all those statistical functions that we're going to use. There's a mean function in there, and I just pass all the values that I want to create the mean of. Now later we're going to see even easier ways of getting to do this without having to type all these values, because we're going to hope that our data exists inside of a spreadsheet file, and we're just going to import that spreadsheet file. We're just going to reference all those numbers, and we're going to calculate the mean. But you can see here behind the scenes how it's done. It's simple arithmetic. We're going to add all these values and divide it by how many there are. That brings me to just a quick note on the different types of data inside of a programming language like Python. And I can ask Python to tell me what type of values or what the data type is being stored. So if I just write type and I put my parentheses and I say, what is the type of the value 1? What type is it? What type? And that's very important in a computer language. Now we're going to talk about statistical data types. As a variable, categorical, numerical. We're going to get into all of that. But I just want to just show you that there are different computer data types as well. So I'm going to hit down shift and hit enter, and I see int for integer. So 1 is an integer. But if I were to type something like 1.0, exactly the same thing, shift and enter, I see this is a floating point value. Float means decimal point. It is a decimal point value. Let me show you a couple of other things. If I were to put something inside of quotation marks, and I were to put the value 1, that's inside of quotation mark, Shift and enter, and it tells me that is not a numerical value anymore. Anything that goes inside of quotation marks is a string. A string just means a letter, a word, a sentence, a paragraph. And that number 1, which inside of quotation marks, is now part of a sentence. And sentences in computer languages are usually referred to as strings. So if it's just a simple single character, a single number, a word, a sentence, a paragraph, doesn't matter if it goes inside of quotation marks, it is a string. So please remember that. So there's your introduction, a fancy calculator. And we've actually gotten a little bit beyond that. I've shown you some very fundamentally important things here. How a computer language is structured, how Python is structured, how you bring something into Python. And this really, if you just get this first tutorial, you will have no problems whatsoever learning Python and doing your statistical analysis. In this section of the course, we're going to look at collections. You've got data and you store them inside of little containers. And you give those containers a name so that you can refer to them again when you do your analysis. Let's have a look. I've opened Jupyter Notebook, and here I am in my default browser. I've navigated to the Biostatistics Fundamentals using Python folder on my desktop. I'm going to click New, and I'm going to click Python 3. There we go. I'm going to click on Untitled to give this a name, and the name of this is Collections. Collections, there we go. Let's start talking about collections. Collections are just groups or sets of elements. Take your cupboard at home. It's a cupboard and it has all sorts of foodstuffs in it. There's some canned goods, there's some salt, there's some pepper. Collections inside of some container, which is your cupboard. Oh, I don't know if that's such a wonderful example, but the same thing happens here. There are ways to collect some elements inside of Python. It's really useful because if we want to do statistical analysis on a set of values, we need to put those values inside of a list. Inside of some sort of collection, we're going to start off with lists. We've seen this before actually. Lists go inside of square brackets. I've hit my open square bracket. There's this immediate automatic addition of the closed one. Jupyter Notebook does that for you. Very nice. And I'm going to say 1, 2, 3, 4, 5. Simple as that. Shift enter, shift return, and we see a list is returned. I'm going to say type. And then again, 1, 2, 3, 4, 5. Doesn't matter what numbers I put in there, but the type is a list. So irrespective of what goes inside of that list, the square bracket still means it's a list. And I can put other things in that list because have a look at this. I can say, we can put in, let's put in group, so group A, and we have a group B. Let's put that in quickly, group B, and we might have a control group. There we go. There we go. And if I hit shift enter, that is a group and it contains just these 3 elements, and those elements are, remember what they are? They are strings. But the type of this whole thing is still a list. Now, note one little important little thing here. You'd see I put double quotes here. The result was single quotes. In Python, you can use either of those 2, and you can actually use them judiciously because let's do that. I'm going to copy all of those. So I've just highlighted that whole, and I'm going to hold down Control and C or Command and C, click at the end, click in the new cell, Control V or Command V, and I've copied that. But what if I wanted to just put some single quotation marks around something? So I'm going to just highlight group, and I'm going to just hit the single quotation mark, so they'll put a single quotation mark in the beginning of the end. So now you see I'm mixing double and single quotation marks. Shift enter, shift return, and now let's put those quotation marks that I asked for here inside of. So it just helps you if you want to put quotation marks inside of something, make use of both the double and the single quotes, and you can reverse them actually. You could have had all single quotes and then a double quote. I digress. This is all about lists. But there's a beauty about Python. As you play with it, you discover these new things and you go off on a tangent. It's just this beautiful, just this big area of exploration. You can run wild and just enjoy yourself. Fantastic. Now, you might have thought to yourself, well, there's one problem. I don't want to type in those numbers every time. Imagine I have a 1,000 numbers I have to type in. Do I have to do that every time? First I want to do the mean, then I want to do standard deviation. No, don't worry about it. There's something called a computer variable. Now, a computer variable is the space that you create inside of the computer's memory to hold something. And what it holds in a computer language we usually refer to as an object. So let's create something, and I'm going to, you've got to give it a name. So I'm going to call this list_1. Now, within reason, choose whatever you want. Make it descriptive, so if you have to refer back to it to remember what it was about. So I'm going to call this list1. It's the convention to use what is called snake case. I think most people refer to it as snake case. And snake case means I just build up this name by putting these underscores in between the elements that make up this naming convention. So try to start that with a lowercase. Always keep everything lowercase when you create these computer variables, and don't use illegal characters like starting with a number or using words that are built in commands or functions inside of Python. Just keep it reasonable. It really is not that difficult to grasp the concept. Use something descriptive. I've called it list_1 space equals. So I'm going to put something inside of that, and what I'm going to put in there is again my 5 numbers, and I'm shift enter shift return. So what have I done? I've created a space in memory to hold an object. The object that it holds is a list, because I've passed a list to it, and I've given that space in the computer's memory a name. It's called list_1, so the computer knows, Python knows where to go inside of your computer's memory to retrieve this. Because if I were to say list1 and shift enter shift return, it returns that object which was inside of that piece of memory back to me. And that makes a computer language so useful, the ability to store things inside of computer variables. Now let's just have a look at a few interesting things about a list. Number one is it's quite easy for me to extract how many elements there are in that list. So I can just use what is called the len, short for length. So what is the length of list_1? Shift enter shift return, and we see it's 5. There are 5 elements inside of that. So let's go off at a tangent again. I'm going to import numpy. Import numpy as np. There we go. And the beauty of Python, just start exploring. Once you know a little bit, you can really figure out how something is going to work even though you've never seen it before. So let's try another way of just calculating the average of 1, 2, 3, 4, 5. So I want to sum up all those values in that list. You can guess it's going to be np.sum. There's a sum function inside of numpy, and I'm going to pass as argument to it list1. List_1 is what I called it, and I'm going to divide it by how many elements there are. So I'm going to say length of list_1. And what do I get? An average of 3. So it's summed all of those. 5 plus 4 is 9, plus 3 is 12, 13, 14, 15. 15 divided by 5 is 3. The average of 1, 2, 3, 4, and 5 is 3. And we just did this in a new way. We just figured out, well, I've just learned about the length. It tells me how many elements there are. What comes to mind? Oh, well, let's do the average of all of these values. So that's really powerful, just to put something inside of a list. Next thing inside of a list I really want to show you is just the address of the elements inside of a list. Yes, every element in there has an address. And it's very important for you to know this fundamental fact. Python starts counting at the number 0. So if we look at this list 1, there's 1, 2, 3, 4, 5 elements in there. The first element has an address of 0. The second one has an address of 1, 2, 3, 4. That's how it works in Python. And how do I get to that? Very simple. I'm going to say list_1, and if I want to address one of the values there, I put square brackets and then put the address that I want inside of there. So I want the first element, which is in Python terms, it's the 0th element in there, and that's 1. So if we say list_1 and I want the second one, what is that going to be? Well, that's going to be 3, because second is actually the third one, with 0, 1, 2, which makes it the third one. Just a little hint. I want to show you something special. List underscore 1. If you didn't know how many there were, you can just use the shortcut -1. -1 refers to, well, start at the back end and give me the last one, please. So we know there was this 5, but if you had, if you had 3,435 and you didn't know, how many there were, of course you can. You can put the length in LEN and put it in. You would know. But there's this -1 just to help you out. Let me show you something special, something more special. What if I want the values from the second value, which would be 1, but I want 2, 3, and 4. So 2, 3, and 4. So I'm going to say, put 1 in, which is the 0th one. Well, let's just do something. 1, 2, 3. And you see that colon that we put in there. So it says from 1 to 3, which actually means 2 to 4, 2, 3, and 4. But look at that, 2, 3, and 4, if you think about it, those are 3 values, but we only got 2 back. We only got 2 and 3. Another little subtlety in Python that you've got to get used to. Usually Python doesn't count the last value that you put in. It says up to, but not including 3. So 1, 2, and 3, which means positions 2, 3, and 4, actually, because remember we start counting at 0, but it's only going to actually be 2 and 3 that we're going to put in. We don't get to the 3. Just get used to it. It's just the way that Python works. When I show you something else, how do you add a value to a list that already exists? So let's just look at list 1 again. We see it's 1, 2, 3, 4, 5. What if I wanted to add the value 6 to that? I'm going to say list underscore 1 and something brand new. You've never seen this before. I can put a dot behind it because this is now a Python object called a list, and a list has certain properties to it. And one of the properties that a list has, it has the ability to be added to. And to be added to is called appending. So I'm saying dot append. So because list 1 is a list object, it has certain properties. One of the properties is the ability to append or to add elements to it. And I'm just going to say, please append the value 6 for me as well. And if I were to do list 1 now, let's have a look what happens. We have 1, 2, 3, 4, 5, 6. So it appended that 6 to the end. So there's another way for a list to be appended to. So let's just do list 1. And I want to add to that the number 7. I can't just say plus 7. I've got to put that 7 inside of a list as well. So if I shift and enter, shift and return, now we've added the 7. So you've got this append property, this method that exists that you can do to a list using the dot append notation. Or you can add it, but you've got to put that inside of square brackets. So you can add this to it. One difference from the append though, if I do list underscore 1, the 7 is gone. That was not permanent. The append function here, this append method here, that is really permanent, but adding it like this is not. So just little subtleties that you can get used to. Now, don't be overwhelmed now. Don't try and remember all of these. This is just exploring. It's like being young again and just playing in the sandbox. We're just enjoying ourselves here. So don't worry too much about all the things that are happening here. Don't try and say, oh, this is not overwhelming. We're just playing around. As we start using these things, these fundamentals will come back to you. We're going to use them over and over again, and this will really become second nature. So how do I remove something? How can I remove one of the elements? Well, we're going to use the dot remove method. So I'm going to say list. Let's just do list underscore 1, and I want to remove something. And let's just remove 5. Let's just see what happens. List underscore 1, and now we have that element 5 having been removed. So I've asked it to remove that element number 5. And we saw that this is permanent because I put list 1 there and it is permanent. That is gone. I think we should stop here. That is just I think perhaps an overwhelming little tutorial here on lists. Look through it again, play with it, start exploring it, do other things, try multiplication, see what happens there. Some interesting things are going to happen when you try that. Explore. You have the fundamentals. You can guess at what can be done. Open a notebook. Play with lists. Next up, we're going to have a look at something slightly different called a range. So we're carrying on our talk about collections, and the next one I want to show you just as a range. The first part of it's going to look slightly weird. I'm going to use the range function that's built inside of Python. I'm going to say range 10. And it just returns this object to me, which is just range 0, 10. That is the object that it is returning. And it can become useful. We cannot use it a lot, but I think it's important that you just know about it. So I can also say, well, range start at 0, end at 21, and go up in steps of 2. So I can do a start, a stop, and a step. If I just put 1, Python is going to use the default, and it says start at 0 and end at 10. So if I put only one value in like we did there, it means end. But I can put all 3 in, and the 3 are start, stop, and step. So I'm going to start at 0, jump by 2, that's 2, jump by another 2, that's 4, and so on. And it's going to get to 20, and then it can't go any further because it'll be 22, and I told it to stop at 21. As I say, we're not going to use this a lot, but I just want to show you where it might become useful. It is something in base Python. There's some built-in functions in NumPy, etc., that I'm going to show you in a moment. So we're not really going to use this, but as part of the fundamentals, I want to show you. I'm going to put something inside of square brackets, meaning it's going to end up being a list. And I'm just going to build this little English sentence. I'm going to say I squared for I in range 5. It's almost like an English sentence. Look at this. So I've got this mathematical variable almost called I, and I'm going to square it. So if I was 2, I squared 2 is 4. If it was 5, I squared it's 25. And I'm saying for every I in the range of 5, and if I say range 5, it's going to be 0, 1, 2, 3, 4. Remember, it always excludes this last one. And it's just going to square each of those. Have a look at this. Just as you thought the answer would be. Number 1, it's an object called a list, still inside of a list. And it's just taken all the values from 0 to 5, excluding the 5, as it always does, and it squares all of them. It's just a little English sentence there. It just makes sense. One of the other beauties of Python. So it says I squared for I in range 0 to 5. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So that might just be one way of doing this. We're not going to do this a lot, as I say. So something else I might show you that's slightly more appropriate, again, is to use a NumPy, special NumPy function called arange. So instead of range, it's arange. And if I were to put in 5 now, it is actually going to return something called not a list, but an array. Think of it as a special kind of list. Don't overthink it. It's just a special kind of list called an array. And once again, you see it did not get to the 5, so it says give me 5 elements, yes, but remember it starts counting at 0, so I'm going to get 0, 1, 2, 3, 4. So I get back this very special little list. Now again, I just put in a single value there, but I can do this whole thing. I can do this start, stop, and step function. So I say start at 0, stop at 21, and go in steps of 2. Again, it's going to omit that 21. It can't do because the next one's 22 anyway, so it doesn't really matter here. But 0, 2, 4, 6, 8, 10 until 20. So start, stop, step. So if you quickly have to create these for whatever reason, remember this arange function. It has a little cousin called line space, which we write linspace for. So it says the following. It says start and stop, and how many of them do I want you to create between these two extremes. So if I were to tell it, start at the number 1, go to the number 10, and whatever that is, divide it up equally so that I end up with 5 values. So I have 1, 2, 3, 4, 5 values. I started at 1, I ended at 10, and what NumPy did here is it divided it up into 5 equal bits. So it's a cousin of arange, and that might also become useful at times, just to have this range of values with a minimum and a maximum value, and I want to chop it up into equal bits, and I want so many equal elements. Please give that back to me. So remember arange and remember linspace. You might see it come up here and there. So it's just another one of these little fundamentals that I want you just to be aware of. Don't try and memorize it. You've seen it now. You know that it exists. Play around with it. See the different values that you can get. It's really fun, actually, to create all these sequences and numbers inside of these little lists, or a very special NumPy lists called arrays. And it's a lot of fun. Play with it. Knock yourselves out. Don't worry about memorizing it. We're not going to use it in exactly this form because we're going to use stuff that's already built in, that it's just going to do all the work for us. But I want you to be aware of it, play with it. It's part of the base knowledge. It's good to have to know about this, and perhaps something that you can refer back to in future. In the next tutorial, I'm going to talk to you about the last special form of a list, and that's called a dictionary, and that is super important because we are most definitely going to use dictionaries. So as promised, the all-important dictionary. We are going to make use of dictionaries, specifically when we're going to start visualizing data. So time to pay attention. So a dictionary is slightly different from a list. Whereas the lists just have these values, the elements are just values, and they each have an address. In dictionaries, they still have an address, but that address is called a key, and that key is just a name. So we're going to have a value, and that value is going to have a name or a key. Let me show you. I'm going to call this dict, short for dictionary, _1, so that I can create this space in memory to hold an object, and the object that I want to hold is a dictionary. And a dictionary doesn't go inside of square brackets, it goes inside of curly braces. And it always has a key name pair. So the key that I want to do here, I'm going to say pneumonia, if I can spell pneumonia, and then a colon, and then a value. Now in this instance, the value is 10, which is an integer, but it can also be a string, it can also be a floating point value. Remember, those are decimals. Can be anything. It can actually, just keep this quiet for now, you'll see it later, it can actually be another dictionary. The value can actually be a dictionary all on its own. Don't worry about it, don't worry about it. So I have a key called pneumonia, and I have a value 10. So the value is actually what makes up this special kind of list called a dictionary. And instead of it having an address, it actually has an address of 0, 1, 2, 3, 4. It actually has a key, which is a name. So let's do another one. So comma, always separate these elements with commas. So let's call the second one hypertension, and remember, see, it goes inside of quotation marks. It's a name, it's a string. Strictly speaking, doesn't have to be a string, but for now let's keep it a string, and I'm going to say there were 5 of those, and let's make the last one diabetes, and my diabetes has, let's make that 4. So I have this key value pairs, and they are separated by colons. The key and the value, they are separated by colons, and I'm going to hit shift enter, shift return, and if I were to say the type of dict _1, it's going to tell me it's a dict, short for a dictionary. Now, as I said, these are pairs of values. So I'm going to say dict _1. Now, remember, dict _1 is a Python object, and I told you an object has certain properties, and in this instance there are a few properties. One of them would be items. So if I were to say items, open, close parentheses, that is just the usual way that we don't just say dot items and leave the items, although there are some that you do. Most of the time you will just put this open and close parentheses, just meaning that there is this property inside of it, and I want to call this property, and that's just a convention. Just get used to it. And now it says, well, the dict items are pneumonia with a 10, hypertension with a 5, and diabetes with a 4. They're inside of these parentheses, just to show you that there are these 3 elements, these key value elements. So you can actually just ask Python, well, what were the keys inside of this dict1? So I'm just going to say dot keys. And now it tells me the dictionary keys were pneumonia, hypertension, and diabetes. What about the actual values? So dict _1 dot values. Simple as that. That wasn't too difficult. I bet you could have guessed that. And it says the values are 10, 5, and 4. So it's this key value pair, and it really makes it very powerful to use, and we are going to use it. Now, remember how we did addressing? I put the address of the element inside of a square bracket. Exactly the same thing here, but instead of now saying, give me the 0th one, I'm going to say, give me, the value that was held in the key hypertension. This gives me this other hypertension. Hypertension just gives me this other way of referencing. And you'll actually see later that makes dictionaries actually a lot more powerful. And it tells me, well, the value 5 was held inside of this key hypertension. So very, very, very powerful. Now, just as we could append to a list, we can do the same here. It's not called append though, it's slightly different. It's called update. So let's do dict1. So dict1 dot update. I'm going to update my dictionary, and I'm going to update it with a key value pair. It is a dictionary. I've got to put it inside of curly braces, and let's put in bronchitis, for instance, bronchitis, and let's make bronchitis 6. There we go. We've updated dict1. If I now call dict1, we're going to say we have bronchitis is now there as well. I can remove things as well. I think it's important for us just to have a quick look at as the last thing that we look at here inside of collections. I think then you know the fundamentals of collections, and you are well equipped to carry on with biostatistics using Python from here. But this last one, it's called pop. If I want to remove something, I'm going to say pop, remove that for me, and I want to remove hypertension, please. So I'm going to say pop, and let's put in hypertension, spell it the same way as you did before, hypertension, there we go. And if I say that, it says 5 there. So let's just have a look at what happened to dict number 1. Hypertension is gone. So it actually tells me the value that it did hold, in case I wanted to know, but it is now gone. And if I call dict 1 again, the hypertension's gone. If I wanted to add to it, remember, just update and put another dictionary in there. So there we go, lists, ranges, and dictionaries. The lists are very important. Most definitely these dictionaries are important. Play around with them. Before you go, and this is so much fun, let's just do this. I'm going to say dict1, let's make it dict2, and it's going to be a dictionary. Let me just show you this. Let's have one that has diabetes in it. Diabetes. I told you it's possible, but let me just show you it's possible. So that's the key, and the value can be another dictionary, and that dictionary holds key value pairs. So that might be insulin, depend, let's just put IDDM, and we're going to make that 10, and we're going to have another one in IDDM, that's easier, and 12. So it's a key value pair still, but the value is another dictionary. And just to be blatant about this, let me put in another one, hypertension. And if I put in hypertension and we make that one, say 12 again, I have this dict2 now again. Let's have a look at dict2. It's going to show me there's diabetes, and it actually holds a dictionary as a value. So if I were to say dict2 and I want to get the values back, look what's going to happen. It's one of the values is actually a whole dictionary. It is actually a whole dictionary. So you can put dictionaries inside of dictionaries inside of dictionaries. Might look a bit funny now, but believe me, it's very powerful. I think I have got to stop here, otherwise this tutorial would never end. So lists, ranges, and dictionaries, play with these, get familiar with them. No need to memorize. We're going to use them in specific manners. I mean, we're going to solve problems here. We're going to do biostatistics. And as you do it yourself, these things will become second nature. For now, just be aware of them and play with them. In this section, we're going to look at how to import data. And I'm going to assume that your data lives inside of a spreadsheet. It's very common to have Microsoft Excel or other spreadsheets. It's also very important to look at those spreadsheets and make sure that your data is proper, that every row is one subject in your research and every column is one specific variable. Now, we're going to have a look at how to import that inside of our software so that we can have it ready for our data analysis. I really believe that you have enough fundamentals now, fundamentals of Python, and we can really get going. We're going to work with data. So in creating the lists and the dictionaries, we typed it all in by hand. That's not the way real life works. In real life, we have a data set. We've collected the data inside of a database, inside of a spreadsheet. Someone has collected it. We're going to import it and we're going to use it. Here we have a very simple example. It is a spreadsheet. And in this fundamentals course, we're just going to work with spreadsheets. So it's a flat file. In other words, it just has rows and columns. And this is the way I want you to see it. Every row is a subject in our study. So this very first one here, all of these variables, these data point values for each of the variables belong to one subject in our study, the second one, the third one, etc. The columns make up the different variables. And in the first row, we're actually going to have those variable names. So we're going to have age, there's some sort of a grade, there's a logistics variable, there's a temperature variable, there's a pneumonia variable, a hypertension variable, and then lastly this diabetes mellitus variable. Note something very special about this. There's no space in between the S and the M. When you get in a data set like this, a flat file like this, like a spreadsheet, this is a Microsoft Excel spreadsheet, do yourself the favor, change it now. You can change it inside of Python, but for me, Python is like this sterile field. I'm a surgeon, what am I going to do? I want to bring in the sterile field before I start operating on it. So I actually just like to fix things up as much as possible, and the best way to do that is design this tool, this data sheet, the spreadsheet file, before data is ever collected. Design it then and do it right from the get-go. But if you get it in and it's not, try and fix things here in Excel. I like to bring it in a sterile and beautifully clean fashion before I start operating on it. And that means analyzing the data, playing with the data, seeing what the story that the data is going to tell me. I like to do that. You can do all of that inside of Python. You can do all of this cleaning up. But this is the fundamentals course. We have this beautiful data set. You see there's no missing values and everything is pristine. Back to where I was. There's no space in between the S and the M. Do this. Don't put any spaces. If you really want two words, do the snake case. In other words, put the underscore in between things. It will really help you along the line. There's some shortcuts that just makes this much easier. If you just have properly formatted computer, or I should say statistical variables names here, and those go on top of the column. So please remember that. You'll also note that everything below that is these data point values. I'm going to call each of these things a data point value of the variable, and they are all of the same statistical type. So we know that we see age here, and we see that it is a numerical variable. So all these data points are numerical variables. We see grade is A and B, so that will be some form of a categorical variable, and I'm going to call it nominal because we don't know that there's a natural order to this. I'm going to call this a nominal categorical variable. Logistics here, that seems to be a nominal categorical variable as well. We look at temperature, the data point values for the variable temperature. These seem to be numerical variables. Pneumonia, it has yes or no. It's nominal categorical. Hypertension is nominal categorical. Diabetes, nominal categorical. If you don't know what any of these are, please look it up. Look at my other course on Coursera on the basics of statistics, really the fundamentals of understanding healthcare statistics. I'll give you all of those links. Look at a course that can show you these things. I'm going to assume that you do understand what these things are. So categorical variables, numerical variables, those are the two big ones. Numericals are obviously numbers. Categorical is categories. Beware of categories, remember though. I might ask someone in a survey to rank something from pain, for instance, from 0, no pain, to 10, the most pain. But even though those are numbers, they're not real numbers, because you can't say someone who has pain value of 5 or 6 has twice as much pain as someone with 3. That difference really is just not defined. That's categorical as well. I'm going to assume that you know this. Numerical variables, categorical variables, beautiful here in a data sheet. You can see this spreadsheet is called Comorbid, and it's an Excel file. That's the one we are going to use. Let's close that up. We'll save that. Now, very importantly, this file has got to live in the same folder as where we are working. So I'm actually going to drop out of this, and I'm going to just, inside of my folder structure, my Finder or my Windows Explorer, depending on the operating system you're on, I'm going to bring that file into this same Biostatistics Fundamentals and watch what's going to happen. So on my second monitor, I have taken that folder, that file where it existed, and I've brought it into this folder, the Biostatistics Fundamentals, using Python on my desktop, and it appears now as one of the files inside of the same folder. So you don't have to do that, but that means you have to explicitly tell Python where this file is and put that type in that whole address as a string. I hate doing that. Fundamentals course this, put this data file, this spreadsheet file, inside of the same folder as what the IPython or the Jupyter notebook file is in. So I'm going to say new, so Python 3 file, and as per usual, I'm going to call it, I'm going to give it a name, I'm going to say working with data. Working with data. And there we go. If we go back to this tab, we see working with data and the comorbid.xlsx file, they're inside of the same folder here. And that's the convention that I'm going to stick with. So let's get going. There is a library, perhaps one of the most fantastic pieces of software development ever, started by a guy called Wes McKinney. It's really this powerful, powerful library package that really makes data analysis this absolute fundamentally powerful but so pleasurable experience. And it's called Pandas. So remember how we imported things. It is basically import, and it's Pandas, and we're going to give it an abbreviation because we don't want to type out the word Pandas every time. So by convention, it's PD. So let's run that. So we've imported Pandas as PD. I'm going to create a computer variable. I'm going to call it df. Call it what you want within the reasons that we've mentioned before, df. And I'm going to call this function inside of pandas. I'm going to say pd dot, so that means pandas dot, and it's read underscore excel. And if I just put ex and I hit the tab, there's autocomplete. There's only one function that starts with read underscore ex, and that's read underscore excel. So it's read excel, and then my parentheses, always at the end of functions, and I'm going to have to put it inside of quotation marks, and that's comorbid, and because it all lives inside of the same folder, I can actually just hit tab. Jupyter Notebook is going to figure out I'm in this folder. Is there a file there that starts with that? Yes, there is, and if I hit tab, it just completes that for me. If it didn't live in that, I would have to put in the long address. Like on Windows, I would have to put C:, I'd actually have to put 2 backslashes and then desktop, and wherever you saved it, save things in the same folder. It just makes it so much easier. So read Excel is this powerful pandas function. It's going to import a spreadsheet for us, and now it's going to live as an object, space in the memory, called df. Shift enter, shift return. Now let's have a look. I just want to show you what is the Python type of this df. And it is a pandas.core.frame.dataframe object. We just call it a data frame. And that is what pandas does. It creates a data frame out of data. There's other ways to create data frames. I can create my own values. I can call on different distributions and put them as data point values into a variable, create a couple of them to create my own data. But this is the way we're going to go about it. Pandas, we're going to use pandas. We're going to import the spreadsheet here. Now, very quickly, let's just explore one thing about this data frame. We saw what the spreadsheet looked like, and there is this beautiful method called df.head. I'm going to call the head function. I can actually put a value in there. If I leave it blank, the default is 5, and it's going to display the first 5 rows. And that's just a sanity check. I just want to check that this import correctly. So shift enter, shift return. And lo and behold, very beautifully, it displays for me the first 5 rows. If I had put 3 there, it would put the first 3. I can also just, for another sanity check, just do the last 5. And that's just the tail function that we put in there. And if it's .tail, I can see the last ones and can actually help me see this little column here down the left hand side. That's the index, starts counting at 0, goes to 596, so we know there's 597 in there. So that's how you import a spreadsheet file. It's a nice beautiful file. I showed you that. Different variables, they have different statistical types, and we're going to explore this data frame in the next tutorial. So exciting stuff. Let's start exploring, let's start finding out what's going on inside of this data set of ours. If you didn't call the heads or tails, or there were too many here, you can just find out what the variables are, the statistical variables, by calling df.columns. So df.columns, we don't put open and close parentheses with columns. Just learn that. This is df.columns, and there we go. It's going to give you this list of all the statistical variables, the random variables inside of our data set. We see age, grade, logistics, temperature, pneumonia, hypertension, diabetes, mellitus. We've got all of those. I can quickly find out how many rows there are by just doing len. That comes from normal Python. We saw that before. It can give you the length of a list. So length df, length df, there we go, and we see 597. A better way to go about it is just to say df.shape. That's the pandas way of doing it. No open and close parentheses, just like columns. This is df.shape, and it gives you back, this is called a tuple. It's actually another kind of collection, not really important for us in this course, but it gives you back this tuple. Tuple is, instead of a list that goes in square brackets, it goes inside of parentheses. Don't worry about it, but it's rows, columns. There are 597 rows, so there are 597 observations or subjects in there across 7 variables. Rows, columns, as simple as that. Now, we can also do indexing on that, so I suppose we could say shape, df.shape, and if I were to say 0, that just gives me the number of subjects in my study. And if I say df.shape and I do 1, it's going to give me the number of variables. So you can do any of these just to get a sense of the size. So this is a tiny little data set. You're going to have much more variables in real life, and many more, perhaps not. Perhaps your study is a bit smaller. Doesn't matter. It'll tell you how many subjects are in there, if the data was entered properly, that each row is a different subject, and then across how many variables you have to play with. So there we go. We've got this idea. Now, imagine I only want to look at the age column. We saw the head and we saw the tail, but I just want to have a look at temperature. I can say df.temperature, and I just hit TE and then tab, because there was only one variable that started with TE, and that was temperature, so I did the autocomplete for me there, df.temperature. And this is very important. That's why we named it without spaces, without anything, just these words concatenated together. And for that reason, I can use this dot notation. So just have a look at that. It's not going to do all 597 for me. That's too much screen real estate. But there's the list of the temperatures together with its index. So this is actually not a data frame. This is actually called a pandas series. Don't worry about that. Don't worry about it. But it still brings my index in for me. And you say it jumps there from number 29 in the index, which is actually the 30th subject, till 567, and shows me the last of those. Because the other way I could reference this is by saying the square brackets and then in inverted commas and putting the temperature in. That would give me the exact same thing. But because there was no spaces in that word, in that random variable name, it allowed me to use that dot notation, and that just saves so much time using that dot notation. I love that dot notation, but it only works if your variables were named correctly. So there we go. I can just get back those. So that's one way I can, just look at all of them. What if I want to do something very special? I suppose there's so many things we can talk about, but let's jump into this one. I like this one. Let's just look at this. Let's just look at this grade one. So it's df.grade. It was df.grade, and we see A B C A B C A B. There's actually just the two AB. Now I can do something very special here. I could say, for instance, I don't want this whole data set with all the ABs and ABs. I want to just select all the A's. I want to discard all the B's. Just want to look at the patients who fall into group A. And this is something I want you to get used to, and I could have spoken about a lot of other things before, but for me this is of fundamental importance because we're going to use this so much. I'm going to show you what it looks like before we start explaining it. df.df.grade equals A. Have a look at that. You've never seen this before, but it will make sense. I think you can see what's happening here. It's inside of square brackets. So that means I'm addressing this thing. The df in the front means I'm talking about the data frame. And the address that I'm saying here is very specific. It says go to the column df.grade, and you see two equals signs there, equal, equal. Double equal signs in Python means go look at something and look if it's true or false. If it's true, keep it. If it's false, let it go. So equals A's, so it's going to look down that column of grade and only take the A's because that'll return a true value. This is called a Boolean value. Only has a Boolean value, only has true or false. And it will only accept the true values and it'll discard all the false ones. So df and then do an address. And there's a very specific address. I'm saying my address here is df.grade equals A. And now what it spits back for me is this new data frame, and it only has A's in it. There'll be no B's in there whatsoever. There's only going to be A values in there. And that's what, for me, this is the fundamental aspect of pandas, which makes it so powerful to look at your data, to explore your data. So that's easy for a categorical variable. What about numerical variable? Let's have a look at this. df. I'm going to say df.temperature, and I'm going to say give me back only the ones that have a temperature larger than or equal to 39. Larger than or equal to 39, let's make it 39.5. So it says take df, the data frame, and I want you to address that. And the way I want you to address that is go to the df.temperature. So I can't just say temperature, I've got to say df.temperature. You've got to tell Python what are you looking for. And go down that column and find data point values where the temperature is more than or equal to 39. And now if I look at this data frame that it returns, all these temperatures here will be 39.5 or higher. It'll discard all the others. Now you can see there weren't a lot of those. It actually can print all of them to the screen in one foul swoop. Now a natural thing that you might want to know is, can I combine these? Can I be super selective about all of these? Of course you can. This is Python, this is pandas, of course you can. There's nothing that you can't do. And all I'm going to do is I'm going to separate my selections by putting them inside of parentheses. So there's going to be one set of parentheses. So imagine I want only grade A and temperature more than 39.5. So AND is a very specific, it's called a logical operator. And there's a little symbol for that in Python, and it's the ampersand, so shift 7 on my keyboard, most keyboards. So I want to two things, one and the other. Both of them have to be true before that gets entered into what is going to be selected for me. If it's false, if one of the two is false, it is not an A, even though it might be more than 39.5, or it's more than 39.5 and it's a B, those get discarded. So let's have a look at this. So I'm just going to put in the df.grade, and that's got to equal A, and on this side we have df.temperature, TE capital, and that's got to be more than or equal to 39.5. And now if we do this even shorter, because it's much more selective now there'll only be A's and temperatures more than 39.5. So you can well imagine that you can build this, you can just ask anything of your data set, just select out whatever, to your heart's content, select really what you need. It makes pandas so absolutely powerful. Oh, maybe just show you one more little of these logical operators, and that's the not. It's actually quite a bit of fun. So let's say df. I don't strictly need to show you this, but what the hell? Let's go for it. df.grade, and I don't want the A's not equal to A. That's what this exclamation mark is, not equal to A. and that's going to return all the B's. Now there's just going to be B's in there. So it really is a powerful thing to do. Now, Pandas is an enormous package. Go look find its website, just Google it. It is enormous. It can do so many things. But for the sake of sanity and for the sake of this fundamentals course, this is what I want you to know. Yes, we are going to use some other things as this course progresses. The natural, it's just going to flow from the problem that we're going to solve. So you're going to see more of the power of Pandas, but I'd rather introduce it in the context of the statistical problem that we want to solve rather than showing you here. For me, this is really the fundamentals of it. Understand that it's the spreadsheet file that you imported, and understand that you can be so expressive in the data that you want to draw out of it before you do your analysis. That's what I want you to understand now. If you are, if your interest is really going, it's going berserk at the moment, it's running wild, go look at their website and start exploring it. It is just, it's a rabbit hole though. You'll never come out again once you start exploring. There is so much there, and it's so powerful. We are going to take from it the important things as we solve statistical problems. So that is working with data. Now that you can visualize your data, I think it's important for us just to stand still and just look at ways to simulate data. When you start to learn how to do your own data analysis, you don't always have access to a lot of data. And it's important for you to be able to generate your own simulated data. And that's very easy when you have a computer language. So let's have a look. In this section, I want to show you just how easy it is to create your own data. You might not have a big data set to work from, and you just might want something that you can use to hone your skills, to sit down and practice with. So we started a new notebook here. I'm going to call it Creating Simulated Data. And let's see what we're going to use. We're going to import Pandas as PD. We're going to import NumPy as NP. And then from SciPy, we're going to import stats. And then from plotly.offline, we're going to import iplot and init notebook mode. And we're actually going to call init notebook mode. And then from import plotly.graph objects as go. That's what we're going to use. So let's have a look at NumPy. We're going to use the NumPy library and then the SciPy library throughout here. I'm going to say np.random, and then I'm going to say seed. np.random.seed 123. Now the way that your computer generates a random number, so it just pulls a number out of the air, is actually quite complex. And these are referred to as pseudo-random numbers because they're not really random, but for practical purposes they really are. But we can force Python to give us a specific set of random numbers decided beforehand, so that if we run this code, we all see the same thing. And you can put any number there that you want. You can just put 1 or 12 or 10, or I've put 1, 2, 3. As simple as that. And let's just keep it at that. And then let's run the following. numpy.random.rand. numpy.random.rand. So all of these different types of random numbers, they all live in this random submodule. And the first one we're going to use is rand. So I'm using both of those cells. It's going to force the specific pattern so that if you do this, you're going to see the same value. Shift and enter, shift return, and we see 0.696469. So what rand actually does, it picks a number in this domain from 0 to 1. And in that fraction, it just returns a random number. And that's how you generate random numbers. So let's do the following. As per usual, I'm going to cheat a bit so you don't have to see me write code. So every time I do this, I'm going to reset this random seed value. If you run a few and you go back and run another random, it's going to follow a pattern down the line, so you actually want to reset it every time. So let's do this, and this time I'm just going to pass an argument called 10. So that's going to give me 10 pseudo-random numbers in this domain from 0 to 1. So we see 0.69, the same that we saw up there, and then 0.286 and 0.22. So we've generated 10 pseudo-random numbers. Let's do the following. What if we don't just want 10, but we actually want them in a little bit of a grid, in a matrix, rows and columns? So what I'm saying here, I want 5 rows and 3 columns of data. And there we see, beautifully, we have 5 rows across 3 columns. No problems whatsoever. Well, it's fair enough just to have these values at random between 0 and 1, but let's do something that might be a bit more practical if indeed you want to simulate your own data. So let's have a look at this. Random.seed again, and then numpy.random.randint. That's a random integer, and I'm going to pass 3 arguments. I'm going to say the low is 15 and the high is 86. So what you can see here, I've got a semi-closed domain here. On the left-hand side, there's a square bracket. So in mathematical notation, that means the 15 is included. And on the right-hand side, we have just this open parentheses, so the 86 is not included. So up until 86, but not including 86. Remember, that's how Python works most of the time. So if I want really numbers between 15 and 85 inclusive for my random variable here, I've got to put the high as 86. So 86 won't be chosen. So random integer, low 15, high 86, please give me 10 of those values, please. And we see 81, 32, 72, 62. So that might be a good way to generate a couple of ages, for instance, if that is what you want to simulate. Next up, though, let's have a look at the standard normal distribution. Up till now, the numbers that we've really used here come from what is called a uniform distribution. So every value in that domain has an equal likelihood of being selected at random. But that's not what we always want. Sometimes we want random numbers to be generated from some form of pattern, from some distribution is what we call it in statistics. So let's look at the standard normal distribution. Remember, the standard normal distribution has a mean of 0 and a standard deviation of 1. Now, the code for that would be np.random.randn. So there's a little n in there. So the standard normal distribution. Let's do that. And we see the negative numbers now. So most numbers will be close to 0, and the further it goes towards the negative one side, towards the positive one side, those numbers become less and less likely to be chosen at random. So that's good. The pseudo number generator there, generating numbers for us from the standard normal distribution. Let's have a look at this. Now I'm going to use something from SciPy. Remember, we said from SciPy import stats, and stats actually has a lot of distributions to choose from. So what we're going to do here is actually specify our mean and standard deviation. So it's still going to be a normal distribution, but other than it being the standard normal distribution, we're going to specify the mean and standard deviation. And this is how we go about it. So it's not np.random anymore, but stats.norm.rvs. So that's new. Don't forget this RVS. And then it takes 3 arguments. LOC, that means the mean or location, that's 15. The scale means standard deviation of 3. And I want 10 of those, please. Let's run that. And we see now that we get these 10 values with a mean of 15 and a standard deviation of 3. And we actually have 10 of those. So as you can see, these things are really, really easy to do. Let me do one more. And we're going to take that from a sampling distribution, the chi-squared distribution. So 10 random data point values from the chi-squared distribution. And we're just going to have a degrees of freedom of 2. So that's stats.chi2.rvs, just the lambda there. And then the size equals 10. And we see that we do have these values, no problem whatsoever. Next up, I want to show you just how to choose from a sample space of categorical variables. Yes, you can do that as well. So my random.seed, 1, 2, 3 again, and this time it's np.random.choice. So I'm going to pass a list here, a Python list. So it goes inside of square brackets, and because these are strings, they go inside of each one of them, at least each of the elements go inside of quotation marks. So that's treatment group and control group. So please choose from those. I'm going to say size equals 10. I want 10 random choices from those two. And I'm going to say replace equals true. That's the default, but we've put it down here. That just means if you have a bowl and it just has these 2 little pieces of paper in it, one says treatment group and the other says control, you put your hand, close your eyes, put your hand in, draw one of them out, and it says, well, treatment group. Well, you throw that back in the bowl and you mix the 2 around and you pick one at random again. That's what replace means. And if we don't replace, of course, we're only going to get 2. We can't get 10. So it's got to be thrown back. And I've actually can set the probability of each of these. So in order in which you use them in the list, treatment was first, group was second, you put the same order here, and this is also the default for this argument P. It's 50-50. So if there was 3 of them, as long as these total up to 1.0, they've got to total up to 1.0. So if I had 3 there and I wanted a third each, I would just say 1 divided by 3, 1 divided by 3, 1 divided by 3, so that I know that it does add up to 1. So if you want it skewed towards one of them, you can do this 0.6, 0.4, for instance, whatever the case might be. And there we get control, treatment, treatment, control, control, treatment, control, control, treatment, treatment. So at random there, and that is how you can create the sample space of categorical variables and draw at random from those. In the next video, I'm going to talk to you about how to create a data frame that we can use to create our data set, and we're going to use what we've learned here to create these random data point values for a variety of variables. So here we are. Let's just have a look at how to create a data frame. Now, Pandas provides for many ways for you to actually create data frames. I enjoy using the dictionaries, and that's what I'm going to show you here. First of all, let's remind ourselves of one thing we've seen before, and that is numpy.arange. There we go, numpy.arange. And I want to go from 1 to 10. Let's just remind ourselves what that does. It starts at 1, and as per usual, it does not take the 10 into account. So it's only going to go up to 9. Remember, that's start and stop. And the step we didn't put in, we can put a comma 1 in there for the step size, but that's just by default. It is going to be 1. So remember, that's how arange works. So let's create a numpy, or let's create at least a pandas data frame. I'm going to copy and paste as per usual. I'm going to use numpy.random.seed 1, 2, 3 as per usual. And I'm going to call my data frame, I'm going to call it df_dict, the data frame from a dictionary. And I'm going to use the python.dataframe function here. So that's a high-level function. It's going to create a data frame for us to hold our data that we're going to work in. And then inside of our set of opening and closing parentheses, which denotes that we're using this function data frame, I'm going to pass a dictionary. And remember, a dictionary goes inside of curly braces. So there's my opening and my closing. There we go, the two of them, curly braces. And what we're going to pass, as with a dictionary, is key value pairs. So there's my first key value pair, my comma, see the comma there, and then my second key value pair, comma, and my third key value pair. So I'm actually going to have 3 columns here. My first column is going to be called ID, and that's a name. I put it inside of quotation marks. Remember not to use spaces. It just makes it so much easier to use pandas if you don't put spaces in your variable names and your column names. And then remember, with key value pairs, they're always separated by a colon. And I'm going to say np.arange 1 to 11. Remember what that's going to give me? 1 to 10. So each row is going to have a different value, and it's going to go ID as the column head. Think of a spreadsheet. ID is going to be the column header, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows below that. The second one is going to be age. And we've seen this before now, numpy.random.randint. I'm going to start at a low of 18, go to 86, so that actually means 85, and 10. So 10 random integers for the ages in the age column. And then I'm going to have a group column, and that's going to say numpy.random.choice. So remember, it's a categorical variable, and I'm only specifying the size. So I'm not saying replaces true, because that is the default. You don't have to put it in, and I'm not saying p equals 0.5, 0.5 in a Python list, because that's also the default. So let's run that code, and that's going to generate for us a very nice dictionary, at least a data frame. So let's have a look at what it looks like. There we go. And there we see an age column, a group column, and an ID column. First thing that you'll notice now is not in the order that I used up here. It's actually going alphabetically, so A, G, D, and that's not always what you want. But first, let's just stand still and have a look at this. Beautiful data set for you to work with and do some statistical analysis. And you generate it all by yourself. You've simulated some data, and you can use this in learning how to use Python for your data analysis. So look, the age, and we see our 10 values there. We see the random selection of our sample space of categorical variable, and we see the ID 1 through 10 there. On the left-hand side, as per usual, we see the index. Each of these rows, each of them have their own index, and remember, Python starts counting at 0. So what if you don't want this alphabetical sorting here? We can do something else. We can actually tell pandas in what order we want them. So have a look at this. Everything is the same except outside of my dictionary here, I'm passing some more, one extra argument at least to the data frame function here, and it's called columns. And I pass it as a Python list. In other words, it goes inside of square brackets, and we have ID, then age, then group, and it's got to be exactly the same as this, otherwise you're going to run into trouble. So if I run this and we look at df_dict, we're going to see that we now have that order, ID, then age, then group, and that might make more sense to you. So you might have created your data frame, but you start playing, start your exercises, and then you realize, well, it would have been nice if I just had another column. Well, it's very easy for you just to add your own column, and this is how we're going to do that. So again, random.seed, just to keep things similar, and I'm going to say df_dict, and I'm going to pass a new column name or variable, and I'm going to just call it variable x. And what that's going to do is the following. It's going to take the age column, remember, so there are 10 age values, so df_dict.age, that calls the age series, that whole column. And just to make things simple, I'm going to call .values. So what .values will do, you don't necessarily need it, but it just draws out the numbers and not all the extra information that goes with a Python data frame. So it will just look at those 10 values. You needn't put this, but it's good form to do it. And what we're going to add to that is the following. Now look at this very carefully. It might be intimidating the first time you see something as complex as this. We see all these parentheses. Anyway, it's numpy.abs. That's absolute. Remember, absolute values, negative, all the negative numbers become positive numbers. So the absolute value of -3 is just +3. And the absolute value of +3 is, well, +3. So we're just going to turn all the negatives into positives. And so look at this first part here. I am going to say numpy.random.rand n 100. So what's that going to do? It's going to give me 100 pseudo-random numbers from the standard normal distribution. And so I've got that first. So I've got my 100 values there, and I'm doing multiplying each of them by 10. 10 times that. So what this does is actually called broadcasting. It just means it's a term which says I'm taking a single value, a scalar, and I'm multiplying it by a vector. Don't worry about all of this. A vector just means it's a whole column of numbers. And if I say 10 times that, it just means I'm taking take each element of those 100 and I'm going to multiply it by 10. So what I'm doing here is I'm generating 100 values from the standard normal distribution. Remember, mean of 0, standard deviation of 1. And I'm multiplying each of them by 10 just to make them slightly bigger. And then I'm turning all the negatives into positives, because remember, this is the standard normal distribution, so we're going to have negative numbers as well. I'm just turning them all into positives. So here, remember, I had 100 age values. That's what we did here. We asked for 100 values. And we can see the ID column there going up to 100. So I'm taking those 100, and element for element, row for row, I'm adding whatever was in the age column to this new random number, which comes from a standard normal distribution, but multiplied by 10. Very easy to do. And there we go. Let's do df_dict, and let's just do .head, so that we can see the first 5 rows. 5 is the default. We don't have to put that, but there we have it. So I have an age of 84, and that jumped in variable x to 94. So these two are now correlated. See what I did there? I created this new variable, but it is based on this one. It is based on that one. And if I just run the following bit of code now, don't worry about it, because we are definitely going to look at how to do all these beautiful graphics. But I'm just going to do a scatter plot. So we're going to just have age on the x-axis and variable on the y-axis. Don't worry about the code now. And look at that. Look at my simulated data. I've generated all these ages on the x-axis, and then all variable x here on the y-axis. So that will be a pair for each patient. And if I hover over these, you can see that patient was 29 years old and had a variable X value of 43.95. This patient had an age of 33, see the 33 at the bottom, and had an X variable of 54.23. But I've created it such that they are correlated. See how the age goes up, variable X also goes up. There's this tendency, there's this correlation between these. And the way I did that correlation was very carefully here in this line of code. So I took each of the values and I added to that something a bit random, but it's based on this first one. And that's how you would create your own variables that are slightly correlated to each other. So that's it. You can generate your own simulated data, some fake data, if we can use that term. So go out, generate some data, and it will be very useful for you to play with, to practice your skills with. In this section, I want to talk to you about data that is not clean. Now, that is very typical. You will almost never find a data set that has all the values filled in, no duplicates, no errors made, no numbers where you should only have categorical variables, no categorical data point values where it should only be numerical data point values, etc. You have to learn how to clean up your data. Now, you can do some of that right inside of a spreadsheet, and some people prefer that before they bring the spreadsheet into Python, into this Python environment to work with. Sometimes I do like to do that. I think of it as sterilizing the data, and I want to operate on a sterile field. So I'm only going to bring it in once it's cleaned up in Excel, but you can do a lot of cleaning up. You can do all the cleaning up right inside of pandas. So let's have a look. I'm going to import pandas as PD and NumPy as NP. Now we're going to have a whole section on doing graphics, that's plots and graphs. So don't worry about this section now, but in case I want to draw one or two charts, I'm just going to do this import from Plotly. Don't worry about it now. There's a whole section devoted to that. I'm going to import a XLSX file, so I'm going to call my data frame df, so pd.readExcel, and we import that. Remember that this file lives inside of the very same folder as this notebook, so I don't have to refer to it by its address on my hard drive. So we can just run that, and let's have a look at the head. There we go. We see beautiful 4 variables, a group, which seems categorical, a treatment, which also seems categorical, an age, numerical, and a cholesterol value. Now, that seems good, but let's have a look and see if we can detect any problems. Let's just have a look, first of all, at the shape of our data, df.shape. Remember, that's going to give us the number of rows, comma, the number of columns. So indeed, there are 4 columns, we can see that, but we see there are 301 rows. Now, the one thing you can do immediately is just to look for duplicates. Now, be careful. It might be that there are 2 subjects, 2 patients or subjects, whatever, in your data set that has exactly the same entries for each and every one of the variables. That is certainly possible, so you have to understand your data before you do the following. I'm just going to copy and paste from my second monitor here just to speed the typing up a little bit. And there we go, we see df.drop_duplicates. So it's going to go row by row, and it's going to find duplicates. I can pass some arguments. The first argument that I'm using here is keep equals first. You don't have to put that. That's the default. If you have 2 exactly the same, it's just going to delete the second one. And in place equals true, you've got to put that one. That means I'm making this change permanent. I'm changing this df data frame permanently. So let's do that. And now let's look at df.shape. df.shape, that's the one I want. Let's have a look at it. 299. So it seems as if we had 2 rows that had exactly the same data. Now let's move on. Let's have a look at df.dtypes. If we look at df.dtypes, we're going to see there's our 4 columns: group, treatment, age, cholesterol. Group seems to be an object. Object is Python speak for categorical variable. That's fine. It looks down the treatment column. It finds only objects, categorical variable. It looks down the age column. It finds float 64. That's decimal values. That's fine. It goes down the cholesterol value, and it finds it's an object. Something is wrong in the cholesterol. If I look back here, it seems to be numbers, but somewhere down the line, there's something that is not a number. Something completely different. So let's have a look at this. Let's start off with the group variable. I think let's start there. So let's have df.group, and we're going to do the value counts. value underscore counts. So it's going to look for all the unique data point values, so the sample space, and count how many there are. Now remember, we're supposed to have 299 rows, so let's have a look at that. We count, there's 200 group 2s in there, 99 group 1s, and 99 group 3s. Well, if I add that together, I get to 298, not 299. So there's certainly one of the rows that is a bit problematic. Just to be very sure, I can just ask for the length of df.group. So if I just look at the group column, I see that they're 299, but if you add these, you see there's 298. So might it be, which is something that is very, very common, a cell that's just empty? Someone just didn't capture that data, and that happens so much. When you design a data collection tool, best to design it to force the person who's entering the data to be precise about this. So let's find out if there is indeed a cell that's empty, and the way that we're going to do that is df.group, so we only want to look at that, and we say is NA. NA is not available, is not available. It makes sense, it's just normal English. And I'm going to use another function at the end, .sum. So I want all, I don't want you to give me the rows. I'm asking Python, not give me the rows, but count how many empty cells there are, and indeed there is one empty cell. So that might be problematic. Let's go down the treatment group. Let's do df.treatment, and let's say value counts there as well. Value count, counts, there we go. And if we tally that up again, it comes to 298. So is it possible that there is something in here that's missing as well? Let's do that. Remember, is NA. If I just do that, it's going to give me this whole row of true false values. If it has something in it, it's going to be false because it's not available. It actually is there, and then false. But all I want is the sum. I want to sum all of those that are not there, and indeed there's one missing as well. Let's have a look at the age function, and age variable at least. So let's do .age.describe. It's a numerical variable, so we can just ask for describe. We see there's 298. Again, a bit of a problem because we know there should be 299. We see a nice mean, nice standard deviation, but minimum -10, maximum 104. It might well be that you know your data set intimately, and you know that there was no patient, say, that was older than 85. So that might be a problem. There's certainly no one who's younger than 0 years old. So that's a problem that we have to fix as well. Let's just check this out. Let's just see if there is any empty cells, the way that we can go about that. Now it's easy if your data set is small, you can go into Microsoft Excel or LibreOffice Calc, whatever spreadsheet software you have, and you can go have a look at that. But let's just see. So we see, yes, indeed, there is one empty cell there. If we go to cholesterol, which we want to describe because we think, well, it's numbers, it's got to describe, and this comes out, 298, unique 86, top is 5, frequency is 10. That does not describe a numerical variable. We should be seeing mean, standard deviation, minimum, 25 percentile, etc. So something has gone wrong there. So we have to make a plan to find out what is going on there. Now I'm going to take a little sidetrack here. I'm going to show you something. I'm going to say A equals 3, B equals 4, and I'm going to say A plus B. Now you know what this is going to do. It's going to be 7. But I want to show you a little function that I'm going to create. Have a look at this. I'm going to say addition equals, and I'm going to use this thing in Python. It is called the lambda function. And the lambda says I'm going to take a x and y. So I'm going to take two variables and then a colon. What do I want to do with them? I want to add x plus y. So it's called a lambda function. A lambda function, after the lambda comes a space, and then you say what the variables are. Sometimes you just want one, so x, and you want x squared. But here I want two variables, and what I want to do with them after the colon, I want to add them. So now if I call the addition function something that I've created, and I pass a and b to that, what do you think is going to happen? It's going to be 7. It's taking this x and y, the first one being a, y being b, and it knows a is 3, and it knows b is 4. I pass that, and it adds them, and I get that. So there is a function called isInstance. instance. And I'm going to say, is instance 3, is that an integer? So Python for integer is int, and it's going to return true. So it checks what you passed, and it wants to know. You ask it, is it the thing that you want? So you could put in float there, or str for string, whatever. Now have a look at this line of code, what I want to achieve here. So let's copy and paste that. So I'm going to say df, then df.cholesterol. So what this means is, please go down the cholesterol column of df. So with these square brackets, what we're actually doing, we're addressing. So I'm addressing this column. So it's not just df.cholesterol.apply. I'm going df and then addressing df.cholesterol, something you've got to get used to. And then .apply, something new. And what I want to be applied to this column, all the rows in this column, is a lambda function. And the lambda function is of a single variable x, and what it does, it says, is instance x a string? So you can imagine what's going to happen here. It's going to go down the cholesterol column and look at each of the individual data point values, and it's going to say, is this one a string, true or false? Is the next one a string, true or false? And because I've indexed it, so I'm asking for all, I'm indexing by the row. There's no comma column here, just the rows. And df, it's actually going to return for me not true and falses down a column, it's going to return for me the actual problem case. And there we go. We see in the index 26, there's a patient who was in group 3 with treatment B with an age of 42 and a cholesterol value of X. Someone who filled in this data set was, had good intentions. It said, well, we didn't know the cholesterol wasn't measured. The lab doesn't have that result. Let me just put an X there. Of course, it throws off your data analysis, because in that column, all you want to see is numerical variables. And if it wasn't there, you want to see an empty cell. It's not an empty cell. Someone put an X there. They tried to be good, but in the end, it is not good. So how do I get rid of that X in the cholesterol column? Well, it's very easy. I can just change everything to numeric values and have a look at this. Have a look at this. I'm going to say df.cholesterol equals, I'm going to change that column. I'm going to say pd.toNumeric, to_numeric. So it's going to change everything to numeric values. df.cholesterol is what I want you to go down. And if you find any errors, something that is not a number, just delete it. That's what this coerce means. Errors equals coerce. And that says it just empties out that cell. Take that X away and leave nothing in its wake. So if I do that now, and I should have that X gone. So if we say df.cholesterol.describe, what we should have here is an actual description. We now have 297, so we know there's some missing. And we have a mean and standard deviation. That X is now gone from cholesterol. We'll carry on in the next video. So in the previous video, we fixed this problem of this stray X, which is a string, which is something that should not be in a numerical value. And we noticed that there were 297. We know there should be 299. So let's just see if they are indeed empty cells. Remember how to do that. I'm just going to do df.cholesterol is in a sum. I want to run that. Just let me show you something. We haven't done this. So if I were to just do this, if I were to just do that without the sum, what it's going to do, as I said, it's going to go through all of them. I mean, it puts ... in the middle because it doesn't want to fill up your screen with all of these, and it'll say true or false, true or false. It'll be falses because there is actually a value in there. It's not available. And you go down, you go down, you go down. There's one of the true ones there. So that was a missing cell. So what can we do with these missings? Well, we can replace the empty bits. That would be one way. We can just leave them alone. I mean, if that data doesn't exist, it doesn't exist. But it might very well be that you want to fill those empty values with something. So I'm going to say df.cholesterol.fillNA. Fill those that are not available. And what do I want you to fill it with? Go df.cholesterol.drop all the NAs and get the mean. So ignore all the NAs. So there's going to be 290, what was it? Let's have a look. It was going to be 297 values. Only look at those, get the mean, and fill all the empty cells with the mean. Now you can do median, you can do all sorts of things. But this time I'm going to ask for the mean. Please fill those with the mean. And if I were to run that in places true, mean make this permanent. And what we do now, if we look at is there any empty values, let's have a look at that. In SA.sum, nothing, 0. Everything is gone. It looks perfect. So there's a variety of things that you can do. Let's have a look. Remember in our group column, remember there were some missing values in the group column as well. Let's do something with that. What we do here is to pass a method. So we're going to say df.group.fillNA, fill all the not available, all the empty cells, fill it with forward fill. Forward fill means it's going to look at the value that was in the row just above the empty cell, and it's going to copy that down into the empty cell. Again, I'm saying in places true, and now there'll be absolutely no problems there. What though if you were interested in not filling up the values, but you were just interested in deleting all the rows that were not complete? You're not interested in analyzing data that was not complete. For some reason, your data analysis is going to be very strict, and you're only interested in those patients or subjects that had all their variables completed. Let's have a look at what you can do. We're going to use data frame, that was our data frame, .drop_NA, drop these not available, these empty cells. And I'm going to say very specifically access equals 0. That means it's actually across the columns. If you think about that, so it's going to look at a row across all the columns. And I can specify how, either all or any. Any means if any of those rows, that patient's details, that all the variables for that patient is missing, if any one of them is missing, drop that row completely. I don't care if all the other variables are available for that patient or subject, delete them. As I say, an alternative is all. All means if all the variables in that row are empty, you can drop it. But any is more commonly used. So if I were to decide that I want to drop those, I can just do how equals any, and then in place is true, which means lo and behold, it's gone permanently. So if I say df.shape now, we see 297. So we've deleted 2 rows because they didn't have any values in. Now I'm completely sure that all the data cells are actually complete, no problems. Okay, let's try and fix this describe of the age. Let's just bring that up again. I'm going to copy and paste here from the second screen. Let's do that. And remember, we had patients that were less than 10 years old. There was a 104-year-old patient there. We really want to get rid of these. So what are we going to do? Well, let's have a look at this. Let's look at all the patients that were younger than 18. So I'm going to use this indexing. So df and then index all the rows where df.age is less than 18. So that's only going to show me, and it shows me these 1, 2, 3, 4, 5, 6, 7, 8, 9 cases where there was an age of 1, 10, 14, -6, -10, 13, 17, -7, 2. And I tell you, if you start working with data often enough, you get data from someone else. This is what it looks like, and it can be very annoying. So how are we going to fix this so that we have only patients that are older, equal to or older than 18? Because we know that is what our clinic looked like, our ward. There was no one younger than that. So I'm going to actually overwrite my data frame. So I'm going to say df equals df, and I'm going to index where all the ages are equal to or more than. So more than or equal to. There you go, more than or equal to 18. So let's run that. And if I now say df.age.describe, what we're going to see, at least the minimum is going to be 18. They are all gone. Those younger ones are all gone. Now we can do exactly the same if we know for sure that our oldest patient was 85. We're intimately familiar with the patients that were examined in this data set. We can just do this df, and we overwrite the data frame as well. And now we know we've gotten rid of all the ones that were older as well. Let's do df.shape now. If we do df.shape, we see that we're down to 279. So we've dealt with quite a few more of these values. So you can see that is really how we maintain this, how we clean up the data. I think you've got some good ideas now of what to do. So either clean up your data inside. Well, first prize is have the data tool, your spreadsheet file, your database, whatever you're going to use, have it set up so that whoever enters the data doesn't make any mistakes. And there's ways that you can design that. Should you get it in a format that you know there's going to be problems with, sit with a spreadsheet file in Microsoft Excel or another spreadsheet software and clean it up, or use some of these simple tricks that I've shown you now for pandas. So in this part of the course, we're going to look at descriptive statistics. It's a very important part. Always start off with allowing the data to tell you the story that it's hiding. The data really wants to tell you something, and as human beings, it's very difficult for us to know what the data is trying to say. You see columns and rows of data. You can't just look at a big spreadsheet and understand what's going on. We need to summarize that data, and it's the summary of that data that really begins to tell the story of what is going on. So let's have a look at some descriptive statistics. We started the Jupyter Notebook. We're inside of the desktop Biostatistics Fundamentals using Python folder, and we're going to start a new tutorial. So new Python 3, there we go, and we're going to call it descriptive statistics. Descriptive statistics, there we go, descriptive statistics. Rename that. So what is descriptive statistics all about? As human beings, we are terrible at looking at a huge data set. Imagine, multiple variables, thousands of rows, looking at all those values. Your brain can't make sense of that. You need it to be summarized in one way. So immediately when you get a data set, descriptive statistics is one of the first things that you should do. Let that data start telling its story, and the way that it tells you its story is by summarizing that data. So that's what we're going to do here. Let's import a few things to start off with. We need a few additions to Python. So we're going to import pandas. We know pandas by now, and we know that we usually call it PD. And we're also going to import numpy as np. Let's import those two very quickly. So there we go. It's run already. It's imported. Let's get going. We are going to use exactly the same data frame as we used before, the same Excel spreadsheet. I'm going to call it df again. I'm going to say pd.read Excel, and what I want is the comorbid file, a spreadsheet file. It lives in the same folder. Let's go back there in the tab. We see comorbid. It's in exactly the same folder or file, folder I should say, as my descriptive statistics notebook file here. We see the little circle there. It means it's open, and there it is. It's open indeed. So let's import that. Lo and behold, sanity check, df.head. Let's just look at the first two. Yep, imported correctly. I'm happy. Let's go. First form of descriptive statistics we're going to look at is measures of central tendency. And we're going to start off with numerical variables, and you know where this is going. The other term for it is point estimates. I'm going to take all those numbers, and I'm going to ask for it to be represented by a single value. So I have all these numbers. I want it to be summarized by a single value. The first one that comes to mind obviously is mean or average, and that's very simple. So let's just have a quick look again. df.columns, remember that's going to give us all our variable names. It was short enough, we could see it there in the df.head, but it's age, grade, logistics, temperature, pneumonia, hypertension, diabetes mellitus. So let's just look at the age. What is the mean of the age? So let's use, there's different ways we can go about this. I'm going to use the pandas way here. So I'm going to call df.age. Very easy. I've shown you in working with data how to get just that column of data. So df.age, and there's a function called mean. Boom, there we go. 55.1 is the mean age of all of those ages that were in there. And remember, there was over 500 of them. As simple as that. Just call that. Now, let's go on to median. Remember what median is? It takes all of the values, it ranks them in ascending or descending order, cuts it in half. What value will be there such that half of the values will be greater than and half of the values will be less than. Remember, if there's an even number, it's going to take the middle two and take the average of that. I'm sure that you know all of it. So df.age, age, and I'm going to ask for the median. As simple as that. Let's go, and there's the median. We can see the mean and the median very close together there. What about a categorical variable? Now remember, with the categorical variables, even if they're expressed as numbers, so for instance a pain score from 0 to 1, or how satisfied were you with something in a survey that you fill in, and you could mark it from 0 to 5, those might be numbers, but they are categorical variables, and for that we usually use the mode. But for numbers, for numerical values, if they are discrete, I suppose you could also use the mode. Doesn't matter. We're just going to do mode. So let's go df dot, let's do the diabetes, and we're just going to call dot mode on that. And we're going to see, you know, it was just yes and no, it was dichotomous variable, and no was the mode that appeared most commonly. And the 0 there means that as part of the index, there was 0 and 1. There's only 2 rows in this in the sample space of diabetes mellitus, which was no and yes. So I want to show you this df.diabetes.value counts. Get used to that now. We're going to see this a lot. Value counts, very useful. So what that's going to do, it's going to go down a categorical variable like diabetes mellitus. It's going to define the unique values, data point values, in other words, the values that make up the sample space, and it's just going to return them for us and how many there are. So there was no and yes are the two unique values that it found. So the sample space of data point values that make up this variable is just no and yes. There's just 2, it's just dichotomous. And there were 532 no's and 65 yeses, and for that reason the mode was returned as no. But this value counts, very nice one, because it can really, it gives you the sample space and it tells you how many there were. Now those are expressed as counts, so I want to show you one more thing. So diabetes.mellitus, I'm going to do .value counts, remember value counts, and I'm going to pass an argument. The first time we're going to see this, we're actually calling a function, but we're going to pass an argument to that. And one of the arguments there is called normalize. And it doesn't put the spaces there, so I actually use my arrow keys, go back, and I put spaces in there. And I'm going to say true with a capital T. True and false, they are special words, commands inside of Python. So I'm going to say normalize equals true, and what that does, it's going to bring back, it's going to return the fractions. So 532 plus 65, and it's going to divide that by the sum and divide 65 by the sum to give me back the fractions. So I can immediately see that 89% did not have diabetes and 11% had diabetes. Just as a matter of interest, if I put times 100 here, I'm going to get the percentages back. You know, you can do that. You don't have to do that. Fractions or percentages, doesn't matter. You're intelligent. You know what the difference is. You know what this means. So very good there. Now, let's just do one more thing. Remember how we selected only certain things? I want you to explore this. I want you to do this yourself. Let me show you one example and you play with the rest. df.grade, and let's take only the values that were A in that, and then we're going to call the age, so .age, .mean. See how we string these things together? Yet again, the absolute fundamental, awesome, power of pandas. You string these things together. So I'm saying, take the data frame. I'm going to index only certain rows, and I want you to do that on the grade variable and only select those ones with A. So now I've got this little data set, the sub data set. It only has patients in it that was grade A. And I want you to take their age column, and I want you to get the median of that. Voila. So now it is the mean age of only the A patients. Just for the sake of clarity, I just want to show you this. If I were to say, imagine just that you had these spaces inside of the names of your variables, the column names in your spreadsheet. Just imagine there were spaces in there and you didn't clean it up, and I haven't shown you inside of pandas how to rename the columns, because you can do that right inside of pandas. So let's imagine this data set that came in wasn't clean, you haven't cleaned it up. Then just use the square brackets and quotation marks. So I can say that. So grade like that, equals A. So let's say equals A. So just do that. I should actually do this. Let's do this correctly. So the grade there equals A. That looks much better. Close. Okay. So I never use this. So you can see I struggled a bit there, but you've got to get it right. So df grade instead of df dot grade. So it's df, and then inside of the square brackets quotation, put the grade. If there wasn't spaces, so imagine this was grade of patients. You know, it was something like that. Was the column name in your spreadsheet? This is the way you would have had to go about it. This was clean, so this was it, and then equals A. And then imagine age was also not clean. You would have had to do this age and then dot mean. So if you look these things up, you might see this kind of notation. It's purely different notation. For safety's sake, if there was illegal characters in the variable names, in the column names, you would have to go about it this way. You're going to get back exactly the same. But that's why I love having those clean, neat, sterile, beautiful variable names, column names in my spreadsheet, so that I can just do this dot notation. It's much faster, much simpler. It reads better, but it is exactly the same thing. So play around with this. Select only certain things and get their mean, get their median, and get their mode. Very easy to do. So another way to tease information out of your data is to look at measures of dispersion. So we looked at measures of central tendency, summarizing all of the values by a single one. But that doesn't tell the whole story now, does it? Because we need to know how spread out this data is. Measures of dispersion. So the first one I want to show you is just the range. Now remember the range, that is the minimum value and the maximum value. So let's just ask the question, what was the minimum age of the patients in our little simulated data set here? Age.min, that's minimum. We call that, we see the youngest patient was 18 years of age. What was the age of the oldest patient in this data set of ours? And that's just max, min and max. If I could just spell max, M-A-X, there we go. And we see that the oldest patient, simulated patient here, was 90. So that is the range, the minimum and the maximum. And the range, strictly speaking, is the maximum minus the minimum. So you could just say, let's do that. So it was df dot age dot max, max, and then minus. Subtract from that df dot age dot the minimum. And there we have the range. 90 minus 18 is 72. Standard deviation. Remember what standard deviation is? It's the average difference between each value and the mean. And let's look at what the standard deviation was. One standard deviation of the age, df.age, and it's STD, standard deviation, as simple as that. So you could say what the mean age was, plus minus 21.7, the standard deviation. Remember, standard deviation is actually calculated from the variance, which is the standard deviation squared, because we square the differences between each value and the mean. So that's df.age, and it's just VAR for variance. And that will just be the square of the standard deviation, or the standard deviation is the square root of the variance. So let's have a look at the quantiles. We can look at quartiles or percentiles, the same sort of thing. Remember with median, we divided the data set of values, the sample, into 2 equal bits. With quartiles, we're going to do that in quarters. And with percentiles, we can actually specify whatever percentages we want to divide this up in. So I'm going to call df.age, and it is quantile. We're going to use them. We're actually going to pass a list. And I'm going to pass all of them, or the important ones that I want. 0 would be the 0th quartile, and that would be equal to the minimum. I want 0.25, that's the 25th percentile, or the first quartile. 0.5, which is the median, or the 50th percentile, or the second quartile. 0.75, the third quartile, and then 1, which is equal to the maximum. There we go. We see the minimum and the maximum there, and we see the 3 quartiles. First quartile, second quartile, which is the median, and the third quartile. So that would mean the 75% of the values are less than, or 3/4 are less than this value of age of 75, and 1/4 will actually be more. So you can express you can do all of those. There is actually a numpy function as well. Let me just show you that. That's numpy.percentile. And numpy.percentile, we can pass to that the age column. But this time, remember if I say df.age, let's just do that. I'm going to show you a little shortcut. I'm going to hit escape, A, enter, and that's going to add a cell above, but I could also have gone here, cell, where do we go? Or insert, I should say, insert cell above. So let's just do that. If I say df.age, that's going to return a pandas series to me. So I'm going to have both the values and I'm going to have this index. And that's not what I want. I actually only want the values. So let me do that little trick again. Escape, A, enter, or shift or enter, or just go to insert cell above to insert this. I want df.age.values. So that is going to return to me a numpy array, which is actually only the values. So now we don't have that indexing with it anymore. Just a little special thing you can be aware of. So if I use a numpy function here, I better pass a numpy array to it. So I've told numpy, the percentile function, that those are the values, and now I have to pass a list of all the percentiles that I want. So let's do the same. I want the 0th, the 25th percentile, the 50th percentile, the 75th percentile. Let's just be quirky about this, the 90th percentile and the 100th percentile. So this time not the fractions but the actual percentiles, and now you're going to get all of them back. What else can I show you? The interquartile range. Remember, that's the third quartile minus the first quartile. So that would have been 75 minus 35, which gives you 40. There's in SciPy. Now, have we seen SciPy before? SciPy stands for Scientific Python. It's just an extension. You can see it as an extension of numerical Python. It has even more things, but it's built on top of a numerical Python. So I'm going to do this special thing. I'm going to say from SciPy or let's say from SciPy import. It has SciPy, like many other libraries, have sub-libraries inside of them. So from SciPy, I want to import the stats sub-library. You know, this is an important thing. Have a look at that. There are these sub libraries inside of bigger libraries. So I want the stats library, sub-library from the SciPy library. And there we go. And now I can call stats.iqr. And this can just take df.age. And there we go, 40, interquartile range. Just in case you didn't want to subtract that by going the long way around. So that was measures of central tendency, and now measures of dispersion. Now I want to show you one more thing. Now you can do all of these separately, but there's actually a nice little shortcut for numerical variables. Let's have a look at this. df.age.describe. This one you're going to use all the time now that you know about it. And what that does, it does all of those for you. It tells you how many there were, the mean, the standard deviation, the minimum, first, second, and third quartile, and the maximum, all in one go. And that's very neat. So df.describe, remember the describe for your numerical variables, and remember let's say the categorical variables. For that one you use value counts. So remember these two. We're going to use them over and over again. When you start doing your own analysis, you are going to do them over and over again. The describe for numerical variables and the value counts for categorical variables. And that's why you really need to understand the difference between those types of statistical variables. There you go. We have started to explore. So take this data set, start exploring it to your heart's content. But do what we saw in the working with data tutorial. Start selecting only certain rows, the way that I showed you, and then call these descriptive statistical functions on them, and start playing around with them and start exploring. Is there a difference between the mean age of the patients with grade A and grade B? Is there a difference in the mean age of patients in group A and group B. So start doing that. Play and see if you can get that going. Now that you can do descriptive statistics, another important method of trying to get to the story that the data is trying to tell you is to visualize your data. It's the way that human beings interact best with data is to have it visualized. It really, the story that it's trying to tell really comes out. And it really makes it easy for us to understand what the data is trying to say. So let's have a look at visualizing our data. One of the most important tutorials in this whole course, visualizing data. Now we've described the data, we've started to get behind the story, but an even more powerful way of exploring a new data set before you do your statistical analysis is to visualize the data. You get so many reports in scientific journals and it's full of plots and figures. It really conveys so much information. It's such a nice way for human beings to consume information, and it's one of the most important things you can do when you start exploring your data. So there is so much that I can show you inside of plotting your data. I'm going to call it plotting your data. Inside of Python also we have so many plotting libraries. The most important one, the oldest one I suppose, is the matplotlib library, sort of a MATLAB type of library, and creates beautiful plots. There's Seaborn, which builds on top of matplotlib, and that gives you more statistical type of plots, which is important. There's bouquet plots, and so many different libraries. My all-time favorite though is the Plotly library. And the reason why I choose the Plotly library is it's so expressive, and it allows you to export your plots in a very interactive way to the web. So you can save these plots on a web page, and they are interactive. People can play with them, they can zoom into them, they can turn on and off certain things. It is an enormous library. You can look up Plotly on the web. They have a service where you can actually agnostically of a programming language play with Plotly online. You can sign up, you can pay some money, and there's lots more things you can do, but they have this interface with Python which is completely free of charge, and it allows you to plot Plotly plots right inside of your Jupyter Notebook. It really, for me, is the most beautiful of the plotting libraries, and that's why I've chosen it to show you here. It is my favorite, the one that I use all the time. We've opened our Jupyter Notebook. We're in our Biostatistics Fundamentals using Python folder, and inside of our desktop folder, and you'll see there's a new spreadsheet here, plotting.xlsx. Lives in the same folder as that I'm going to create this new notebook. New Python 3, new tab opens up, and I'm going to call this one visualizing data. Such an important thing to do. Rename, let's go. We're going to import a few packages. I'm going to import pandas as PD. Seen that before. We're going to import our old friend NumPy as NP, and for the sake of argument, just in case, let's import SciPy as SP. SciPy as SP. Let's do those. Import it in a flash. Now we've got to import Plotly. Now the way that we're going to do that is through the following, and I'm going to change tact in this part of the course. To create plots involves a lot of typing. The one thing about Plotly is it's completely expressive. You can change the minute details of a plot, really powerful, but that means there's a bit of typing involved, and I really don't want you to waste time in this course by watching me type, because I'm the world's worst typist. So I've got two monitors here in front of me, so I'm going to copy and paste a bit. I'm going to cheat. Make things easier. You can obviously you can pause, but at least you don't, which is much easier than having to fast forward while you watch me painfully type. So here we go. I'm going to say from plotly.offline, import the following. Import iplot and import init underscore notebook underscore mode. Those are the two things I'm going to import from this sub-library called offline, one of the sub-libraries inside of the plotly. And I'm going to import two functions. And I'm immediately going to call one of them, the init notebook mode. Initialize notebook mode. What that does, it allows the plots to be generated and displayed right here inside of this notebook that we are working in. So that's very important. Let's go and do that. The second thing that I want to do is import these high-level chart objects. Now you know what a scatter plot is, you know what a box plot is, you know what a histogram is, a bar chart. These are high-level plots, and Plotly has a lot of them, and it saves a bit of time and it saves a bit of typing if we just use them. So let's import these high-level charting objects, and this is the code that we are going to do. Import plotly.graphObjects, so graph underscore objs, again that's a sub-library inside of the Plotly library, therefore the dot. I'm not going to import anything specific from there. I'm going to import that whole sub-library. So I'm just going to say as GO, graph objects, short for graph objects. So now I can refer to all of them. There's another one I want to import, another sub-library, and that is the figure underscore factory, figure factory. And I'm going to import that as FF because we're going to use both Go and FF. We're going to use both graph objects and figure factory, those two sub-libraries inside of Plotly. If you have those, you've got them all. So let's just import the data frame here, pd.readExcel. You've seen this before, and it's the plotting that we have. Sanity check, df.head. Let's make it 2. Let's see what's inside of there. Oh, there seems to be cholesterol, SBP, systolic blood pressure, creatinine, BUN, blood urea, nitrogen. We just call it urea in my parts, but BUN, and then group and grade. So we have all of these variables inside of our data set. Remember, if we wanted to see how big our data set was, we could call df.shape, and we see we have 900 subjects in this simulated data set over the 6 variables that we see there. So let's start off with a scatter plot. The way that we construct this is to create a few computer variables. As I said, Plotly is very expressive, and it's going to take you a while to get used to this. There's also more than one way to go about doing things. So you might look up other people's code, you might look up Plotly itself, the documentation, and you're going to see different ways of going about this. Makes it difficult in the beginning, but once you get it, it just adds to the power of this library. So this is what we're going to do. Just by convention, we're going to start off with trace 0. Now the trace is the actual thing that lives inside of the figure. There's going to be this blank plot, and then you're going to put stuff on top of it. You're going to layer different things on top of it. And these are, we usually refer to these as traces. So I'm going to say go.scatter. Scatter, there we go, and you can see how many there are. There's actually scatter 3D, scatter carpet, scatter geo. There's so many. We're going to start with just a normal scatter plot. And remember, a scatter plot takes 2 numerical variables. We're going to have pairs of values from each patient, 2 numerical variables. So on the x-axis, I want df dot, let's put cholesterol. And on the y-axis, I just put after the comma, I put a carriage return, enter return, because I don't want this long line of code, and after a while it gets so confusing. So I like breaking these things up, and the notebook is quite kind in this way that it lines things up for me. Let's do the SBP, the systolic blood pressure. And now I've got to tell it what mode I want it to have. Don't worry about this now. Play along with me. You'll soon get used to what's going on here. So there's my trace, and I close my set of arguments, closing the closing parentheses. So on the x-axis, the patient's cholesterol. On the y-axis, that very same patient's SBP. And I want these to be, the mode to be markers. There's another one called lines. We're not worried about lines. We want this. Now I'm going to create a second variable called data, just by convention. And I'm going to, That's going to be a Python list. And I'm going to put all the traces in there. As I said, remember, I could plot more than one thing at one time, and those will all be traces, and I've got to just collect all of them in a list. So I've got that. And the last one is this iplot. Remember we imported iplot? There we go, we imported iplot there. Iplot means plot inside of this notebook. And here comes the dictionaries. Remember we spoke about dictionaries? They make their triumphant return here in plotting. You don't have to use dictionaries here. There's other ways to do it, but I love the dictionary way. So I'm going to say there is a key called data, and the value for that is my data argument. And it's got to be a colon. So the data, iplot takes data and it takes a layout. We'll get to layout very shortly. Those are the two things that you pass to iplot. And I'm passing them as a dictionary. And so the key is data and the value is data. And data holds a trace. And the trace is the scatter. It's weird. You'll get used to it and you'll soon understand why this is so powerful. Oh, and look at that. Isn't that a thing of beauty? I want to just stand still here for a moment and I want you to appreciate what's going on here. So let's bring my mouse over. As soon as I bring my mouse over, this little cursor appears and I can hover over each of these and look at that. At the bottom it says 204 and in blue there in the middle it says 111. So that means the X value was 204, the Y value was 111. So I can actually see in real time all of the values that make up each of these scatter plot dots. That's beautiful. Even more so, look at the stuff that we have up here. Download plot as PNG. So I can download it immediately. That saves it to my hard drive. It'll ask me where I want to save it. And if I'm writing a report, a paper report that I want to submit to a journal, I have a figure that I can, a file that is a photo file, like a JPEG but PNG, that I can just import into my Word document or whatever I'm using to write my report. I can edit it in Chart Studio, that's part of Plotly. If you go on the Plotly website, I can actually zoom in. So I can say, oh, look at that, I've zoomed in. I can pan around, so I can just move around this. Let's hit the pan button properly and I can pan around the data set. If I've lost myself, I can just go home. Let's do that panning again. I can pan around, look at different parts once I've zoomed in a little bit. Let's go back home. I can select with a lasso tool, you know, this part that I want to zoom in on. And now it concentrates on that for me. I can zoom in. Now I can pan again towards these that I have selected, and once I hover over a point again, it's going to show me that. I can go back. I can ask for these values to be listed quite together. Instead of showing them separately, it shows each value together. Or I can show them separately again, the data point values, and then I can go to the Plotly website, and this will open in the Plotly website where I can play with it even more. Isn't that just, that's mind-blowing as far as I'm concerned. Start playing with those buttons up there. It is absolutely fantastic and phenomenal. Now this is going to be a bit of a longer tutorial. I want to press ahead, and I want to add a little something. I want to change these markers. I might not like this tiny little blue ones. So once again, trace, let me stick to my convention by cheating and copying and pasting. There we go, copy and paste. So I've got trace 0 again. It's a scatter plot. On my x-axis is the cholesterol. On my y-axis is the BP. The mode is markers, but I'm bringing in a new one called marker. So the mode is markers, but I want to say something specifically about the marker, and what I pass to this marker argument is a dictionary. Remember, dictionaries go inside of square curly braces, and it's key value pairs. So one of the keys inside of the marker argument here is the size, and I want to pass the value 10 to it, and I also want to change the color. And the value part of this key value pair is this notation that we find here inside of square brackets. So it's also a string, and it says RGBA, that's red, green, and blue, and the A stands for the alpha level, transparency. So 255 on the red channel, 70 on the green channel, 0 on the blue channel, with an opacity of 0.5, so 50% opacified. It might look so weird the first time that you see this. I can remember the first time I saw this. I went, wow, do I have to do all of this? But yes, you do, because it gives you so much power. Data equals trace. There's a list there. And then I plot data. Let's have a look at what happens here. They are much bigger now. They're bigger than these blue dots were. They're orange in color, which is 255,70,0, and they're slightly transparent. And they've got an alpha level of 0.5. So play around with these two, size and color. Those are two arguments inside of this marker argument, and I passed it as a dictionary. That's a very easy way and consistent way of doing this. As I promised, this is a slightly longer tutorial. I want to press ahead, and I want to show you eventually how we get two sets of data, two traces on this same blank plot. This white thing at the back is our plot, and what we plot on top of it are the traces. So let's have a look at this one. So I've got two traces. We said trace 0 and trace 1. So this is, one way to go about it. You could say trace 1 and trace 2 if you wanted to, but this is Python. We start counting at 0. So when I name my variables, I also start at 0. It's just one of those things. So the first one will be go.scatter. And remember, we worked with data before. You should know what this top line of code is. I'm going to say df, and I'm going to reference the df.group. And in this instance, I used this long notation instead of the dot group. Only the ones that are A, and inside of that, we do cholesterol. And that's going to be on my x-axis. So the cholesterol of only the A patients, and on the y, the systolic blood pressure of only the A patients. The mode is still markers. The marker is going to be of size 10, and it's still going to be this orange color. But now I'm going to give it a name, a new argument that you can see here, and it's going to be group A. Trace 1 is exactly the same, other than the fact that I'm only selecting the B patients, patients with B in their group variable. Same cholesterol versus SBP, same mode, same markers, except a different color. 0 red, 190 green, 255 blue, and 0.5, and I'm going to give it a name, group B. My data is now going to be a list of two things on top of this white blank plot, trace 0 and trace 1, and my I plot is still this key value pair. Let's plot that. And now we have two sets of data, and we see this nice little information on the right hand side. We see group A and group B, and they're different colors as we colored them, and those patients are now separated. And as I hover over these, you can see for the same, what do we plot on the bottom, the cholesterol. For the same cholesterol, there were two patients there with different systolic blood pressures, one with 132 and one with 136. Now we are so zoomed out, it's impossible to see these. But you can get all that information more beautifully, though, as look at this. I can hover over this on the right hand side and click on A, or click on B. Now they're all gone. So let me just look at the A's, and now it shows me only the A's. I can click on it again, click on the B's, only show me the B's. Oh, that is phenomenal. That is absolutely phenomenal. Okay, let's push through. There's no title to my plot, and there is definitely no access labels. I can fix that in one fell swoop. I'm going to copy my second monitor, and I'm going to paste. Isn't that lovely? Look how quickly I typed. So that I have trace 0 and trace 1 exactly the same. My data still holds the list of my traces, but now I bring in a new computer variable called layout. You can call it whatever you want. I call it layout. And this looks a bit messy, but it's not. It is a dictionary. And key value pairs. The first key value pair is title and a title. The second one is x-axis, and its value is actually another dictionary. We've seen this before, nothing new. Go watch the lecture again, the tutorial again, at least on the dictionaries. and the y-axis has a dictionary as its value as well. So title, and I've chosen a title, correlation between serum cholesterol and systolic blood pressure. My x-axis has a title, and the title is serum cholesterol, comma, another key value pair. There's something called zero line. Sometimes Plotly does this heavy black line at the across your axis, and I personally don't like it. You might like it. I put false there. I don't want it to be there. And on my y-axis, I have title systolic blood pressure, and my zero line is false as well. Now for the iPlot, it's data and data, and layout as a dictionary. Let's run this and have a look. Beautiful. Now I have my title at the top. I have my x-axis title, my y-axis title, and everything else is still there. I can still play around with these, no problem whatsoever. Now this tutorial is getting really long, but we're not done with scatter plots. I'm using scatter plots to introduce all these things to you. It is overwhelming, but what you will find is this is going to sneak up on you. It won't take you long to get behind doing this, playing with it, making one or two little mistakes, figuring out very quickly how this works, and off you go. You'll be running and creating the most stunning plots. You know, none of your colleagues are going to have these beautiful plots, and you can even just export them to the web, import them into your read about Plotly. You can just import them into your own websites. You can use this to do presentations with, and your plots are just going to stand out so much with a little bit of effort. I'm going to stop here. We're going to carry on in the next section. So that was a long section. Let's carry on. Plotting is so important. We've got to pay attention. We've got to do a bit of due diligence here. Now it's beautiful that I have two numerical variables here, one against each other, and every dot comes from the same patient, that patient's cholesterol and blood pressure. Scatter plots are beautiful because I can actually bring in a third variable into all of this. And there are two ways to go about this. I want to show you this first one. I'm going to copy and paste my text. Let's go through it. I've got trace 0 again. It's a scatter plot. On the x-axis is the cholesterol level. On the y-axis, the systolic blood pressure. The mode is still a markers, but my marker now is going to be slightly different. I'm going to have a size to it. It's part of the dictionary, key value pairs, size of 10. There's another argument called color. So it's going to be color, and it is going to take the blood urea nitrogen variable, its values as the color. You'll see in a moment what that's going to do. Color scale is Portland. Now you can look it up. There are a variety of color scales you can use. Portland is just one of my favorites. And show scale is 2. I'm going to show you what this looks like, and then we'll go back to what's going on here. The data is just a single trace, and then I'm going to plot that. We've seen that before. Now have a look at what happened here. Well, isn't that just a stunning plot? Anyway, so we've got the blood urea nitrogen here on this scale, and if we did a summary statistic on that, we would notice it goes from 10 up to just over 40, and it colors the value of that specific patient's blood urea nitrogen. So we take one patient, we now have that patient's cholesterol and systolic BP and their blood urea nitrogen all inside of the same dot. And the color scale is a visual thing. So your eye leads you to the fact it looks like, when the patients have a low cholesterol, they seem to have a low systolic blood pressure, and they seem to have a low blood urea nitrogen. Now this was simulated data, so it's, this is not realistic. But anyway, you can see this plot tells you a lot of things. Seems to be this correlation between all three of these variables. And that's why we have this color argument. The color argument says create this color scale for me, please, and scale it according to this third variable here. That's what the color means. Now I don't have to put color scale. Color scale, there's a default one, and Plotly will just use the default one, but I like Portland, and I like the scale to be shown here on the side so everyone can know what that is all about. Now there's another way, and instead of using color, I can actually use the size of the dots to indicate a third numerical variable for me, and that's actually called a bubble chart. It's called a bubble chart. So let's just have a look at it quickly. Let's just do creatinine this time. So let's do df.creatinine, and let's just describe it. Remember the describe function that gives us all this nice statistics all in one go. It seems as the mean was 1.7, the minimum was 0.1, and the maximum was 5.9. We've got to keep this in our mind, because what we want to do is to scale the size of this dot. And we can't use a scale of 0.1 until 5.9. Those are tiny little dots. So we just got to do something about this. And the way that there's many ways to solve this problem, but this is one way to solve the problem. So I've got the cholesterol and the BP from the same patients. Then, Plotly is going to line these up for me, pair by pair. Mode as markers. The marker has a size now. And the size is not going to be a fixed size. It's going to depend on that patient's creatinine level. But look at this creatinine level. It was actually a floating point value. I don't want the float. I want it to be rounded off, and I want it to round up. So mp.seal, we've seen that before for sealing. And multiply that by 10, please. So this patient here in the middle was 1.8. That will be rounded up to 2. Multiplied by 10 is 20. So the size of the marker for that patient will be 20, for instance. Let's run that and see how beautiful that is. So once again, I bring in this third numerical variable by the size of the dot. So certainly this patient here had a bigger, or let's say at least a higher creatinine level than a patient down here. So this patient had low cholesterol, low systolic blood pressure, and also a low creatinine. So another way, instead of a color scale, I can do that, which brings us to the ultimate way of expressing yourself with a scatter plot, and that's 4 numerical variables in one go. So let's highlight this, copy, and let's paste it properly. I just pasted the previous one. So I'm now going to bring in size, which is going to be the creatinine, and I'm going to bring in the color as the blood urea nitrogen. So I'm bringing in 2 things here. So together with the cholesterol and BP. So we'll have 4 variables per patient being expressed inside of one scatter plot. And that's just beautiful. I mean, that's a thing of beauty. Come on. So data is just a single trace, and my layout is going to be this whole long dictionary. We've seen it before. The title is going to be correlation between cholesterol and serum BP, with blood urea nitrogen as color and creatinine as size. The X title is going to be cholesterol, the 0 line being false. The Y-axis is going to have a title of systolic blood pressure and the 0 line being false. And I'm going to call the data in my data key and the layout value for my layout key. So let's run that. And just look at that. Is that not one of the most beautiful plots you've ever seen? Really, 4 sets of numerical variables inside of a single scatter plot. And that is just fantastic. With the added bonus that this is all interactive. In other words, I can save it as a file to my computer. I can open it in Chart Studio inside of Plotly. I can just export it to Plotly there. I can zoom in. We can zoom in on the data, and now let's zoom in some more. And now that we've zoomed in, we can hit the pan key, and we can pan around this data. And if I hover over one, we're going to still see those values. It's just, for me, it's just this absolute thing of beauty, and that is why I choose Plotly as my plotting library above all the other equally excellent plotting libraries that are out there. But really, this is a favorite of mine. So that's it for scatter plots. I've abused it slightly to introduce all sorts of things, how to put in a title and how to put in X and Y axis titles, etc. You know these now, so the rest will go a bit quicker. I want to have a look next though at box plots. So box plots, it's one of the most common plots that you'll find published in the literature. Copy and paste, there we go, our first box plot. So trace 0, nothing new, go.box, so instead of go.scatter, one of the high-level graph objects is a box. And all I'm going to say is on the y-axis, do for me the blood urea nitrogen. So df.bun. Smart enough to extract the values. I don't have to put dot values. Data is a list of just the trace, and I'm going to plot that. Let's have a look at that. A big, fat old, wide old, I should say, box plot there. And we can see If we hover over that, we see the median, we see the quartiles, first and third quartile, we see the upper and lower fence, we see the minimum and maximum, and it takes 1.5 times the interquartile range over and above to calculate for us where it thinks possible outliers would be. So in short, a little box plot. But now we want to be more clever about it. So let's put on the x-axis two things. Let me show you. So I'm going to say now not just the y-axis. The y-axis, remember, is taking the blood urea and nitrogen, but on the x-axis, take df.group. And once again, Plotly is clever enough to go down the group and notice what the unique values in the sample space is of this variable group. And it's going to create separate little box plots for whatever it finds there. And what it finds, it's going to group those patients together and individually look at those blood urea nitrogens. Let's have a look. So that's a minimum of code. I mean, I didn't have to do all of this extraction to say, group equals A and equals B. Plotly was smart enough to do this all for me. Another reason to love it. Now, I could extract it myself by hand, and there's some instance that we're going to do that, but I just wanted to show you this. So now it found A and B. It took blood urea nitrogen only from the A's, only from the B's, and now we can start looking at this. Well, it seems as if the median was 26 there and 26 on this side, so that, that's kind of equal to each other, and we can start getting some sense of what is going on here. Let me just show you something. Some people don't like these vertical plots. Some like horizontal plots, and the way to go about that is just to say x equals df bun. So it's just going to be the single one. I just wanted to show you that. So just this little single one is just going to do a horizontal plot. Instead of here we said y equals, now we're going to say x equals. So just play around with that. Some people like the horizontal plots. So I just want to show you that. What I like to do sometimes is just to display all the data points themselves. Have a look at this. So I have got a box. On the x-axis is the different groups that it finds. On the y-axis, the BUN. The box points is a new argument you haven't seen before, and I'm passing to that the argument all. The jitter, you'll see in a moment what that is, and point position, point pos, another one. Let's have a look. Best thing is to have a look at what happens here. And what it's doing, it's actually plotting all this, but if it plotted it all in one line, there'll be so many on top of each other, it doesn't make much sense, hence the jitter. So a jitter of 0.3 means it's just randomly plotting them left, right, left, right, left, right, left, right, and further left and further right, then just a straight line up and down. And point pos negative 1.5, it's minus 1.5 units to the left, minus to the left of the actual trace, which is the actual box plot. So that's one neat thing to do. I sometimes like to do that just to introduce all of the actual data values that we have. One thing I want to show you as well, and that is just to add the mean and the standard deviation to this. So exactly the same everything, but I've introduced a new one called box mean, and I'm setting that to SD. And that means it's going to plot the standard deviation and the mean actually. Let's have a look at that. And that's what it does for me. On the second one, you can see the dotted line is actually slightly different. So the median, the mean is slightly different there. Here they're almost exactly the same. You see 25.97 and 26. And here they're slightly different, 26 for the medium and 26.3 about for the mean. And you can see the sigma there, the standard deviation, which is the top and the bottom of these where they intersect here. So that really adds an extra bit of value there to your box plots, just to be able to have these mean and standard deviations showing up again. So in short, that's what I wanted to show you about box plots. Really nice things to do, and I want you to explore with them, create different traces, and that's a good thing to do. And if you do different traces, then extract the A patients and the B patients separately and put them each on their own trace and see how that is different from what we've just done here, this automatic way of just getting our categorical variables on the x-axis. Next up, histograms. As promised, we get to histograms. Now, histogram takes a numerical variable on the x-axis and it divides it up into little bits. Remember how we had lin space for NumPy, when we looked at collections, we just divided up into equal little sections. So it takes a numerical variable between the minimum and the maximum value, chops it up into equal little bits, and you can specify those bits, and those are called bins. And it counts how many values are inside of each of those little bins. So let's have a look at this copy and paste quickly. There we go, magical typing. This time it's go.histogram. And on the x-axis, I'm putting a numerical variable, df.sbp. Trace, data is the same, I plot, everything is there, and this is what it does. So it goes from the minimum to the maximum, and it creates these little bins, and it counts how many there are. And it's actually lovely because if I hover over it, it says that this bin is SBP from 110 to 114, and it counts that there are 86 patients who had a blood pressure between 110 and 114. 115 to 119. So it looks like it's doing this in bins of values of 5. There were 61 patients in, let's say, 135 to 139. There were 55 patients, and way out here, 2 patients between 220 and 224. So that's quite good. And you see the counts here on the left-hand side. Perhaps sometimes more common to have a normalized, what's called a normalized histogram. So we can have this frequency distribution. And I just introduced this by saying hist norm equals probability. It's a new argument there. And when we do that, instead of the counts here, we see what fraction of the total of the 900 patients that were in there actually had that. So if we look at patients between 110 and 114 by hovering over that, it seems that about 0.096, almost 10% of patients were in that bracket of 110 to 114 in that bin. And as it goes out, patients with a blood pressure of between 165 and 169, there was only about 2% of patients fell in there. And if you sum all of this up, it's got to be 100%. So this is a frequency distribution, and you see the percentages here, the fractions on the side. That's a normalized histogram as opposed to the counts, the absolute counts. So all it does actually is just takes the count and divides by how many there are. It's as simple as that. But this is the base of inferential statistics because it's p-values. What was the probability of being way out here, less than 0.03 was the probability of finding a blood pressure of between 220 and 225. I can say what was the probability of finding, in this data set, a blood pressure of 180 or more, and that means I've got to add all of these little probabilities here, and that will be the p-value of finding a blood pressure larger than 180. So this is quite an important thing in statistics. Okay, let's just specify the bin size. I might not like that bin size. I might like to do that myself. And there we go. I'm going to do the X bins. I'm still doing hist norm as probability, but I'm introducing X bins. And I'm going to say start at the minimum, the df.sbp.min, end at the maximum, and make 20 of those. Please, so it's almost like linspace. So let's see what happens there. So it's going to do that, and you can see it's these weird cutoffs, 113 to 132, 133 to 152, but still counting then the probabilities of all of those are falling inside of there. But that's just me being very expressive here in the way that I want those to be done. Let's just change this, or let's just do something a bit different. Let's cut and paste this one, or copy and paste. There we go. I have this time X bin start at 0 and end at 250, and now make 20 of those. And now you see the way that I've selected it. I've just figured that out as I sat and developed this, just to get these a little bit better. So it goes from 100 to 120, so 100 to 119, 120 to 139, just to give a better spread there and make things a bit easier. Now, I think what I want to do is just to show you how to overlay I'm going to do two different histograms on the same blank plot. And I'm going to do that in a way that you haven't seen before. Just to introduce it here, because I want you to have a whole arsenal of tools. I'm actually going to create 2 whole new data frames. So I'm going to split it in 2, but I'm going to split it permanently. I mean, the DF is still going to exist, but I'm going to create 2 new spaces in memory to hold 2 new sub data frames. So I'm going to call one _A and one _B, call them what you like. and one holds the whole data frame, but only if the group equals A, and the other one if group equals B. So I've got two, I'm not specifying them inside of anything else. I'm actually physically creating two new data frames out of the original DF. And that would be one way to go about solving this problem of getting more than one histogram on the same plot. So now I've got go.histogram, my x-axis, I've got the A, this new data set, SBP, and I know that it's only going to have BPs from the patients in group A, and this one is only going to have from group B, and I'm actually putting the naming group A and the name group B, and it's going to plot, it's going to stack them from back to front. So the one in the front, I'm giving it a bit of opacity. So I'm going to say opacity equals 0.6 to the front one, the second one being listed here in the data. I've listed it second, so it's going to go in front of trace 0, and I'm giving a bit of opacity so it shines through, so you can actually see the group A patients in the back. So this whole layout I'm going to do, a distribution of systolic blood pressure of groups A and B, and I'm going to put the title systolic blood pressure on the x-axis and the counts on the y-axis. These are counts. I'm not doing this probability hist norm there. And the rest is all familiar to you now. Let's run that, and you can see the two overlays. Once again, I can make them all disappear, and I can say, well, show me only the A's, show me only the B's. Oh, that's so beautiful. I love that so much. And I've plotted this B in front of, and I've given it some opacity, because if I didn't, you'd see this orange line here, for instance. You wouldn't see the blue behind it. So I've given it some opacity so that it just shines through. So the shining through is one way to get rid of it. The other way, to show two data sets like this is to just use a stacked histogram. So let me copy and paste here, and everything the same, X in the group, B in group. I don't have to do an opacity anymore, because I've got on my layout a new key value pair here, bar mode is stack. So if I run that, it actually stacks them on top of each other, which is, I don't really like it, because you have to sort of do the subtraction in your head if you were to just look at the values, because now you've got to look at the top of that orange and the bottom and subtract it from what you think it was to get that. But this is Plotly. I don't have to do it, because if I just hover over it, it's going to show me the group A was 35 and the group B in that instance was 14. I love Plotly. If I used one of the other plotting libraries, I would have had to do a lot more work just to get this. It is absolutely beautiful. The cumulative histogram is one last one that I want to show you here when it comes to histograms. Let's have a look at that. And that is something that goes inside of the histogram function here, and I'm going to say cumulative enabled equals true. So I'm actually passing this key value pair in a dictionary to cumulative, and if we do that, all it's going to do is just going to add whatever is inside of there to the previous one, to the previous one, to the previous one, and eventually you're going to get to 100%. All of the 900 patients are in that last one. So that's just the cumulative, and that's where a cumulative density function comes in if you really are calculating the p-values. Don't worry about that now, but there is your cumulative distribution, your cumulative histogram. In the next section, we're going to look at something that's not used too often, but I wanted to show it to you, and those are called dot plots. So the dot plot, it's a slightly awkward plot. I want to show it to you though, because I do use it and I think it is helpful. Now we've created this two separate data frames, the A and B one, and I want to use that very quickly. Do the following for me. It's a.grade. So we're just going to look at the grade, and we're going to use the unique function. The unique function. So it's going to go down, just the A data frame, go down grade and find the sample space. And it says I found 4, 3, 2, and 1. And that's in the reverse order. And that is just as it finds them, as it goes down. And that's not the way that you want it. You actually want it in a proper order. And every data set is going to be different, and that's just the order in which the first and the second and the third and the fourth patient is just how it found it. Now, I don't actually need a NumPy array. What I need is a list. So have a look at this. If I say a.grade, let's do that properly, a.grade, and I say unique, and I say to list, that is going to actually create a NumPy list. So we've gone from a Python list. So we've gone from a NumPy array to a Python list, and I actually want a list. The last thing I need to do is I've actually got to sort this list. So have a look at this. So I'm going to say np.sort. So np.sort for me, and what I want you to sort is the following: a.grade and the unique values. So sort that for me, and when you are done outside of this, so all of this here was the argument for the sort function, and when you are done there sorting your NumPy array, please pass it out as a Python list. And now eventually I'm going to get 1, 2, 3, 4. So no matter what the scrambled order was initially, this is the unfortunately what you have to go through, or it's one way that you have to go through to get this sorted. Now, what I want to do is the next thing. I'm going to say a.groupby, and eventually we are going to get to the plot. Just bear with me. I'm going to say group by grade. Now, group by, it's going to take this A and it's going to find all the unique values in grade, which we've seen is 1, 2, 3, 4. And then I want to take the cholesterol, so dot cholesterol, there we go, and I want the mean of those. Because this is built inside of pandas here, I am going to get them in order, 1, 2, 3, 4. And I see the mean. So it's taking my A data frame, it's grouping them by whatever it finds in the grade, and then takes the cholesterol of the corresponding grades and giving me the mean of all of these. Once again, that's not really what I'm interested in, so I'm going to go copy, and I'm going to go paste. I'm interested in it being a list. I'm interested in it being a list. Now I'm just going to get that value. Note though that the order is still correct. It's still 235.7, 235.7, 236.29, 236.29, the last one 233.99, 233.99. So the order is still there. So now I've got these two Python lists. I've got my lists of values here, 1, 2, 3, 4, and I've got my lists of means here. That is what I wanted. I went through all of this on purpose because I want to show you what we can do with a dot plot. So let me copy and paste over here. Let's have a look. So I've got two traces, and on these two traces I've actually got exactly the same thing. I've got a.group.grade.cholesterol mean.toList, and I've got b.groupByGrade.cholesterol mean.toList. And you've seen up here now what it means. It's going to give me two of these lists of 1, 2, 3, 4 values for the group A dataset and the group B dataset. On the y-axis, exactly the same thing. It's np.sort a.grade unique, and I use the A again because my dataset is complete. The A and the B is going to have exactly the same unique ones, but just to be pedantic about it, let's put the B in there. The mode is markers. I'm going to give the color instead of RGBA. I'm just going to use one of the standard colors called orange, and here I'm going to use one of the standard colors called deep sky blue. And because this was not go.scatter or anything, I'm actually see all of this. It's all a dictionary and all a dictionary, and now I put type being scatter, type being scatter. So yet another way to go about that little problem. Trace 0, trace 1, my titles, everything else the same. Let's have a look eventually what a dot plot is. So I've got my two groups here, the trace 0 and trace 1. On my x-axis, I've got the cholesterol, and on my y-axis here, I've got the grade. So it extracted the list of grades that we had here in a very neat order, and there they are now in the neat order, and it extracts these 4 values here for the mean of each of these, and I'm just actually plotting that. So you can see the cholesterol mean of group A and group B, of group A and group B for grade 2, group A and group B for grade 3, group A and group B for grade 4. So that is a dot plot. I'm mixing these categories up with some statistics, something like the mean. I could have also put the standard deviation or something else. So slightly awkward plot and a bit of work to do, but there might be instances that you need this and you want to express things in this way. Use it, don't use it, up to you. The next one is the bar chart. So let's look at bar charts or bar plots. Now they are different from histograms, where a histogram had a numerical variable on the x-axis. Now we're going to have a categorical variable, and we're just going to count how many of those categorical variables there are. So remember, let's just go back to our original data frame. So df dot, let's just do group, the group this time, and remember dot value counts. Value counts, it's going to count how many of each of the unique values in the sample space that we have. So 516A and 384Bs. Now one way I can go about that is not let Plotly figure this all out for me, but do it absolutely by hand. So I'm going to say go.bar, so bar is the high level chart name, X is, I'm passing it a list, A and B, and Y is 516384, which I've just manually copied from there. So that is one way of doing it, just doing it absolutely manually, and we can see the A and the B there. Not very exciting. I don't find bar charts very exciting. Anyway, you see this dark black line there? That's why I put that 0 line false as a key value pair in the layout. That's why I do it. You see this black line. I don't like it. You might like that black line. One problem that you might have come across is if you have very long names, A and B is very short, so I've done something here. I've said this is the value for group A instead of just A, and the second value is this is the value of group B, so that's going to be plotted at the bottom here, and that might be too long, it might stretch over, and then the two titles actually are printed over each other, and that's very ugly. And one way to go about that is I'm going to use an x-axis key value pair here. In my layout, x-axis is the key, the value is actually a dictionary, and that takes key value pairs, the title being groups, and the title angle being -20. So it's actually going to put a little bit of an angle to that. I wanted to show you, you can do that at any time. So that's a -20-degree angle there, and what happens there then, if you had to have a lot of these, and these sentences were quite long, these names, you can angle it so that they don't go over each other. Now, that was a manual way of doing this. I want to show you more of a Python stroke NumPy stroke pandas way of going about this. So we've seen df.group.value counts. It was 516 in A, and I think there was 384 in B. And remember that I could do that, and I can just express that as a list. And I can also do the unique toList for A and B, so that I have those completely inside of a Pythonic way of doing these. So my X is going to be df.group.unique.toList and df.group.value.counts. I'm not going to do the AB, because if you go through that, you'll see that it is in this data set it's AB, but remember how to do that by the sort, by going through NumPy and sort. And so instead of me having to copy the values, I can just write code, and which will hard code, instead of hard coding this, I can just do it this way. Now, let's introduce just more than one thing here. So I'm going to do a copy and paste. So just, that's not very informative. It's just two categories. So yeah, I'm going to do two traces. I am going to do the group A patients on one side, and then the 4 grades as this unique list, and the same for B. I'm going to run through all of that. You can go through the code, and now you can see that we now have group A and group B totally separately from each other, and I can plot either one separately, or I can plot them all combined. I want you to perhaps find something slightly wrong with this, because what I didn't do here, I didn't go through this process perhaps of making sure that my sort was completely properly there. So I'm going to leave that up to you as a bit of homework to check whether that was done properly. So these are the fundamental plots I wanted you to be aware of. These are the plots that you're going to make use of most of the time in biostatistics. There are so many others that you can look at. Have a look at the Plotly site, perhaps learn about the others. Play with these, play with the data. Together with descriptive statistics, this is what you start off with before you do any statistical analysis. Do this, play with it, start allowing the data to tell you the story that it wants to tell you. by doing descriptive statistics and doing the plotting. While the graph object module inside of Plotly is a fantastic library, it's sometimes difficult, or at least it takes a little bit of more work to work with a data frame, a pandas data frame. Fortunately, we have another module called Plotly Express, and we can import that and very easily work with pandas data frames. We can just reference those data frames and the columns that come in the data frames. It's also very short syntax. So if you're wanting to explore your data, specifically at the beginning when you're just starting to look at your data, use Plotly Express. There's lots of arguments built into the Plotly Express plots though, so you can just change those plots whichever way you like. We're going to open a notebook and we're going to explore some of the plots available in Plotly Express. Here we are in the notebook, and you see my first cell there. It's just going to execute a cascading style sheet file, which will also be available to you if it lives in the same folder as this notebook on your computer, on your hard drive. It'll execute that cascading style sheet, and that just allows us to change the look and feel of the notebook. So let's execute that, and you can see we have this orange coloring and blue and orange title coloring. So Plotly Express. So in this notebook we're really going to express this library in Plotly. It used to be a separate library, but it's now incorporated into Plotly. And the beauty of it all is that we can just take a normal data frame, a pandas data frame, and incorporate that data frame or reference that data frame right inside the plots that we're going to do, and then just reference directly the different columns that we are interested in. So to do that, we're going to use the import statement, import plotly.express as px, and then I'm going to also import plotly.io as pio. One of the things about plotly.io, or input-output, is the fact that we can style our plots. And there are 5 or 6 different styles that you can choose from, and none here. So pio.templates.default, I'm setting that equal to none, and none is actually not none. It is a theme for plots. So let's execute this. And then we're also going to import NumPy, and we're going to import pandas as we've always done. The file that we're going to work with here is participants.csv. That contains all the data that we're going to use just to create our plots in using Plotly Express. And there we can see the first 5 rows of data. We've kept it very simple. There's a code column, feature 1, feature 2, feature 3 up till feature 6. There's a group column, there's a target 1 and target 2 column. So we're just keeping things nice and neat. And you can play around with these, use them to plot, and none of them refer to a specific variable. The features seem to be here just to be continuous numerical variables. The target 1 is a continuous numerical variable, group is a categorical variable, and so is the target and code. So the first type of plot that we're going to deal with is the scatter plot. Scatter plot obviously very good for comparing continuous numerical variables, and that is how we set up to look for correlation and how to set up linear regression models. So on both axes we're going to have a continuous numerical variable, and for each participant, each subject in our data, if it is presented very neatly as a row in our spreadsheet as it is here, then every point has or is a representation of 2 continuous numerical variables for that specific individual. So the function that we're going to use here is the scatter function. So because we imported Plotly Express as px, we can use that namespace abbreviation, px.scatter. Scatter is our function, and there we go, we passed the data frame to it. And because we imported this pandas data frame as the computer variable df, as you can see there, we just passed df, comma, what of the continuous variables do we want on the x-axis and which ones do we want on the y-axis. So I only need to mention the column name there, nothing else. So let's run this. And there we go, we can see our plot, and this is the theme. The theme is a white background with this very light gray grid on top of it. And there you can see still Plotly. In other words, we can still move around, and if I hover over any of these markers, call them markers, you can see what the value is for that specific participant or subject. And that sample in our data set, that for feature 1 they had a value of 17.91 and for feature 2 22.7. And there seems to be this correlation, positive correlation between
these two variables. As feature 1 increases, so does feature 2. Now we are just plotting all the data points here for all our subjects, but we can also just split that up by the sample space elements of one of our categorical variables. So let's look at target 2. Remember that that was a categorical variable, and the .unique method will give us the sample space elements that was found in that column. So remember, if I just type df.target2, that creates a pandas series object for me, and from that we want the unique values in that series, in other words in that column, and we see there are 2 of them. So we can use the color argument, and if we set that color to this target 2, it's going to split up our data into 2 separate sets. And if we plot that now, we can see that we get all these values both for target 1 participants and target 2 participants. And as always, I can just click on these and then remove them, bring them back, remove them. So there we've removed 2, so we only see participants that had their target 2 variables set to or captured as Roman numeral 1. So it always makes Plotly such a nice feature to use, such a nice library to use. Remember, you can always export this specific image just as a PNG file. To add a title is quite easy. We see here px.scatter. We still have our data frame, our x variable, our y variable. Color is still going to be target 2, but now we just add a title. And the title, for the title at least, we just simply pass a string, and that contains the name of our, or the title at least, that we want to add. And now we can see a title correlation between feature 1 and feature 2, and it is still split up by this color argument here. The color, by what categorical variable do we want to split this data. Now I can also, instead of what you see, what we've done up till now, I've just used px.scatter, and right at the end you see I used the .show method. You needn't even use the .show method. You can remove that completely and it will still plot, no problem. But we can save our figure as a computer variable, or inside of a computer variable, and this time we're going to use the fig computer variable, and just doing what we've done before. But now I can start updating things that I want to add. So I can update the x-axis, and so I'm going to say fig.update, so the update underscore axis method for my fig object here, and the updates that we're going to do is title underscore text, and we set that to a string value. And then again, fig.update x-axis. This time we're going to do the title font, and there's lots of things we can change about the title font. So we're going to pass all these things as a dictionary. The size is 12 of that font, the family should be Courier, and the color should be gray. Instead of doing that all separately, I can do it all in one. So here we have fig.update underscore y-axis. So this is going to be a method for updating the text, or at least the axis label. And I'm stating here title underscore text as the string values for feature 2. And then the title font is a dict with size 12, family Courier, and color gray. So that's either way. And then in the end, I will have to say fig.show just to show up this figure. And now you can see in light gray with a very specific type of font and font size, I have axis labels for my x and my y axis. Now, instead of creating a specific object and then using methods to update those, I can do it all in one with this labels. If I just want to change the axis labels, I can just do that with the labels argument. So here we have px.scatter, and we have dx, again, just my x-axis, my y-axis, my color, and then labels here. Labels are passed or changed as a dictionary. So by default, what Plotly and Python is going to do, it's going to grab that column name, and sometimes we use underscores for variable names in our first row, our column headers, and that might look a bit ugly when we're trying to make a nice figure like this. So we can use a dictionary here. So we have a key value pair here, and the key is then the value in the data frame itself, the column header, and then the value would be what we want it to be. So we can do that for both of these axes, and that would be another way that we can just change the names of the axis here, the x and the y axis. Now it's not always easy from a scatter plot to get an idea of the distribution of the data. So along the x and the y axis we can add separate plots to help us out with that. So in this instance we've got our title, but if I scroll all the way over, I've got two new arguments here, marginal underscore x and marginal underscore y. So on the x-axis I want a histogram, please, and on the y-axis I want a box plot, a box and whisker plot. So let's see what that's going to do for us. So very beautifully here on the x-axis, now it's going to do it at the top of the x-axis, I see a lovely histogram of both of my groups, target 2 with values 1 and 2. I see for both of them, I see a distribution. Very nicely done there for feature 1. And then on the x-axis, I'm going to see that for feature 2. So this one is going to be all the way across. That's feature 2. And then the top here, that was going to be for feature 1. So we can see two different ways to visualize a distribution. And we would just put these on the margins. So by now, this plot really conveys an enormous amount of information. And it's absolutely fantastic. And it was a line of code, as you can see there. Again, I've saved this as a figure and then fig.show, but I needn't have done all of this. I could just say px.scatter, but if I wanted to refer to it again, of course it's safe just to save it as that. Now one thing that's missing from this, it's only going to show us distribution and correlation here, but what if we want to change this into a regression, a linear regression model? We want to add a trend line, a model. And one way we can do that is what we've put here at the end here, trend line equals OLS. It's going to use ordinary least squares, the method for determining the best fit lines. So if we execute that, we are going to see, it's going to take a while just to work out these two trend lines, and we can see the two trend lines there, and we can actually see quite a bit of information about that. We see the R squared values. There's the R squared value of 0.48, R squared also of 0.48 here. And we see the intercept there and the slope of those two lines. So a beautiful set of information, again from a single line of code. Now this can become a bit busy. Perhaps we want to split this up into two plots, and I'm going to use the facet column, facet underscore col in over here. There we go, facet underscore col, and I'm going to set that to target 2, which means it's going to break it up into two things on the same column. So now I have it separately for target 2 equals this group 2 and target 2 equals this group 1, and we see the data is now split up column wise, and I can also do it row wise with facet underscore row. While scatter plots are great for two numerical variables, I might want to bring in a third numerical variable, and there are two beautiful ways to do that. The first one is just for us to use a color chart. So I've got my trend line there, but I'm also going to bring in color. I'm going to use color, and instead of a categorical variable, I bring in my third numerical variable. Let's have a look at that. And now there's going to be a change in color as far as this third numerical variable is concerned. And of course, the other way to go about that is to use the size of these markers as a way to indicate my third numerical variable. So here we're going to say size equals feature 3, and then I can still group them by a categorical variable using the color argument. So if we look at that, now the size of these markers is indicative of that third categorical variable. If you want to know more about all the arguments that we can use, just hover inside of your parentheses, hold down Shift and hit Tab, hit it again, and now you can see a list of all the arguments that you can use, what the defaults are, and if you scroll further down, it actually just gives you more information about each of these arguments that you can use. Other than scatter plots, there are other ways that we can visualize numerical variables. One of those are a heat map. Now I'm going to show you px.density underscore heat map, and we're passing the data frame and our x and our y variables. So it's pretty much the same as we started the scatter plot. So let's have a look at this heat map. And there we go. what we can see here is the feature on the x-axis, and we've got little bins. So that'll be from 14 to 15, 15 to 16, 16 to 17. So all the cases that fall within there, which would also have between 16 and 18, you can see here, for feature 2, and how many there are of those sample cases that would fall within those bins. And the lighter the color here, and you can actually choose different styles for this color. The higher this goes, the count, it goes from blue up to yellow, and so we can see most people, or most participants or subjects, participants fall in this little section here. So they'll have a feature 1 value between 20 and 21, and a feature 2 value between 22 and 24. So it counts for us how many there are. Now from this, it looks like the further way we go, both for the x-axis and the y-axis, it gets fewer and fewer participants. So we get some idea of this distribution, but of course it'd be lovely just to add those marginal plots, and here we're going to add marginal plots for both feature 1 and feature 2. And so we've put histogram both on the marginal underscore x and in margin underscore y. So we can see here feature 1's distribution. There's a bit of a tail here, but it's almost normal, and the same goes for feature 2. And that gives us a much better idea of the distribution of the data as far as these heat maps are concerned. Now these heat maps are discrete. In other words, we are breaking the continuous numerical variable up into bins so that they become ordinal categorical. But of course we can keep things completely numerical by doing contour plots. So instead of what we had here, density heat map, which is going to be more discrete, we have density underscore contour. And if we run this, we see that, and I've used the facet column here so that we get by target 2 these two things separately. We see feature 1 versus feature 2 as this idea of this continuity. So if these continuous curves, as you would see on an elevation map as far as geography is concerned, so we can see how many cases fall within those parameters. Next up, the plots that really help us determine the distribution, and specifically comparing two groups or more groups to each other. So let's look at the unique elements, so the sample space elements of the group column. So df.group, remember that gives me the pandas series, or just that single column, and we want to know what unique elements they are, and it found A, B, and C as the sample space elements. So let's create a box plot. The data frame on our y-axis, we're going to have feature 1. That's the continuous numerical variable that we're interested in, but we're going to break it up into the 3 sample space elements of group, and we're going to put that on the x-axis. If you swap those around, of course you're going to get horizontal box and whisker plots, and they're my 3 box and whisker plots with a simple line of code there. Now we can also have a look at the specific values themselves by just looking at all the points. So I've got my df, I've got my y, I've got my x. Now I'm just say points, and I'm going to say all, and I'm bringing in a title, and the labels, once again, I'm going to use the dictionary, and the key value pair are the key, at least is the actual value that's in my data frame, and the value is what I would like to be on the plot. And now we can see we've got a title, we've got all our values there, and we've got different labels here as far as the axis labels are concerned. Now what about color? So we can use the color equals argument to set another categorical variable. So let's do this. So now we see that by target 2, or each of these, so for group A, group B, and group C, each of them have now been subdivided according to the sample space elements of the target variable. So a lot of information here. We've split this data up by 2 categorical variables, and we're displaying one of our continuous numerical variables there. And we do that by the x-axis. If we pass a categorical variable for the x-axis in the box plot, of course it's going to break it down into the sample space elements, but we can also break it down even further with the color argument. Then lastly, just histograms, a beautiful way to draw on the screen for some visualization of the distribution. And so that's this px.histogram, again passing my data frame I'm interested in feature 1, and I'm just going to break it up by the sample space elements in my target 2 variable, and I've added a lovely title there. So there we go, we've got our title and we see our histogram. By default though, we see a stacked histogram, so just be mindful of that. If we look at this, we see it goes up to nearly 100, but that doesn't mean this orange, my target 2 equals Roman numeral 1, goes is all the way up there. No, it starts counting at the bottom, so that it's very difficult to discern how many, if you just look at the plot, how many of our samples are in that little bin. So if you hover over it, at least you can see the count was 48 for 1 and 49 for 2. So remember, if you see it like this, that's a stacked histogram. So the overall height, the heights gives us an idea of the overall distribution for this feature 1 variable. If I set the bar mode argument to overlay though, we get something that we might be more interested in. So it's going to add a little bit of opacity so that these two are on top of each other, and we get an idea of what they both are, and it's not stacked. So just looking at these heights, you get a real idea of the counts inside of those bins. We can use the hist norm, because what we have here is count, how many values fall inside of those bins. We can also express that as something else. Here I'm going to express it as a percentage. I'm just going to say hist norm equals percent. And now what we see here, although it still says count there, it's the percentage. So what percentage of values for each of these classes for the target 2 variable, what percentage of values will fall in this little bin? And we see 10.8% and 10.1%. So that gives us, we can express this as a percentage of the total. And then second, last thing I want to show you is just that we can control the number of bins. So here I've set n bins equal to 10, and now I'm just going to get bin size bins here that are wide at the bottom. So this goes from 12 to 14, 14 to 16, so I can control how many bins I want, and we can see here this went from 16 to 16.49, and this one goes from 16.5 to 16.99. So it went up in increments of a half, but I can control that by just deciding how many bins there should be. And a neat thing, if we are dealing with statistics, is just to look at the cumulative frequency here. So we can set a histogram and we set cumulative equal to true, and then I've set the hist norm to percent again, and we can see how many are in each case, but it is cumulative, so that in the end I do get to 100% of the values, because it counts all the values before that. So that's a cumulative frequency distribution here. And that's a look at the Plotly Express library. All of these functions just have so much that you can do with them. Remember, just hover inside, hit Shift Tab, hold down the Shift, hit the tab twice, and you can get all the information. Also go on the Plotly website. It'll explain or show you at least some examples of what all of these arguments can do, and you can really change so much about these plots. Plotly Express is really the library that I use most often now. It's very quick to get a visual representation of your data, and we can code directly from our pandas data frame, which makes it absolutely useful.
The most common tests that you'll see in journals are called parametric tests. Those are student's t-test, ANOVA, that's analysis of variance, correlation, and those are all based on certain assumptions though. You cannot do those tests unless these assumptions are met, and that's very important for you to realize when you start doing your own data analysis. So in this section we're really going to dig deep into how to test your data before you do any statistical analysis. We are getting closer and closer to doing some real inferential statistics, some statistical analysis. We've explored our data through descriptive statistics, we've looked at it through visualization, and now we have to do some statistical tests. In a manner of speaking, there are two broad methods of statistical tests. One is called parametric tests and one is called non-parametric tests. Parametric tests are by far the most common. Those are your student's t-tests, your linear regression, the normal tests that you see most of the journals using for reporting, most authors using for reporting inside of their journal articles. So we're going to stick in this fundamentals course to parametric tests. Before you do a parametric test though, there are some assumptions on which these parametric test, students t-test, is based. And you've got to check whether the data that you have actually meet those assumptions. Otherwise, if you use a t-test or one of these, you are cheating. There's just no other way to put it. You have to show that the data meet the assumptions of, for the use at least, of parametric tests. And that's what I want to show you in this tutorial. You'll see a new data set here. It's called assumptions.xlsx, a spreadsheet file, Microsoft Excel spreadsheet called assumptions, inside of the same folder that we are working in, Biostatistics Fundamentals using Python. New Python file. There we go. Again, so that you don't have to watch me type, I'm going to copy and paste every now and again. So here goes the first one. Importing as normal. Import pandas as PD, import SciPy as SP. I'm doing my normal Plotly sub libraries. You see them there. And we're also going to import one of the other plotting libraries. I've spoken to you about them. That's the main one really in Python, the old one, matplotlib, and a sub package in that called pyplot. So it's matplotlib.pyplot, and I'm going to import that sub library or sub package of the matplotlib package as PLT. And then I'm going to use this, that's called a magix command. So it's percentage matplotlib in line. Matplotlib works in a slightly different way, and I've got to ask it really to print its plots inside of this notebook, and the way that we do that is matplotlib.inline. So let's run all of those. There we go. It's what we've done. Now the data set that we're going to use, as I said, is the assumptions spreadsheet file. So again, I'm just going to call it dfpd.readexcel and that assumptions, and we import that. Sanity check, let's just look at the head, make sure everything important and imported, and we can have a sneak peek here. It looks like there's a group categorical variable, there's an age, a CRP, and a white cell count. So those all seem to be numerical variables except for the group, which is a categorical variable. So there we go. Now the assumptions, the first most one that you have to check is this assumption of normality. What that says is the population from which your samples were taken. So you have a population, you take random samples, random subjects, random patients from that population. You take data point values for a variable. The data point values of that variable in the population has to have a normal distribution. That doesn't mean it has to really have a normal distribution in the sample that you have, because it's not gonna. Most of the time your sample is so small. But what you want some assurity that the population from which those samples were taken have this variable normally distributed. You can't do that though if you think about it, because you don't know this value in all of the population. Otherwise, you would have included all the population in your study, and that's impossible. No one's got the time or money to do that, unless the population of some very rare disease that you're working with, is quite small. But there are some things that we can do. Now, as I said, your data is not going to, your sample data is not going to be normally distributed, but if it is, it gives you some understanding of what is going on. And the first plot I want to show you, or the first way I want to show you, is a visual way. We're going to just show a histogram of the data itself, and that'll sort of give us an understanding of what's going on here. Now, we've done visualizing data. I think you've got a good grasp of that, and I hope you played around with that a bit. And if you looked on the website, you see there's a different kind of plot called a distribution plot. Now, we've imported figure factory as FF, and it's this FF, one of those plots that we're going to use. So you haven't seen this before, but it will make sense to you. I'm introducing a few different ways of doing it though, so let's just go through it. So instead of being trace 0, it all lives inside of one element, and this time I'm going to call it fig instead of trace. ff.create this plot. That is like we had go.box and go.scatter. Now we had ff.create this plot. And I want to pass it a few arguments. The first one is hist data, because a distribution plot does create a histogram. And instead of saying x equals, we actually say hist underscore data equals, but that's the same as hist. Instead of x equals, we have hist data equals. And what I want to pass to it is a df.age.values.toList. So I'm going to go down my age column, find all the values, but I'm going to express it as a Python list. But just look here, it lives inside of square brackets, so it's actually going to create a list inside of a list. That is because this create dist plot allows me to make more than one in the same. I don't have to do different traces. I can actually just list them inside of this one list. And the group labels, I am doing this by age, so I'm putting age there. If I had something else there, I would say comma, that other thing as well. And now fig layout. So remember before I created that as a dictionary, this is another way of doing it. And you can do it with the normal Go plots that we did before. So fig and then layout. I could also have said fig.layout, but don't worry about it. We do it this way. Dot update. So a whole different way of going about it, and I'm smiling as I'm talking to you here because it is confusing, I know it is, but there are more than one ways of doing things inside of Plotly, and I want to show you some of them. And I'm going to say title equals, so instead of this being a dictionary, I'm just updating this fig object here. So that's age distribution of all the patients, and I don't want to show a legend, so the legend is false. That's that little thing you see on the side. Because I've only got one thing here, I'm just showing the age, I'm not showing more than one thing. And then I plot this. So what do we have here? A histogram. So could you have just done a histogram? Of course, you didn't have to do this. I just wanted to show off a bit, showing off Plotly here. So it creates this, but it also creates this smooth, this density estimate here, this kernel density estimate. So it's making this nice little mathematical equation that draws this little line that gives you sort of an idea of the spread, the distribution of the ages in this. So instead of these Manhattan little towers here, Manhattan skyline towers, we actually see this representation in a mathematical function which draws this nice little line. And we could agree that it looks slightly normally distributed. There's a bit of bell shape to it. And what we have here at the bottom, that's called a rug plot, R-U-G, rug plot, and that is just the actual values itself. All the data points are on this little rug plot at the bottom. So that's one way and we'd agree it looks normal, and that's nothing. This doesn't tell us anything about the underlying population, but at least it tells us something about what we have here in front of us. Now I'm going to copy and paste this next one because just for you to peruse, so pause and have a quick look at that. So what I'm creating here is one element, which is in the end going to be a Python list, which lives inside of a bigger list once again. But this time I'm not just doing the df.age, I'm actually just looking at all the group 1 patients. Now we haven't looked at this data set, but naughty, we should have. There's group 1 and 2, so do df.group.value counts, so you can see what is in there. Otherwise everything is exactly the same. So now we're only looking at the group 1 patients, and we also actually have to do that for the group 2 patients, because if we want to do a student's t-test to see if there's a statistically significant difference in age between group 1 and group 2 patients, I've got to check that both of them satisfy the assumptions individually. They've got to satisfy these assumptions. So let's do that. Let me just clear this up. And let's just copy and paste this, copy and paste, and now we've got the group 2 patients here. Let's run that, and we see, yeah, they also sort of look like there's a normal distribution to that. Now for argument's sake, I want to show you the distribution of CRP. Again, you can just do the histogram, you needn't do this create this plot, but I like this nice little kernel density estimate graph. Now look at this. There's no normal distribution here in the CRP levels. This looks much more like a chi-square distribution to me. Anyway, so this is not bell-shaped. So just by eyeballing this, I would not say that we can use a normal parametric test to compare the CRP between two groups. I wouldn't say, if I want to do a statistical test to see if there's a statistically significant difference in the CRP between group 1 and group 2 patients here, I could not use a t-test. This is not normally distributed. This is way off. We can't do that. Now, Again, I said you have to do these individually. You have to then look, if you wanted to compare group 1 and group 2 patients, you have to do them separately. And that's why we have this list inside of a list. Now see, I've got this one Python list, but I've also got the second Python list there. And then this first one I'm asking for group 1 and the second one for group 2 patients, the CRP. So my group labels now is also a list of 2 different things. And now I'm not saying legend is false this time, I'm leaving that out. I'm just updating with a title. And if I do that, I can get the CRP for both of these sets of patients. And again, I can only look at the group 2 or the group 1, but I want to look at both of them. And really, neither of them follow a normal distribution, and I would be very uncomfortable doing a student's t-test there. So that is one way of doing it. Just this eyeball test. Now, the second lot of visual ways to look at these assumptions is also, it's also visual, but it's a bit more statistical. Let me show you. It's called a QQ plot. It stands for quantile. It is going to plot every point against its quantile. And it's one of the SciPy's, Scientific Python's functions. So it's scipy.stats.prop plot, a probability plot. And I'm passing a list to it again. So it's df group is 1, age 2 list. It's got 3 arguments. It's got a dist argument as well and a plot argument. Dist is norm. So I want to test whether this comes from a normal distribution. Just memorize how this is done. And plot is PLT. Remember, PLT was matplotlib that we imported. So I've got to do something before just to make it a bit bigger because these plots tend to be a bit small. So I'm going to say plt.figure, and it has an argument called fig size, and you pass the width and height. So I'm doing a 16:9 aspect ratio there. Have a look at that code. It's not difficult. It makes sense. This is the normal line here, and I see age, and age follows this normal line. So I'm pretty sure that this comes from a population in which these values are normally distributed, because this is plotting the value against their theoretical quantile. And that's a very good way of eyeballing, perhaps better than this, eyeballing whether you can use, whether this assumption of normality is really met. So let's just do this for CRP. Let me copy and paste that for CRP. Let's do that. And again, my stats.prop plot, I'm passing this list to it. I'm saying it's a normal distribution. And lo and behold, you can agree, that looks nothing like that. So these are not plots that make it into your publication, into your report. This is a visual a cue to you to say this assumption is not met. I better not use students' t-test. So those are the visual ways. Next up, more importantly, we're going to do statistical tests to see if this assumption of normality is met. So let's look at these all-important, the statistical tests that you can do for this assumption of normality. Now, there are quite a few of them, but there's one that stands out, and that's the one that we use in my research group, and that's called the Shapiro-Wilk test. So not much to it. Please remember the following. Do your visual ones first, sort of get an idea. You can do your histogram or the more fancy distribution plot that I showed you. Stick with a histogram if you want. Do your QQ plots, which is from the SciPy library, .stats.prop plot. Remember that. But then do your Shapiro-Wilk test. It's also from the SciPy .stats sublibrary. So the way that we're going to pass that is say scipy.stats.shapiro. So Shapiro is short for Shapiro-Wilk test. And I'm going to say df.age. So the first thing I'm looking at here is the age of the whole data set. Shift enter, shift return, and I get 2 values back. The first value there is the Shapiro-Wilk test statistic, 0.99, and then the p-value for that test statistic. So that's 0.06. Now, the way that the null hypothesis works for the Shapiro-Wilk test is to say that, yes, this does come from a population in which, underlying population in which that variable is normally distributed. That's the null hypothesis. If the p-value is less than your chosen alpha value, which normally for us is 0.05, then no, it did not come from. So this is 0.06, it's close, but it's there, so I cannot reject my null hypothesis. So I would say that this age, as a whole, does come from a population in which age is normally distributed. That means I'm still meeting my assumption for the use of parametric test. But remember what I said, we have to do this for each individual group if I'm going to do two different groups, if I'm going to compare two different groups. So we didn't do that before, but let's do that now. So it is dot group. Let's just do value counts, just to make sure we've got group 1 and 2 patients here. There's 251 in group 1, 249 in group 2. So I might want to do this. I might want to say, is there statistically significant difference in age between patients in group 1 and patients in group 2? Now, we might have explored this. We might have done some descriptive statistics on that. We might have done some box plots on that. And now we want to compare them. And first of all, though, let's make sure for each group that this assumption is met. So I'm going to say df, and then I'm going to say df.group for the first group equals 1. And then from that, I want the age. So I want the age just from the group 1. I could say to list as well, just to make sure this is a list. But I'm going to wrap all of this. So I'm selecting all of that, putting my little open parenthesis that will put the closing one there as well, because I want all of this to live in a scipy.stats.shapiro function. So I'm doing scipy.stats.shapiro. I'm only looking at the age of group 1 patients. And there I find a p-value of 0.07. So again, I cannot reject my null hypothesis. Age is seems to be from a population in which I cannot reject that null hypothesis. So I've got to keep that. And then let me copy and paste, because what we also want to do is just to go for our, I didn't do the SP, let me do SP, stats.shapiro, and this time I'm going to look at the age of my group 2 patients, and my test statistic here is 0.995, and that's a p-value of 0.756, so really still not rejecting. So I could really, as far as we stand now, say that I can use a t-test to compare the mean age of these two groups of patients. So that would be your statistical test as far as assumptions are concerned. So your visual showed you 2 visual ways, and now the statistical way. There are other tests called Markov-Smirnov and a few others. This is the one in this fundamentals course I want you to know about. It gives you a test statistic and a p-value. If that p-value is less than 0.05, you reject. Well, let's just do that, because we know, remember that this looked odd. So let's just do that. We saw CRP, we saw that that was a bit abnormal. So let's just have a look at that. scipy.stats.shapiro, I'm going to do df group equals 1, so only the ones. crp.toList, and we're going to do Shapiro work on that. And look at that, 9.4 times 10 to the power negative 14. That's way less than 0.01. So we reject the null hypothesis. We accept the alternate hypothesis, which states for the Shapiro work test that this is not from a population in which that variable is normally distributed. And therefore, I cannot compare the CRP between group 1 and group 2 using a parametric test such as student's t-test. It's failed. So you've got to do each individual one, and if either of them fail for group 1 or group 2, or how many other groups, if you had group 3 and you're going to do analysis of variance, you can't do a parametric test. You'll have to use one of the non-parametric versions. Please look at these assumptions visually and statistically. So let's carry on. We've done normality now. Let's carry on looking at the next assumption, which is the homogeneity of variance. What that states, homogeneity, fancy word, what that means is I'm going to take my 2 groups and I'm going to look at the variance of that variable, and they've got to be sort of the same. So let's just do that. Let's just check up on this. I'm going to say df, and let's say df.group equals 1, and I want the age and I want the variance. Let's have a look at that, and the variance is 111. Let's copy that and paste it there, and this time I want group 2, and I see the variance there is 103. That's quite close. I think that assumption is sort of met, but there's a statistical test for this, and that's called Levine's test. So, in being a bit lazy, let's copy and paste that one in. Let me show you what that looks like. So it's scipy.stats.levine, and I'm going to pass 2 arguments to it, and that is just separated by a comma. The first one is df.group equals 1, the age, and df group 2, that age. So I'm just passing the 2. I could say to list as well. I could have said dot age and other than specifying this. You know by now there's more than one ways of doing it. The point being, I'm passing the two sets of values to the Levine test, and it's also going to express a p-value for me. The null assumption is that the variances are equal enough, and the alternate hypothesis, if we have a small p-value, is that no, they are not equal enough. And there we go. We get a test statistic, which is 1.31 in this instance, and a p-value of 0.25. It's not less than 0.05. I cannot reject the null hypothesis, which by the Levine test here should state that these variances are close enough that I could still meet the assumptions for the use of parametric tests. So that's the next hurdle pass if you want to compare two sets of numeric, the mean of two sets of a variable between two groups or three groups or more. So the next one I want to talk to you about is just some statistical outliers. So another important assumption to be met is that there are no outliers. If there are outliers, you should not, if there are quite a few of them and they're quite far away from the mean, especially if it's all more or less, the assumption for the use of parametric tests is just not met. So one way we could go about this, again, as with the normality, is just to plot this. And we're going to use cut and paste there. So I'm going to do a box plot, and I'm going to do CRP of group 1, and I'm going to do CRP of group 2. And for box points, you've seen this one before. Remember before we had all when we put the jitter and the point pos in. This time I'm going to say box points equals outliers to force Plotly to do suspected outliers. And then the data and the trace, nothing different. Let's have a look at this. And if you look at this, there are quite a few statistical outliers beyond this upper fence for both of them. And we could expect that. We looked at the QQ plot before for CRP. And there's definitely, by this visual test, there's just too many outliers here. Another reason why I would not use a parametric test to compare the CRP between these two sets of patients. So that's the visual way, but there's also a statistical way, and that's to express every value as a standardized value. How many standard deviations away from the mean it is. And let me show you the code for that. You've got to construct that a little bit. So here we go, copy and paste. And there we go. So what have I done here? So I've said the df.crp minus df.crp.mean. So it's going to take every CRP level and it's going to subtract from that the mean. So some are going to be more than the mean, so you're going to get positive values, some are going to be less, and you're going to get negative values. So you're going to get this whole set of values, some being more or some being less than 0. There's some of the CRP that might be at the mean. But you just subtract everything from the mean. So what this is going to do, there's lots of values there, and there's only a single value there, but Python's clever enough to figure out the fact that it wants you to subtract that from each of the values in there. And then I'm going to divide by the standard deviation. The standard deviation of each of these values, so of each of these differences. So first of all, I'm subtracting the mean from each of the values. So I'm going to have a whole bunch of values, and then each of them I'm going to divide by the standard deviation. That's going to give me how many standard deviations away from the mean every value is. And then lastly, I'm going to say dot sort values, not two values, but sort values, because I just want them to be sorted. And there you go. So on the negative side, the furthest one away was patient number 358. Remember, it started counting from 0, so it's actually one more. But anyway, that patient had a CRP that was minus 1.1 standard deviations away from the mean. And I sorted them, so it's going to go in ascending order to the other side. And remember here, we had lots of values that were above the upper fence. Now, if we look at this here, we see on the positive side, there were a lot of values. And what we're looking for really here is values that are more than, it's a thumb suck, but more about 3 standard deviations away from the mean. And we can see there's quite a few here, 1, 2, 3, 4, 5, 6, 7 values that are more than 3 standard deviations away from the mean. And really that's too far. I would consider these as statistical outliers, and you've now got to decide whether you exclude them from the analysis. So exclude these patients manually. Then you have to redo all the other assumption tests and see if they are still met. But this is one way to legitimately decide to remove these patients. If you do, you've got to put that in the method section of your paper. Say that some of the patients have been removed from the analysis and say why, because they were more than 3 standard deviations away from there. So you've got to state this. Don't hide the fact. And I think sometimes this fact is hidden from us when we do read a journal paper, and that's wrong. State it clearly in your method section why this was done, so someone who reads your paper can decide, what kind of trust they want to put in this analysis. But you have to go through these steps. Let me reiterate that. Please always go through these steps of checking whether the assumptions for the use of parametric tests, that are students' t-tests, ANOVA, linear regression, or correlations, check that they are met. If they are not, you cannot use the normal parametric tests. Play with these, import some of your data sets that you have, and check whether your actual data meet these assumptions, now that you know how to do it. Now that you know that your data does meet some of the assumptions for the use of parametric tests, let's start off by looking at correlation and a little bit of linear regression. So what we're going to do, we're going to take 2 numerical variables. So they're going to form these little pairs, each pair from the same subject in your research, and we're going to look at how they are correlated. How does one affect the other? So let's have a look. Here we are in the Biostatistics Fundamentals using Python folder, and you will notice that we have a new spreadsheet here called correlation.xlsx. So we're going to talk about correlation and linear regression. Let's open up a new Python notebook, and I'm going to click on Untitled. Let's call it correlation. There we go. Now I'm going to import quite a few things. Most of it you've seen before, so I'm going to copy and paste from my second screen there. So pandas is PD, numpy is NP, scipy, from scipy at least import stats. And here's the new one, import statsmodels.api as SM. Statsmodels is a library that greatly extends the statistical modeling ability of Python, and we're certainly going to use that in this tutorial. Again, from Plotly offline, import my iPlot and init notebook mode. I initialize the notebook mode, and we're also going to do the high-level graph objects in Plotly. We're going to run this, and we're going to get a little warning. There is something in the stats model library that uses something in pandas, and it hasn't quite updated to the newest version, or at least the version that I'm running on this notebook. So you might see this kind of warning pop up. For the vast majority of time, you can just simply ignore that. So let's import our spreadsheet. I'm going to call it df as per usual. We're going to do pd.readExcel, read Excel, and the file we're looking for, remember, is correlation.slsx. There we go. Shift enter, shift return. It's imported. Let's have a look at the shape of this so we can see what the size of it looks like. We see there are 100 rows across 3 variables. Let's have a look at the first 5 of these rows. Let's do head, there we go. And we see we have 3 numerical variables, CRP, WCC, ESR, C-reactive protein, white cell count, and erythrocyte sedimentation rate. So 3 numerical variables. Correlation, we want to know, as one of these values change, does the other one change as well? So imagine, as always, that each of these rows represent one subject in our research project. So one subject had a CRP of 5.5, a white cell count of 13.2, and an ESR of 10. And we want to know, are there correlations between these values? First of all, we're going to stick to CRP and white cell count. Let's have a look at that. If we just look at CRP and white cell count. So what we're going to do, we want pairs of these values. So we're going to set CRP to be, let's make that the independent variable and white cell count the dependent variable. So as CRP changes, does white cell count for that specific patient change accordingly, and we're going to string all of them together. So here comes the big typing cheat. So I'm just going to copy and paste. You can pause and just copy this if you want to. So I'm going to start with a trace, and that's a scatter. So on the x-axis, we're going to have the CRP, and the y-axis, the white cell count. So that's going to make little pairs, a pair for each patient. The mode is markers, my tick size is 12. You see the color there, a bit of orange. And I'm going to do correlation between CRP and white cell count. So let's go and run this. There we go, we see correlation between CRP and white cell count. And can you see this? As CRP increases, it seems so does white cell count. There is definitely a correlation between these two. We all know statistics, we know that that does not prove causation, but there's a correlation, and it's a positive correlation because there's an increase in white cell count as CRP decreases. So that's the correlation. If we view this as a linear regression problem, we say that the dependent variable, white cell count, is dependent on this independent variable CRP. As CRP increases, so does white cell count. Given any CRP value, we can come up with a model that will predict this dependent variable white cell count. So that's very good. Now let's look at at another one. Let's do the CRP. Let's do CRP now as our independent variable and ESR as our dependent variable. And that's really the only thing that's changing here between correlation and linear regression. And correlation, we're just going to eventually do the correlation coefficient, and linear regression, we want a bit more, but they're all based on the same principles. So let's have a look at this. Not so well correlated at all. There certainly doesn't seem to be this pattern as CRP increases that ESR would increase. I would suggest that the correlation there is not so good, and if we do linear regression and we can actually measure or do statistical tests on this correlation, then it might not be so good. So under the assumption that my assumptions for the use of parametric tests have been met, let's have a look at correlation and Pearson correlations coefficient, or R. You've seen R in publications before. So that lives in stats, which is in SciPy, and it's just Pearson R. So Pearson R, and what it wants to take is just the two values separately, the value for one single pair, the one variable, comma the other variable. So that will be df, comma CRP was the first one, and the second one was df dot, let's make this white cell count. Remember, they were well correlated. And there we go. We see a correlation coefficient of 0.97. It's positive. Remember, it goes from +1 to -1. +1 being absolutely 100% correlated. They lie on a straight line, those dots. -1 being absolutely negatively correlated. In other words, the dots will go down towards from left top to right bottom. And we see a p-value there for this correlation coefficient there, indeed tiny, tiny, tiny. So now let's have a look though at linear regression. So that's stats.linearregress instead of stats.Pearson R. That's going to give us a bit more information, not only the correlation coefficient, but a bit more information. So let's run this line of code, and there we go. We see a linear regression. We see the slope there, the slope of the line, the coefficient. It's at 1.97. That means for every unit increase in the independent variable, there'll be a 1.97 increase in the dependent variable. So I can almost calculate what the CRP or what the white cell count is going to be given a CRP. There's an intercept of 1.35. That's the null model. And we see the R value there and its P value again. And this time we also see the standard deviation. So let me write a little markdown here. So I've changed this into a markdown cell, and I'm going to write in a language that is called LaTeX. So that is for mathematical equations. And to do that, you put these two $signs on both sides. That just indicates to the notebook that you want to center this. And I'm just going to write out what I see there. It says that y equals 1.970 thereabouts. That was my times x, plus the intercept was 1.315. Shift enter, shift return. So this is what I'm getting from this. I'm saying with linear regression, if I plug in the CRP value here, I multiply it by 1.97, that's the slope, and I add 1.315, that's the intercept, I'm going to get y, I'm going to get a white cell count. That is what the linear regression model is trying to tell us. So let's visualize this linear regression. So I've got a trace 0, which is just all my dots, and then on my second plot here, my trace number 1, I'm also doing a scatter plot, but you can see a few things. Let's do the first one down here, which says mode equals lines. We haven't seen this before, so instead of being markers, we want a line. And what I'm doing for my x-axis is I want a line space. So I'm going to go from 0 to the maximum of the CRP. And the number that I want in there is just going to be the length of the data frame. So I want the number of rows that there was. I want so many points between 0 and the maximum of the CRP. And on my y, I actually multiply 1.97 by each of these values, and I add the 1.316. Pause the video, have a look at this. It's not difficult to tease out, and that's just going to give us the ability to draw a straight line there. Everything else being exactly the same. There we go. And now we see this line, of which I showed you the equation there. I show you, there's this line, and you can see it follows these dots. The regression line does follow the dots. So given any CRP value, I can calculate what the white cell count should really be. So that's simple enough, but let's look at something that we know is not so well correlated. So let's look at the linear regression model. If we look at CRP and ESR, and if we look at that, definitely we see a p-value there of 0.58, so definitely not statistically significant there. We see a slope, and that slope is very close to 0, and our intercept there, R value, really bad. Near 0 means there's no correlation between these two as well. And you can see how you would construct your equation again. And let me copy and paste here so we can quickly have a look at this regression line. And once again, I'm just creating a bunch of x values using numpy.linspace from 0 to the maximum of CRP. And on my y-axis, I'm taking the slope, which was 0.182, multiplied by each individual one here in x, and I'm adding 30.336, which was my intercept there. And let's plot this and have a look. And there we see this line is certainly a lot flatter, so the correlation is much poorer. The slope there is a lot flatter, and hence we see that very poor p-value there, or I should say a p-value that's not significant. In the next section, I want to talk to you about multiple regression. Here we only had one independent variable, but we might have more than one independent numerical variable trying to predict an outcome variable. So let's have a look at multiple regression. That's why where we're going to have at least two independent variables trying to predict a dependent variable. Now we're going to use stats models, and we're going to use the ordinary least squares model to build this. And we've got to make a few changes though. There's a certain format in which we want our numbers, our variables, to go into this model. So what I usually do is create a new predictor data frame, and I'm just going to select out of that the columns or the variables that I'm interested in. And as you can see, it's double square brackets there, and I want CRP, and I want, let's do white cell count. So what this model is going to do, it's going to say, let's use CRP and white cell count as independent models, and we're trying to predict ESR. Now that doesn't make a lot of sense really clinically, but for the sake of this models. Now to have a linear regression model, you also need a column that contains all ones. That is our intercept. So I'm going to use this SM, remember we imported stats models. I'm going to say add constant, and I'm going to add the constant to x. So let's just have a quick look at what the first couple of rows looks like, so we can see what happened here. So I only have CRP and white cell count, ESR is gone, and I have this new column called constant, and every value there is 1, and you need that for a linear regression model. Now I also need y, and that is just my dependent variable. Remember that was df.esr. So if I just look at y.head, let's have a look at that quickly. That is just going to be this series just of the single variable, the outcome. So I want to say, can I use CRP and white cell count to predict ESR? I'm going to build that model. Now we've got to give the model a name, so I'm just going to call it model, and it is sm.ols, ordinary least squares. That's what we do. And we give the dependent variable first, and then the independent variables, which is x, and we call this method fit. We call this fit method. So it's going to fit this model given these parameters that I've given it. Shift enter, shift return, that model runs, and now we just want to look at what we came up with. So we're going to say print and then model dot the summary. There's a summary method there, and if we do that, there we go, our whole model right there. We can see the R value there, or adjusted R squared, the F statistic, the log likelihood, and we see our information values there. Let's have a look. That's our coefficients. The coefficient, the first line that you're going to see, that's the constant, so that's going to be the intercept. And we see the coefficients of CRP and white cell count. So as far as this model is concerned, there's a negative correlation with the CRP and the ESR and positive correlation with the white cell count. Remember, this is now a multidimensional model. We see the statistics there. We see the p-value of CRP and white cell count, and we see the 95% confidence intervals around this coefficient. So all the information that we might need should we write a report having created this model. So there you go. We have a univariate linear regression and our multivariate, or multiple at least, linear regression. And this is how you would use these. It's quite simple to do, quite powerful, quite easy to do in Python. Build your models, get your solutions, and it's very easy to get or to just write this up into a report. I'm still here at one of the libraries here at the University of Cape Town. In this section, we're going to talk about something that you will have to learn after looking at correlation, and that is linear regression. How do we predict a numerical variable given the values for independent variables? So let's have a look at linear regression. So what is linear regression all about? Well, it's about modeling. We have some data and we want to model an outcome. A model is an idealized object. And what modeling does is it predicts something. So given some data for across one or more variables, we want to predict the value in another variable. And the variables that we have that we're going to use to make our prediction with, those will be our independent variables, and the variable which contains the data that we want to actually predict, that is our dependent variable. That value depends on all the others. And that's a model. We have our data for our independent variables and we use that to calculate a predicted value for the dependent variable. Now that dependent variable actually has a value, and usually our prediction is not going to be exactly the same as the actual value, but we build models, idealized models, so that these predictions are as close as possible to the actual value. So let's get started. We're going to import the libraries. Let's have a look at the libraries that we're going to use in this section. Pandas, NumPy, and then from SciPy, we're going to import the stats module. So that's pretty standard when we analyze data. And then we're going to do some plotting. As we've seen in this course before, we're going to use graph objects from Plotly. We import that as Geo. But we're also going to make use of the new Plotly Express library. And that is just quick and easy plotting, very high level API. So very minimal code just to give us a quick plot. Not plots that I necessarily use when I'm submitting something for a research project to a journal, but very easy to use. And then from plotly.io, or at least we're going to import plotly.io as PIO, and we're going to then set pio.templates.default. We're going to set that to plotly white so that we have white backgrounds. And then also this nice library, stats models. Stats models really contains a lot of statistical functions. So we're going to import statsmodels.api as SM. If you haven't got stats models imported or into your system or downloaded onto your system, just drop a comment in the discussion down below, and I'll help you out with that. So import statsmodels.api as SM. There we go. Let's have a look in this first video also at this data set that we're going to use. And we're going to use the read underscore CSV function inside of Pandas, because the data is inside of a CSV file, comma separated values file. Remember, you can always save a spreadsheet file as a CSV file. There are many benefits to doing that. It just strips away all bells and whistles that something like Microsoft Excel will add to a file, and you just sit with the raw data.
So when you have a data set open in a spreadsheet program like Microsoft Excel, just say file save as and save it as a CSV instead of the proprietary format that your program uses. Let's have a look also then at the first 5 rows. A bit small there, but we can see we have NO2, that's nitrogen dioxide. We have PM2-5. Now that is particulate matter that is less than 2.5 micrometers in diameter. PM10, that is particles that are less than 10 micrometers in diameter. And then we have LDL, as in low density lipoprotein. So that's a type of cholesterol. And this is simulated data. It's not real world data, but it's modeled on a real research project that is published in a real journal. So using these nasty things in the atmosphere and seeing if they have an effect on someone's bad cholesterol levels. So that's quite interesting. Let's just have a look at the shape of the data, and we see that we have data on 209 subjects across these 4 variables. Now, no matter what we do, we're always going to start off with descriptive statistics. And the easiest way to do that is to just use this .describe function. So we have a look down there. We seem to have 290 under each of those, so no missing values, and we can see the mean of the NO2, the PM2.5, the PM10, and then the LDL cholesterol. We can see the standard deviation and everything else down this very familiar column. So always remember the df.describe. In this first video then, let's do the second part of what we always do initially, and that is just to look at data visualization. So we're just going to do quick histograms of this data, and we're going to use this Plotly Express. And look how easy this is. I'm going to give it a computer variable name, fig_NO2, and that's just px.histogram. And all I'm saying is where does the data come from? Well, the df data frame, and what column do I want NO2? And then it's just fig_NO2.show. As simple, really as simple as that. And we have a quick histogram here. And we're not going to be worried too much about it in this section on linear regression. Let's just look at all of them. We can get some idea of the distribution of our data. And there we go, all 4 of them. We see a bit of a weird distribution when it comes here to the LDL cholesterol. In the next section, we're really going to start looking then at first correlation, which you've seen before, you know everything about, and then we'll do some linear modeling. So let's have a look at correlation, which we definitely have seen before, and that is just where we take 2 numerical variables per subject in our data set, and we just compare those two. Are the 2 variables correlated? Does one increase as the other one increases? Does one decrease as the other one increases? So that's positive and negative correlation, or is it just all over the show? And for that, we use stats.pearson_r, and we just pass the 2 sets of values, the pairs. Now remember, there cannot be any missing data, so all of these data points have to be available for both variables for every subject. And if we do that, we see there's a very high correlation. Look at that. We have there a p-value for our correlation here of 1.96 times 10 to the power negative 51. Let's have a look at the correlation between the particulate matter that's less than 2.5 micrometers, and we see that is not, the correlation there is not so good. We see an R value then of 0.08. And let's look at PM10 and cholesterol, and we see the correlation there is also not so good. So really good for NO2, but not so much for the other 2. So just a quick review of how we do correlation. Now we need to step it up from there. We need to know, can we predict LDL cholesterol? That means if we build a model like this and we go out and we just collect these 3 variables, and we can predict someone's cholesterol. That's the whole idea here. So to do this, we need to do a few things. First of all, we're going to create 2 data frames, one just to hold our predictive variables, that is our independent variables, and I'm going to call those X. That is the usual thing to do. And what we just want to do from that is just remove the LDL column, because remember that is our dependent variable. So we can use the drop function here. So df.drop, what do we want to drop? The LDL column. We still have to tell pandas what axis this is. And remember, you can use axis equals 0, axis equals 1, and no one can ever remember which one is which one. But you can also just use the words. Is it rows or columns? Well, that LDL is a column. I want to drop that whole column. And then what I want to do is I want to save it not as a data frame, but just as a NumPy array. So I'm going to use this method .to_NumPy. So that's going to strip off everything about a data frame. It's going to strip off the column names, etc., the variable names. So we just have this array of values. And then y, my dependent variable, I should say, is df.ldl.toNumPy, so that I have a NumPy array there as well. Now, to build a linear model, we must have an intercept. Now, we're not going to go into the details of how ordinary least squares works and why we need a constant, but we need this for the mathematics to work out. So I'm going to use the sm.add_constant to x, and I'm going to save that back into x, overwrite x. So let's have a look. It's an array now. I can still use indexing, so let's look at the first 5 rows in this array of mine. So you can see what it's done is I've still got my 3 values here, my 37.7, so that was the NO2, the PM2.5, and the PM10. The PM10 was 129.7 and 71.5 there for the PM2.5 and 37.7 for the NO2. But I also have this column here of ones. That's what this add constant has done. We need those ones so that we can calculate really calculate the intercept. If you don't add that, you're going to get false values. So please do that. So there are various methods to use. We're going to use the easiest one, ordinary least squares, OLS. So we're going to save our model here in a computer variable called model, and that's going to be sm.ols. The first thing that we pass is our dependent variable, just y, that contains just a listing of all of our LDL values, and then the independent variables x. So we pass those two into our OLS function, and now we have a model. But we need some results from this model, so we need to fit all the data to our model. And we're going to save that in this variable called result. So model that we've just created, .fit, and we do that. And now we have the results. We just have to print them out to the screen. And what we do here is say result.summary. So let's go ahead and do that. And there we get, it's a bit small. Let's try and increase the size just a little bit for you there. There we go. And lots of information here. Information such as the hierarchy, information criteria, etc. Now these things are a bit advanced forms of looking at linear regression. We're not going to do that now. What we are interested in is just the results here and our adjusted R² value here. So we see an adjusted R², and it's adjusted because we don't have just one variable. We have 3 predictive variables and then the constant. And that gives us 5.43 for our adjusted R². Now, if we go down, we scroll down, we see coefficient, standard error, t, p-value, and then 0.25 there and 0.975. And then we see the values for constant, and then x1, x2, and x3. And that is just the way that we put in our x variable. The first column was just our constants, so that's why it says there constant. x1 was our NO2 column, x2 was our PM2.5 column, x3 would then be our PM10 column. And what these coefficients are, again, it's a little bit deeper theory of linear regression. They would be slopes of these hyperplanes. Think, for instance, of a line just on a flat piece of paper, and if it has an xy coordinate system, a line will have a slope. So if we were just to look at one single variable, that will have a slope, so all of these will have slopes. The p-value is pretty much what we know about. p-values that we know. So we see x1, NO2, remember that was highly correlated with the LDL cholesterol. So that has a tiny p-value. The x2, which was particulate matter 2.5, has a p-value of 0.883, and x3 0.46. So not significant there. So as far as this is concerned, they're not really predictive of this outcome that we have the cholesterol. So let's just make that a bit smaller. And what does all this mean for us? So let's just look at our first subject here. An NO2 level was 37.7, PM was 2.4 was 71.5 and 129.7, and the LDL cholesterol that we want to predict is 4.1. And now we have a model, because what the model will say with these coefficients is take the constant 0.978 and we times that with 1 because there was a 1 in that column, but anything times 1 is just 1, plus now we have this 37.7, we multiply it by its coefficient, and the coefficient is up here under coefficient, and x2, that's x1 I should say, is 0.1075, and there we have the 0.1075, and then we have the second coefficient times this 71.5 for PM 2.5, and then for PM10, which is 129.7, we multiply it by its coefficient. And if we do all of that, that is what our model says, we predict a value of about 3.8. But the actual value was 4.1, so not too bad. And that's what these coefficients are. That is what you multiply that variable value by. So you do the constant times 1, x1, this coefficient here, times the NO2, this one times the PM2.5, this one times the PM 10. And as you can see there, and that is your model. So let's just see how our model did in this video. We're going to use the zip function. Now what zip does inside of Python, it's just going to create little pairs of these values that we put in. So what are we putting in there? We're saying take the NP round function, and we're going to round this to 1 there so that we don't see all these decimal values. And we're going to use the results.predict. And what do we want to predict? All those x values. Remember, x only contained our independent variables, so we just want to predict, just get a list of those predictions. And then comma, what we want is y, that was the actual values, 0 to 5. So what the zip function is going to do, it's going to do 1 by 1. So the first subject, the second subject, the third subject. So its predicted value according to our model, and its actual value from the data itself. And then list. You've got to put that inside of a list as an argument to the list function, so you can actually list this to the screen. And there we go. There's our 3.8 rounded off from our 3.7, and the actual value is 4.1. For the second subject, we had an actual value of 4, and the model predicted 3.7. Third one had an actual value of 3.7, model predicted 3.7, and you can see the rest there. So that is how we use a model. We just we can just put the values in there and it will predict a value. And the OLS algorithm is going to, it is of such a nature that it is going to give us the best possible values for those coefficients so that our predicted values are as close as possible to the actual values. And now I can put any 3 new values in there plus the 1, and it'll give me a new prediction. And that is linear regression, simple linear regression, where we had our 3 independent variables trying to predict a dependent variable value.
Now that you know that your data meets the assumptions for the use of parametric tests, let's do some parametric tests. The famous student t-test. We're also going to look at other t-tests and also analysis of variance. We are going to compare the mean of the same variable amongst 2 or more groups. Let's have a look.
Eventually we get to the very exciting comparison of means. The vast majority of published research will show you a t-test, just comparing 2 means, or if we want to compare more than 2 means, we're going to use analysis of variance. It is so simple to do in Python. This is really going to be such a short and sweet tutorial. I'm going to just show you how to do a variety of t-tests inside of Python. So we'll see a new spreadsheet here, parametric.
.xlsx, and that's what we're going to use. So let's start a new notebook. I'm going to say new Python 3. Let's do this, and we're going to say comparing means. There we go. Now this is going to be very simple. I'm only going to import pandas, and I'm only going to import the stats submodule of the SciPy module. That's all we're going to need. Let's do df as our data frame, and that's going to be pd.read excel as per normal, and we have this parametric.slx. Let's have a look at the shape, df.shape of our data frame, and we see there are 4 variables and there are 300 patients or subjects in this research project. Let's have a look at the first 5 rows there, and we can see we have a group variable, we have treatment groups A and B it seems, and we have an age and cholesterol. So there we go. Let's have a look at what we can do. What kind of t-tests there are. The simplest t-test that you really get. Now again, the assumptions are that I've met the assumptions for the use of parametric tests. You know how to do that now, you know how to go through that. So let's just assume that this is true, and all I want to do is I want to make a claim. So my claim is going to be that the cholesterol has a mean of 6. So that's a one sample t-test. I'm comparing my sample of values to a fixed constant value. So where would you use that? You might use that when there is a new product on the market and you have a little test reagent, and the test reagent is supposed to measure something like a value of 6. So you do a bunch of tests and you see, and you want to verify this claim. Is there a difference between the mean of all these values that I do have and the value 6, the constant 6? So let's have a look at what the mean cholesterol is. Let's just have a look at that, cholesterol.mean. There we go, and indeed it is very close to 6. So it doesn't really make sense, a clinical sense, to do this kind of test in this setting, but we have a value there, so let's just do this one sample t-test. I just want to know, is there a statistically significant difference between the cholesterol values that I do have in my subset and the constant 6? So that's going to be stats dot, let's have a look, that's going to be t-test, and if I hit tab I can see all of the t-tests come up there, and this is the one I want, the one sample t-test. So I'm going to give it all my values, that is all the values of my cholesterol, and I want to know, is it statistically significantly different from 6? So there we go, and we see a t-statistic there of 0.0662699, etc., and a p-value of 0.94. So really, as we would expect, the mean was really 6, so there isn't a statistically significant difference between the mean of our cholesterol levels and that. I mean, if I were to do this, and imagine this is not cholesterol we're talking about, just think about the reagent example that I have, and suppose it was supposed to come out 4, you know, and now we are going to get a very statistically significant p-value, as you can see there. So that's not terribly exciting. The one that we all want to see that you can use most of the time is student's t-test. Student's t-test, so I'm going to compare the same variable between 2 groups. So I've got to have 2 groups, and between those they are independent of each other. That's very important. So I can't use monozygotic twins or before and after. Well, I have 2 separate groups, and I want to see if there's a difference in means between those 2 as far as a single numerical variable, continuous numerical variable is concerned. So let's do stats.t-test. So it's t-test, I'm going to hit tab, and the one I'm looking for there is t-test independent. You see the t-test related, so if you have related samples, or before and after samples, or homozygotic twins, or if there's some relationship between the 2 groups. But we want this independent one, and all we have to do now is just to list the 2 values. So the one is going to be, let's make it df. Let's have df dot, let's make it df dot treatment equals a, and from that we want the cholesterol values, cholesterol, if I can spell correctly, and the second group is going to be df dot treatment, and we're going to say equals b, and again dot cholesterol. So there we go. and we see we get a test statistic and a p-value. So for those two groups, there was not a statistically significant difference between the p-values. So you can say the t-statistic is 1.64, p-value 0.10. It is as simple as that. I just want to show you a little trick. There is a t-test, a little change in the mathematical equation. Should the variances not be equal, then we would say equal var equals false. So if we have unequal variances, there is this t-test for unequal variances, and all you have to do is just to put in this extra argument, and you see you're going to get slightly different values there. So that's how to do that. It is so simple. There's really nothing else to show you here. What if we wanted to do more than two means? Then we're going to move on to analysis of variance and get an F statistic and the p-value for that F statistic. So let's just see if we take groups 1, 2, and 3. There were 3 groups in this data set under the group column. I'm going to make 3 groups, and we're going to compare is there a difference in their age. So once again, by the magic of copying and pasting, there's the text. And the one-way analysis of variance we're looking for is F underscore one-way. Also in the stats submodule of the SciPy little library, big library, stats.f underscore one-way. And all we're going to do is just to list the 3 or more values there, or sets of values. Remember, it's the same variable, so it's age, and I've got different groups. So let's run that, and we get an F statistic, and we get a p-value. So there was no statistically significant difference. Remember, you've got to do this first before you do any post hoc analysis. So if this value was not statistically significant, this is where you have to stop. Only when it is less than 0.05 can you start looking at where the differences were. Was it between groups 1 and 2, or 2 and 3, or 1 and 3? You can't do that here. You have to stop here. And that's it. Students t-test and one-way ANOVA. It is so simple. I mean, obviously, you've got to know a lot about it in statistics, but to do it, to actually just sit down and do it, is so simple. Python makes it so simple. There you go. You can now do a variety of t-test and one-way analysis of variance. Off you go. Do your own analysis. So now that you're familiar with how to do your analysis when it comes to numerical variables, let's move on to categorical variables. Now, even though sometimes we can use numbers here, they don't really mean numbers. We're talking about categories. That's nominal and ordinal categorical variables. And we want to compare them. So we're going to have a look at the chi-square test for independence and the chi-square test for proportions. Let's have a look. So let's have a look at comparing categorical variables, where we can only count how many of a unique value in the sample space of a variable exists. The most important test, of course, is the chi-square test for independence. If I take two variables, is there some dependence between the two, or are they totally independent? So we're going to do the chi-square test for independence. We see that we have a new data set here, categorical.slsx. Let's do new, and Python 3 notebook. We're going to click on untitled, and I'm going to say comparing categorical variables. There we go. Comparing categorical variables. Let's go. Now, again, as with comparing the t-test, this is just so simple to do. I'm going to import only pandas and the stats sub-library of the SciPy library. So there we go, only those two. The data frame, we're going to say pd.read underscore Excel. There we go, and remember it was categorical.slsx. Let's have a look at the shape of it as per usual. There's 300 rows across 4 variables. Let's just have a look at the first 5 rows, and we see we have groups, which seems to be A and B's, treatments, which looks like it's 1, 2, and 3. A choice, 3, 2, 5, and immediately the red flag should go up, because even though those are numbers, it's probably ordinal categorical variables. There's some order to it, but those are not numbers. That is a choice between 1, 2, 3, 4, and 5, and specifically the outcome there as well. It's either dead or alive, or better or worse, whatever the case might be. Although there are numbers there, that is still a categorical variable. So let's not get confused with those. Now let's have a look just to count some of these things. So let's just have a look at the group. So let's do df.group, and we're going to say value counts. We say value counts because we know this is a categorical variable. So let's have a look, and there seems to be 158 cases of patients in group B and 142 in A. Remember, very simply, we can also express those as a percentage if we want. So df.group, and we're going to say value counts again, value counts, but this time we're going to use the normalize equals true argument, and I'm just multiplying it by 100, to give me the percentages there. So 52.7% and 47.3% of patients in those two groups. Very simple to do. Let's have a look at the treatment, just for argument's sake, just for some exercise. So df.treatment, and we're going to do some value counts there. And let's have a look, and we see 150, 90, and 60. And let's do choice again. Remember, we're not going to do dot describe. These are not numerical variables, so we're going to say df.choice. And we're again going to say value counts. We really don't want to say dot describe. So 69 patients chose 1 and 54 chose 2, etc. So we can express it as such. Now let's just have a look and see, have a look at groups and choices. So we know there are two groups, groups A and B. And if I separate them out, what were their choices? So how would we do that? Remember, that's df.group by, so we're going to group by the group, and the one that we want is the choice, and of that, let's just put that in the right spot there. That's got to be closed there, and then we're going to put choice. That looks better, if I can spell, and from there we want the value counts. Value counts, there we go. And now we're going to see two groups. So group A, where's the number 1? So 27 had choice 1 and 42 there had choice 2. So that's one way to go about it, and it's a bit difficult to read this. We can also put normalize in there, and it's going to give us the fractions or the percentages. But there is a nice little function called crosstab. So it's pd.crosstab. pd.crosstab, and what I can put in is what I want. So it's df.group on the one side, remember, and I want df.choice on the other side. Let's have a look at this, and this gives me this lovely little table. So I can see patients in group A and B there and what their choices were. So when it comes to how many chose 1, it was 27 and 42 for the two groups. How many chose choice number 2, 33 and 21, etc. Now I can ask myself the question, is choice and group, are they independent of each other, or is there dependence on one? If you're in a certain group, would that lead you to a certain proportion of choices there versus group B? So it's the chi-square test for independence, and that is what this is all about. And it is just so simple. It is actually an anticlimax most of the time as far as Python's concerned, just how easy things are. So it's in the stats model. So let's do that, stats, and it's chi2 underscore contingency. So chi-square, chi2 underscore contingency. And all I want to do is just pass this little table that I've just created. So I'm going to highlight that, copy it, and I'm going to pass that as an argument, paste. As simple as that. Shift enter, shift return, and have a look at that. So what do we get back? We get the chi-square value, which is 7.5, so you can actually write that in report. A p-value for that chi-square value is 0.11. And what you get here is 4 degrees of freedom, the 4 there, so it's 1 is chi-square, 2 is the p-value, 3 is the degrees of freedom, and here is your expected table. That was your observed table, and here's your expected table. So very simple now to write your report. You've got your chi-square, you've got your p-value, the degrees of freedom, you've got your observed and your expected table. And that's as simple as that. Chi-square test for independence. And in this section, we're going to talk about logistic regression. That's why we're going to use independent variables, and we're going to try and predict the outcome of a categorical variable. So we're going to build a model just to look at how we increase and decrease the odds of landing in one of the binary classes of the outcome variable. Let's have a look.
So let's start looking at logistic regression. In logistic regression, unlike linear regression, our dependent variable is categorical in nature. And what we're going to look at in this series is just a binary outcome, a dichotomous dependent variable. In other words, there are only two different elements in its sample space. Yes or no, alive or dead, improved or not improved. A categorical variable that only has a sample space of two values, and we usually call these classes. There are only two classes in this dependent variable or this outcome variable. Two, which means we can represent them numerically as a 0 and a 1. Now be very careful which one you choose as your 0 and which one of the two you choose as your 1, because that is under your control. The one that you're usually interested in is the one that you're going to set to 1. So if you're interested in looking at what factors predict death, then make dead 1 and alive 0. It's the one that you're interested in. And you can swap them around, and later on we'll see it just changes the meaning completely because it's just going to swap the numbers around. And instead of something causing an increase in death, now it's going to cause an increase in being alive, or a decrease then in death. And this decrease and increase is going to be called odds ratios. So we're going to have a look at those as well. So let's have a look then at the libraries that we're going to use. Pandas, NumPy, and from SciPy, the stats module. That is just the usual thing that we do. We're also then going to use Plotly, and in the video set on linear regression, we had a look at Plotly Express. So we're just going to use the graph objects and Plotly Express. And then also from stats model or statsmodels.api at least, we're going to import that as SM. Now let's have a look at the data. The data is in the same folder as this notebook, so you can just import it, and it's a comma-separated value file called logistic. And there we go, a bit small on the screen, but we can see a group age, CRP, white cell count, and then target. So this 1, 2, 3, 4, first 4, we might want to use as predictors of this target value. But you can see we have some problems. First of all, the group column here is written in words. Now, those are not numbers, and the same goes for the target. Okay, before we get to solving that, let's just have a look at how big our data set is. 500 subjects across these 5 variables, and we can just look at them, the data types. And as we said before, the group is an object, and the target's also an object. Age is saved as integers, and CRP and white cell count as floating point values. Now, as I've written here, the dependent variable values must be numeric, so we need to convert the A and B values. Now, for the argument here, we're going to choose B as our class of choice, the one that we are interested in, and we're going to encode that B as a 1 and the A as a 0. And that's very easy to do with pandas, so we're going to say our data frame.target, so it's that column, we're going to say replace, and we're going to use a dictionary for the replacement because it's dichotomous, a binary outcome, so we only have 2 to fill in here. We're going to use, as I say, just a dictionary. Dictionaries always go inside of curly braces, and we have a colon separating the values. So A, if it was the string A, I want to replace that with a 0, and if it was B, I want to replace that with a 1, and we're going to use inplace equals true argument because we want to overwrite the data frame permanently. So if we now have a look at the DF, we see this targets going 0, 1, 0, 0, 0, etc. So we've changed that, and the D types, the target is now an integer. And we're going to do the same with the groups, and we're going to replace them with numbers as well. So 1 is going to become 1, 2, 2, 3, 3, 4, 4. Still the replace function, nothing has changed. So let's have a look at that. In place is true, and now we have this. Now, I want you to be very careful when you do this for the dependent variables. As you can see here, our sample space is more than 2. There are 4 elements in the sample space. And how these things work, how logistic regression works is with categorical variables like this, one of them you have to choose as your base value. In other words, the others will be compared to if you fall into one of the other of those sample space elements. Does that increase or decrease your chance of being a 0 or a 1? And it is against some base value. Now, this was easy because we had 1, 2, 3, 4, but you might have something completely different, a nominal categorical variable, but one of them has got to be the base against which the others are measured, and make that base one 1. And when I explain to you what happens in the results section, you'll understand why.
So just choose the one which is the base. You might have a dichotomous one like male and female if you're just interested in the binary classification of gender, and you want to make males your base, and you want to see if you are a female compared to a male, does that increase or decrease your chance of being in the one target value? Or you might want to swap that around. Or in our instance here, we have 4 elements in our sample space, but one of them has to be the base against which the others are measured. Make that the one. In the next section, we'll do what we always do when we do any kind of data analysis. We'll start with descriptive statistics. So let's have a look at the descriptive statistics. First of all, let's just have a look at group, and we're just going to do a value counts there. Remember, even though we change them to numbers, this is still a categorical variable. And we see 138 was in group 1, 123 in group 4, 123, 119 in group 2. And remember, if we say normalize equals true, we're going to see a relative frequency. So just expressed as fractions. So 27.6%, 24.6%, etc. Let's have a look. By the way, they're sort of all in the same ballpark. So a good distribution, the equal distribution. If we look at the age column, we see all 500 are there, so there's no missing values. We see a mean of 44 and a median there, also 44. We can see the rest of our descriptive statistics there. Let's have a look at the CRP, and of course we'll have a detailed look at it if we are interested in the data itself. Now I've constructed it so this is simulated data, that there really isn't anything weird here, so I just want to remind you really to do this and to look at it carefully, but in this instance I will just go over it very quickly. We can look at the group by function here, so we're going to group by the target and then look at the value counts. And just to show you actually here that there's the crosstab function, so in pandas.crosstab, and then just pass your 2 categorical variables, and that's going to give you a nice cross-tabulated table. So we have groups 1, 2, 3, 4, and then target 0 and 1, and we can see how many there are in each. And that's perhaps a nicer way to express it than using the group by function as we did up here. So let's just describe the age according to the target. And we can see here there's a big difference, 50 versus 38, as far as the mean is concerned. Let's have a look at the CRP. CRP values 1.6 versus almost 2, or 1.7 versus almost 2. That's also quite a difference. And then when it comes to the white cell count, 10 versus 13. So it really seems as if there's a difference between which target group you fell in, 0 or 1. Let's just make sure of one thing. The important thing in this descriptive statistics, perhaps more important than anything else, is to look at the frequency of your actual dependent variable. And we see in group 1 or target B, which was our one of interest, we saw 256 versus 243. This is very important that we have almost the same number in these two. So say, for instance, your categorical variable consisted of 95% of cases being one of the sample space elements. Then there's no need to build a model because you can just predict that majority class and you'll be right 95% of the time. You'll only make a mistake in the other 5%. So it's quite important that when you build these models that you don't have what we call class imbalance. So there's a good balance here, 256, 243, so there's really not a lot wrong there. Remember to do all the other things, look for NaN values, and look at imputing the data for these missing values. Let's go on to data visualization though. So I'm going to create two, let's just look right at the end here, we're going to do toList. See there at the end, we're using the .toList function there. So we're going to say the df and then index on the df target that is equal to 0, take the group there, and do a value counts and save that as a list. And I'm going to save that as target 0 group counts and target 1 group counts. So if I do that, it makes it very easy for me to create a bar plot because I can use go.figure. We've seen this before in the data visualization. I'm using a bar plot. My x-axis I'm going to have 1, 2, 3, and 4. And on my y-axis I'm going to have all those counts that we've just created there as NumPy lists. And I'm just going to do that for target 1 as well, and just add some nice elements such as the title there and the axis labels, etc. And then we see there for target 0 and target 1 what the difference was in the counts
for our variable group. Let's just use the express chart. We're just going to create a quick box plot of the ages for the two targets, so target 0 and target 1, and we see there's quite a bit of difference in the ages between these two. Let's have a look at CRP, if there's anything interesting there. Well, it seems as if there's not really a normal distribution here. There seems to be a lot of outliers on the upper side, but not a big difference between our two target classes. And when we look at the white cell count, so almost similar. In the next section, we're going to just talk about odds ratios, because that is really, really important when it comes to just understanding what the results are going to look like when we do logistic regression. So this is not a lecture on odds ratios, but we are going to see the odds ratios when we look at the results of logistic regression. And I just want for you to consider the odds. Odds really are something like, imagine your favorite team plays 10 games, and they win 6 and they lose 4. The odds of winning are 6 to 4, because they won 6 and they lost 4. The odds are 6 to 4, 6 divided by 4. As simple as that. Now, an odds ratio really then is the ratio for comparing two different groups. In other words, we'd have the odds for two different teams with their win and loss, with the odds for the one and the win and loss odds for the other one, and it is the ratio between those two. And if a ratio is 1, it means there's really no increase or decrease in the chance of a specific outcome. Now remember, our outcome was B, and that was encoded as a 1. So increasing or decreasing your odds of falling into 1. So if it's a categorical variable, it's very easy. Let's start as simple as possible and make one of our predictive variables, our independent variables, as only a binary outcome, 0 or 1, yes or no. And one of them will be 0 again, one of them will be 1. And what the odds ratio would mean in those cases is if you are a 1 compared to a 0, does that increase or decrease your odds of falling into the 1 in your target or your dependent variable? If it's numerical, it's a bit different. It says that you increase or decrease your odds of falling into the 1 for your dependent variable for every unit increase in the numerical variable. So if it was age, the units there would be years. So 1 year, 2 year, 3 year. Okay, we'll go say patients from 18 years old, 18 to 19. So that 1 unit increases or decreases your odds of landing up in the 1 of your dependent variable. That's why we encode them as 0 and 1, and that's why the one that we're interested in, we make the 1. And then back to categorical variables where we have more than just a binary target or binary independent variable. So for instance, our group variable there, we had 4 elements, 1, 2, 3, and 4. And what we have to do here is to choose one of them as the base. And if we only had 2, it was very easy because it's 0 and 1. We make one of them the base, and that's why we encoded them as 1, 2, 3, 4. And it is compared to that 1. So if you are in group 2, compared to 1, does that increase or decrease your odds of landing in your dependent variable with a 1 or a B in our instance? If you are in group 3, does that increase or decrease your odds of landing in the 1 in the target variable compared to being a group 1 patient? So what we have to do is we have to create dummy variables. And I'm going to create a computer variable called dummies_group, and I'm going to use the getDummies function in pandas, so pd.getDummies. So it's in the df.group function. Because I'm going to create new variables, I've got to give them a prefix, and I'm going to use prefix group. And I've got to drop one of them. And it's the one that is the base that we are comparing to. And in our instance, we chose that to be 1, O-N-E 1, and we encoded that as the number 1. So that's the one that's going to be dropped. So drop first is true. And then I'm going to use the concat function, so pd.concat there. So I'm just going to concatenate this dummies_group data frame with our existing data frame, and I want to do that along the columns. And then just have a look at our new data frame. So let's just have a look here at group 1. This first patient was in group 2, and under the group 1 they get a 1 and a 0 and 0. The 0 indicates they weren't in group 3, they weren't in group 4, they were indeed in group 1.
And look at this number 3 here, or the 4th patient was in group 1, and it'll be a 0, 0, 0. A 0, 0, 0 meaning they were really in group 1. And that is how you have to set it up. Now, we don't want this group inside of our data set anymore, so we're just going to drop it from the axis columns and in places true. We really don't want that because we are using dummy variables now. Very important, choose the one that is the base against which the others are going to be measured, and drop that one when you create the dummies. So there we go. Let's create our logistic regression model. I'm going to use X to represent my independent variables and Y my dependent variable. So X is just df.drop, and we drop the target from there on down the axis, the columns axis, and then Y is just going to be df target. So I've split my dependent and my independent variables. Now, as with linear regression, we have to add this constant, one column, all of ones. Exact same thing. So we can use sm.addConstant to X, and there we go. If we now look at the first couple of 5 cases here, we'll see constant 1, 1, 1, 1, 1, 1 all the way down, and we see all the other ones. This is the format that you're finally going to import into your linear model. And then let's do y.head, and you can see 1, 0, 0, 1, etc. Now, in the last video, we're going to actually create a model and look at what it all means. So let's look at creating our model. And we're going to use the stats model library here, so sm dot and logit, whichever way you want to pronounce it, uppercase L. And then we're going to pass our dependent variable and then our set of independent variables, so y comma x, and then we've got to fit our data to this model, so model.fit, and we're going to save that in the result computer variable. So let's have a look at the results, and we can say result.summary. And there we go, it's a bit small. Let's increase the size so we can have a look at this. Now this is different from the linear regression. There's really a couple of differences that we have to look at. First of all, we are still going to get an r squared, but this time it's a pseudo r squared. Because of the way that the mathematics works, it's not a true r squared value, but it's a sort of derivation of that, and it gives us some idea of how good our model is doing. We are still going to see coefficients for constant age, CRP, white cell count, and then being in group 2, being in group 3, being in group 4. But these coefficients we have to express slightly differently. We also see p-values for these. So we see that the age was significant, the CRP was significant, the white cell count was significant, but being in group 2 or 3 or 4 was not really significant as a predictor of landing in the target class B, which we encoded as 1. And then we see 95% confidence intervals here, and that is around the coefficient that we see on this side. So what is this coefficient all about? It is not the same as linear regression in as much as we can't now take those values and multiply it, because what are we going to multiply it with when it comes to categorical variable? It simply doesn't work that way. So what we have here really are the odds ratios. Now, to express coefficients as odds ratios, we have to take the exponent of them. So that's E Euler's number to the power of the coefficient. So what I'm going to do here at the bottom is np.exponent and then results.params.values. So let's have a look at that. I'm just going to make it slightly smaller. So this params, that really refers to this coefficient. Okay, and what we see here is odds ratios. So the first one we're going to ignore because that's just our constant. It says when all the other values are 0, what is the odds ratio of landing in with a target class B that we encoded as 1? So let's just forget about that. The second one's the one of interest, and that is age. And we see a value there. It's expressed in scientific notation, but it's to the power 0. So that's just 1.2188654. There we go. Let me highlight it there so you can see it. 1.2, 1.22, for instance. So that's an odds ratio. Age has an odds ratio of 1.21. What does this mean? Remember, it's a numerical variable. And what it says that for every unit increase in age, you're going to increase the odds of landing in the target variable 1, the dependent variable B in our instance. It's going to increase your odds by 1.22 times.
What does that mean? Well, if it's more than 1, simply just subtract 1 from it. So 1 minus 1.22, that leaves you with 0.22. Express 0.22 as a percentage, that's 22%. So what odds ratio here means is for every unit increase in age, you increase your odds of being in 1 by 22%. As simple as that. Let's look at one of the groups there. You can see the coefficient there was let's take the last one, group 4, 0.422, because we can see here that we have an odds ratio of 1.52. Again, being in class 4 as compared to being in group 1 increases your odds of landing in target variable 1, so B, by 1.525 times. It's higher than 1, subtract 1 from it, that leaves you with 0.52, express 0.52 as a percentage, that's 52%. So you increase your odds of being in target group B by 52%, being in group 4 versus patients in group 1. And that's as simple as that. So with both categorical and numerical variables, you can now express the odds ratio. But we see here, when we come to something like group 3, we see p-values, and for group 3 and 4, that are not significant. It's higher than a chosen alpha value of 0.05. And if you look at these 95% confidence intervals, look at them. For the bottom one, it's a negative value. For the positive one, it's a positive. For the higher one, it's a positive value. Negative, positive, negative, positive. Whereas if we look at the 95% confidence intervals here of age, CRP, and white cell count, both of them are positive. Both of them are positive for CRP. Both of them are positive for white cell count. And what happens if you take the exponent of a value that's positive, it is going to be more than 1. And if you take the exponent of a value that's less than 0, it's going to end up being less than 1. Because let's express these confidence intervals now. So it's results.conf_int.values, and we take the exponent of all of them, and now we see these. So let's have a look at this last one. 7.8 times 10 to the power negative 1, that means 0.78. So it's 0.78 to 2.97, or 98 even. See this last one? That's the 95% confidence intervals around the odds ratio for group 4. Now we saw that the odds ratio was 1.52 here, 1.53. So we're going to say that it increases being in group 4 increases the odds of landing in target B by 53%. But we're not so confident about that 53%. No. Our odds ratio is from 0.78 to 2.97. If you have a number lower than 1, subtract it from 1. In other words, we're going to have here 1 minus 0.78. That's 0.22, so that's 22%. Up till this one here is bigger than 1, we're going to subtract 1 from it. That's 1.97. Express 1.97 as a percentage, that's 197%. So our confidence interval goes from a 22% decrease in the odds of being in B to a 197% increase in the odds. So if it goes positive and negative, when it comes to these 95% confidence intervals, you know that you're never going to get a significant p-value. They've both got to be negative or they've both got to be positive, because then our 95% confidence intervals will either both be on the side of decreasing the odds or on the side of increasing the odds. So I've left you some notes. Read through that just so that you know that this is all clear to you. Again, for this last one in group 4, it'll be the 95% confidence intervals will be a 22% decrease up to a 197% increase in the odds of being in target group B compared to, for patient in group 4 compared to a patient in group 1. Okay, I think you have a good understanding, a clear understanding now of how these odds ratios work. And as you've seen here in Python, it's very, very simple to do. Follow the recipe as I've set it out for you here, and you can do logistic regression.
Now, I hope you've enjoyed this course. It's really been a pleasure for me to show you, to introduce you to the fundamentals of biostatistics, using a computer language. Now what we're going to do in this last section, we're going to run through a demo research project. So we're going to set some research questions, we're going to import our data, and we're going to do the analysis, we're going to answer those questions. I hope you enjoy it.
So in the next couple of videos, I really want to take a project from start to finish. Just want to show you one way of going about it in just extracting that knowledge from your data set and answering a few research questions. Now, this is going to be loosely based on a journal article that was published, and I'll put the link in the description that accompanies these videos. Now, we don't have access to that data set, so we've just simulated some of that data, and it is saved in a CSV file called raw data. So just simulated to loosely based on what was generated in this article. So have a look at the article, get to know what it's about, and we'll simplify that a bit just so that we can run through the process of doing this. I am going to do it in the Google Colaboratory. So I am here in my Google Drive. I have navigated to the appropriate folder, my Google Drive, right online, and you can see everything is here. The IPYNB file is there, the CSV file, and the logo that I always use. So without further ado, let's just open up this IPython notebook. When I double click on it, it's going to say open with Colaboratory. You can just click on it down here if you want to. A new tab will open up as per usual, and the page will load with our IPython notebook or our Jupyter notebook. So up top, the file has already been named. I'm calling it SSI after spinal surgery. So that's skin and soft tissue infections. Now we've looked at this before. There are a few things that you have to do if you use the Colaboratory versus a Jupyter notebook on your local system. So I always start with from google.colab import files so that we can import files into this project. And then from ipython.display, we're going to import image just to show images on the screen as well. So to run this, we can just click on the little run button there. As always, you would notice on the side here, if I want to delete or link the cell or add a comment, and that is beautiful for just sharing your work with someone else because we can really just share this. I'm going to create a computer variable called logo, and that's going to be equal to files.upload. I'm going to call the upload functions from files that we imported here from google.colab import files. I'm going to call files.upload. And that'll keep spinning until I choose the file that I want to upload. And at the moment for me, this is in my pictures folder on my hard drive, and I'm going to choose that file. You'll see the upload counter move there. And now we have a file available, and you can see there 2 krg space logo space light.png. So I can just refer to this name that now exists online in the cloud for me to use inside of this notebook. So I'm going to use the image function that we imported here from ipython.display, and I'm going to pass the string here that is this name, and I'm just going to limit the width to 1200 pixels. And that is how I brand the majority of the research work that we do. So if we do share our research with colleagues or someone externally or within the research group, we always put our logo there. And this will be the normal start to. Now, of course, you don't have to go through any of this, but certainly if you work inside of a large organization or you share your work, this might be important to you. So, skin and soft tissue infections after open and minimally invasive surgery. You can see there the data that we are going to be after. Patients will have 2 types of surgery. Either it will be performed open or through minimally invasive techniques. And we're just going to look at who develops a skin and soft tissue infection, a surgical site infection or wound infection after these 2 procedures. Is the number of cases that develop, or the proportion of cases that develop wound infection, is it different for these 2? And we can certainly do that. So in the last part, before we really get going, I'm just going to upload the data file. And for that, we're going to use some libraries. That's import pandas as PD. We're going to import numpy as NP. That's as usual. From SciPy, we're going to import stats. And then my old favorite from plotly.offline, we're going to import iplot and init notebook mode. But remember, we don't call init notebook mode. We have to do it differently here in the co-laboratory. Then from plotly.graphObjects, we're going to just import that at least as Go. The little function that we have to create for co-laboratory so that we can see these plotly graphs inside of co-laboratory, that's just copy and paste. You can just, well, at least pause the video and type that in if you want to. You do need this to do plotly in co-laboratory. So let's run all of these. I can run that. I can create my definition there. And then we're going to upload the data file. So I'm going to call it data_file and again call files.upload because I want this to exist in the cloud so that I can use it. So I've navigated to my hard drive where this file exists, data.csv. I click on it and we'll see the upload counter go there, and this file now exists here as data.csv. So now I can just use df, create my computer variable, and that's going to be pd.read_csv, and I can refer to this data file. Let's have a look at the first 5 rows of data. And there we go. We've got these columns: SSI, gender, approach, pre-op, CRP, post-op CRP, pre-op albumin, and pre-op white cell count. Let's have a look at the dimensions, at least, of this data set that we do have. We see we have 189 observations. That's rows over 7 columns or 7 variables. And let's just have a look at the types. We see SSI is an object, gender is an object, approach is an object, pre-op CRP is an integer, pre-op post-op CRP is an integer, pre-op albumin is a floating point number, and pre-op white cell count a floating number as well. So in the next section, we're going to start looking at these research questions. The first question is going to be a descriptive statistics question, and many journal articles just describe the statistics before they do any inferential work. And then we have our 5 proper questions. We're going to ask, is the presence of skin and soft tissue infection independent from surgical approach? Is the presence of skin and soft tissue infection independent of gender? Is there a significant difference in the rise in CRP? So that's the difference between the before and after CRP, between the patients with and without SSI. Then we want to know if there's a significant difference in the preoperative albumin levels between the patients with and without the SSI. And is there a significant difference in pre-op white cell counts between patients with and without SSI? So those are our main research questions. And in between these videos, you can start to ponder what tests you will do to answer these questions. So let's just have a look at answering the descriptive statistics question. Notice where we're just going to simply take each variable and we're just going to describe it. So we're not going to create little subgroups or group by the data by anything. We're just going to describe what we have. So the first variable we had was gender. And if we look back up here, we note that gender there was an object. That means it's a categorical variable, and we know that it is nominal categorical at that. And for the sake of just a simple explanation in these videos, we're going to stick to binary classification of gender. So there'll only be male and female, and that does not reflect reality in any way. So we see here in our data set, calling gender the series, the column, .value_counts. So that's going to give us 108 females and 81 males. Remember, if we wanted to express this as a percentage, very easy. We're going to pass an argument to the value_counts function here, and we're going to call it normalized equals true. And we just multiply by 100 because otherwise we'll get a fraction back, and it broadcasts this times 100 to both of the values that we have. So it's 57% female and 43% then if we round off male, and that you can put in the description of your paper. Let's have a look, just a quick look at a contingency table, because in the end that is going to be one of our research questions. So I thought let's just throw it in very quickly. We just want to create this little table that gives us the skin and soft tissue infection on the one axis and the gender on the other axis, and we call pd.crosstab. And there we go, very beautiful there. We see patients who did not develop SSI, 95%, 95, the count was female, 67 was male. And those that did develop a skin and soft tissue infection, wound infection, 13 were female, 14 were male. Now, if we want to express this as percentage, we're just going to do it in a slightly different way, not as a nice table like this, but we can just do the group by. So df.group by SSI, the gender column we're interested in, value counts that, normalize being true, and multiply by 100. And certainly this is something that you can put in your report very easily. So those without SSI, 59% were female, 41% were male, and with, you'll see male and female, the proportions there. Let's have a quick look at the approach. So that was also a categorical variable, so we're going to call dot value counts, and we see there was 106 cases where the surgery was done open, just a normal old-fashioned technique, and minimally invasive through a scope that was done in 83 cases. Again, all we have to do is just say normalize equals true so that we can just get that expressed as a percentage. Makes it very easy for you to write your report. Very quickly and sneakily, let's run the cross tab there so we can see the distribution and just look at the percentages of that, doing it in exactly the same way. First, we take the data frame, we group by this column so that we get the yes and no's separately. What do we want separately analyzed? Well, the approach, and we want the numbers, but we want to normalize it and multiply by 100 to give us the percentage. Let's look at the CRP, C-reactive protein. We remember that that was a numerical value. And what we want to do here, because remember one of our research questions was, is there a difference between these two groups, those with and without infection, in the change of their CRP levels? So what we do here, we just create a new column, and we're going to have the post-op values and then subtract from that the pre-op values. As simple as that. And get is going to give us a new variable, a new column, and it's just the difference between those two. So let's have a look at this difference and just describe that. Since it is numerical data, we see there are 189 values. We see the mean difference of 2.7. We see the median there of 3. So very quickly, let's just group by the SSI and just describe that. And there we go, those without the skin and soft tissue infection, those with, and we can see the difference there. There was 27 in the one group, 162 in the other, but we see with this change, it went up, and the mean that it changed is 5 for those with infection and only 2.4 when they did not develop infection. So let's just plot that out a little bit. And just to give us the information, and this is really the part of the data analysis that I really do like. I just like to explore what is going on. And as I do this descriptive statistics, it says, oh, let me just plot that. Let me just group by this and have a quick look at that. That is really how you explore the data, how you start questioning the data, tease out of it the story that it's trying to tell you. So I might flip-flop all the way, look into this side, look into that side, just divide it a little bit further and look at it again, then plot it and then get the numbers. We are just playing around, just describing this data. So remember, if you want to do a Plotly cell, we've got to run this 2 lines of code, always with every cell to have Plotly inside of Colaboratory. If you run your notebook, your Jupyter notebook on a local system, of course you don't need this. So the plot itself, we're going to have 2 traces. They're both going to be box plots, so go.box. On the y-axis, we want the CRP delta for both of them. On the one side where the SSI is no, on the other side where SSI is yes. We see I name them, and I give a color to each of these, and I want the outliers. Data is then this list of 2 values, trace 0 and trace 1. And on the layout, I use this dictionary with title and y-axis and x-axis, and the x-axis, the key value pair there, but the value pair is the key value pairs. It's a dictionary in its own right. We've done this before. You can have a look again at those videos of how to create these plots. And there we go. We see the change in CRP, and there seems to be this huge difference between these two, those with the SSI and those without the SSI, and I can start thinking, is there going to be a statistically significant difference? I can sniff a statistically significant difference here. So let's just quickly look at the preoperative albumin. Remember, that that was a numerical variable, so we're going to describe that, not count it, and we see the descriptive statistic there. Or just for the sake of argument, I'm going to group the two groups and just compare those. They seem very close to each other. I wonder if there's going to be a statistically significant difference there. And then very easily just plot that. And the same sort of recipe that you've learned and you almost know by heart now. There we go. And notice that I've colored these in, so they are just ready for publication. And we see some statistical outliers there, which might make us concerned about the type of test that we can do to compare this. But as we see, it looks pretty close. Let's look at the white cell count, the description of it there. And if we just group them, let's have a look at that. There we go. And finally, just plotting them, pause the video, retype that, or just create your own plot. Put in the colors and all the different values that you want. We can see that this is really, really close. Good, that is how far we've come in this video. In the next video, we are just going to start doing the inferential statistics, doing the actual test so that we can answer these questions that we had. So let's start answering these research questions that we had. The first one that we had is there an independence between the development of the infection, yes or no, and the surgical approach, open or minimally invasive? And for that, we're going to use the cross tabulation, remember. So I'm going to use the cross tab to create that little contingency table for myself there, but it goes inside of a chi-squared test for independence. It is numerical variable against numerical variable. And the test that we use there is the chi-squared test for independence. Is there an independence between surgical site infection and surgical approach? Or are they dependent somehow on each other? We can look at that dependence by just looking at the counts and the percentages that we did before. So let's run that. It gives us a chi-square value, which is quite high there, and a p-value. And the p-value is less than 0.01 here. And that means these things are not independent of each other. They are dependent. And then we see the degree of freedom there, 1, and the expected table. We expected so many cases given the values that we had. So for a moment, let's just go back up. And here we are where we just did this cross tab here and the percentages there. So if we looked at patients here at the bottom, at the top who did not develop an SSI, we see that it was about 50-50. The types of procedures that they had. But if we look at those with infection, we see a big skew. The open ones seem to have a lot more percentage there of the infection than did the minimally invasive technique. That really is telling us here that it is your probability of getting an infection really has something to do with whether the case was done open or not. And you can see how skewed these values are. So we could really expect that there would be some dependence between the two. The next thing we're going to just ask the question is the development of this infection, is it independent of gender? And once again, it's a chi-square test and we can pass the cross tab directly to that. And we remember that there was an equal distribution amongst the males and females there. So we're really getting a low chi-square value. The p-value is not significant there. 1 degree of freedom and the expected table is listed there as well. Now let's move on to something a bit more interesting. We're going to look at the change in CRP. So we created this new column, CRP delta. This is how much did it go up before and after the surgery. And we want to know, is there a statistically significant difference between these two? So our hope is here just to do a parametric test of the difference between the two means. So I'm forming my two groups, looking at this variable CRP delta. Is there a difference between the two? First though, I've got to do all my tests for the assumptions of normality. I like to start off with the Shapiro-Wilk test, and I'm going to look at each group individually. So the first group that I'm choosing here, I'm going to call my data frame, and remember with the square brackets, we are just indexing then according to this column, and only where the value for that column is no, and for that we want the Shapiro-Wilk test on the CRP delta value. And we see our test statistic on the left-hand side and on the right-hand side, a tiny p-value. That's violated one of the assumptions. There's a statistically significant value here, p-value. We are rejecting the null hypothesis that this is from a population in which, the underlying population in which the this variable is normally distributed. We cannot use a parametric test. I'm not even going to test for anything else. I'm moving straight onto a non-parametric test. So I'm going to use the t-test equivalent in the non-parametric world, and that's the Mann-Whitney U test. So stats.Mann-Whitney U, and I pass the two lists of values. That first one is DF, and then the DF SSI column where there's no and the CRP delta values there, and where it's yes and the CRP. So I'm just creating the two values there. I have to use a two-sided p-value, two-sided test here. And we go two-sided alternative hypothesis, and then we see a test statistic, a U statistic, and a very small p-value. So there is a statistically significant difference between the two, and we can report those values from when we did the analysis before, where we just looked at the descriptive statistic. Let's have a look at the difference in preoperative albumin now. I'm going to run through my test for normality. So let's look at the pre-albumin levels for those without infection. And we see we can't reject the null hypothesis, so that's fine. For those with, we can't reject the null hypothesis there. Let's look for the variances being equal, and we're going to use the Bartlett test on both of these sets of values. Let's do the Bartlett test again. Now we see this highly significant p-value here, less than 0.01. My assumptions have failed. Again, I'm going to go on to the Mann-Whitney U test. Let's do the Mann-Whitney U test, and we see a p-value of 0.15. For argument's sake, let's just look at what the result would have been if we were to use the t-test for independence, a normal student's t-test. And we see the difference in p-values there. This p-value would have been 0.22. But it would be wrong to report that. In this case, both of them are not significant, so not a major problem, but just sticking to principles, we would use the Mann-Whitney U test. Let's have a look at difference in preoperative white cell count. My test for normality again. And we do the Shapiro-Wilk test. No problems there. Can't reject the null hypothesis. For those with can't reject the null hypothesis, let's look at the differences in variances with the Bartlett test. Not statistically significant. Lastly, let's have a look if we can see any outliers visually. So I've asked for box points to be the outliers in my Plotly graph here. And we can see from those without and those with, and we look at the white cell count, there's one little outlier there and one little outlier there. We see that was even a negative number, which makes no sense. That data was done incorrectly. By and large, though, this is not enough of statistical outliers to really be concerned about. We can go ahead with our test. In strict reality, though, what I would do is just go and have a look at this data collection of that negative 0.2 value, and if there was an error in that, just correct that error. For now, though, let's end this off. Assume that we are happy, and we're just going to do a normal student's t-test, and we see, as we expected from looking at these graphs, that there was never going to be a statistically significant difference between those. So there you go. That was one example of just approaching a problem and a few research questions. You can well see that this notebook environment is fantastic to do your analysis in, and also to share your analysis with someone else. This is a report. It exists. Everyone can see exactly what you did. These results are reproducible. You can really show the analysis that was done, and it's easily readable by someone who doesn't understand statistics even. We can really put in a nice little text in between all of these analyses, and really this all makes for a beautiful way to represent your research.